Ladies and gentlemen, it's my privilege to introduce the messenger lecturer, Professor Richard P. Feynman of the California Institute of Technology. Professor Feynman is a distinguished theoretical physicist, and he's done much to bring order out of the confusion which has marked much of the spectacular development in physics during the post-war period. Among his honors and awards, I will mention only the Albert Einstein Award in 1954. This is an award which is made every third year and which includes a gold medal and a substantial sum of money. Professor Feynman did his undergraduate work at MIT and his graduate work at Princeton. He worked on the Manhattan Project at Princeton and later at Los Alamos. He was appointed an assistant professor here at Cornell in 1944, although he did not assume residence until the end of the war. I thought it might be interesting to see what was said about him when he was appointed at Cornell, so I searched the minutes of our Board of Trustees, and there's absolutely no record of his appointment. There are, however, some 20 references to leaves of absence, salary, and promotions. One reference interested me especially. On July 31, 1945, the chairman of the physics department wrote the dean of the Arts College stating that Dr. Feynman is an outstanding teacher and investigator, the equal of whom develops infrequently. The chairman suggested that an annual salary of $3,000 was a bit too low for a distinguished faculty member and recommended that Professor Feynman's salary be increased $900. The dean, in an act of unusual generosity and with complete disregard for the solvency of the university, crossed out the $900 and made it an even $1,000. You can see that we thought highly of Professor Feynman even then. Feynman took up residence here at the end of 1945 and spent 5 highly productive years on our faculty. He left Cornell in 1950 and went to Caltech, where he has been ever since. Before I let him talk, I want to tell you just a little bit more about him. 3 or 4 years ago, he started teaching a beginning physics course at Caltech, and the result has added a new dimension to his fame. His lectures are now published in 2 volumes, and they represent a refreshing approach to the subject. In the preface of the published lectures, there's a picture of Feynman performing happily on the bongo drums. My Caltech friends tell me that he sometimes drops in on the Los Angeles night spots and takes over the work of the drummer, but Professor Feynman tells me that that's not so. Another of his specialties is safe cracking. One legend says that he once opened a locked safe in a secret establishment, removed the secret document, and left a note saying, "Guess who?" I could tell you about the time that he learned Spanish before he went to give a series of lectures in Brazil, but I won't. This gives you enough background, I think. So let me say that I'm delighted to welcome Professor Feynman back to Cornell. His general topic is the nature of physical law, and his topic for tonight is the law of gravitation, an example of physical law. Professor Feynman.
It's odd, but in the infrequent occasions when I've been called upon in a formal place to play the bongo drums, the introducer never seems to find it necessary to mention that I also do theoretical physics. I believe that's probably that we respect the arts more than the sciences. The artists of the Renaissance said that man's main concern should be for man. And yet, there are some other things of interest in the world. Even the artists appreciate sunsets and the ocean waves and the march of the stars across the heavens. And there is some reason then to talk of other things sometimes. As we look into these things, we get an aesthetic pleasure from them directly on observation. But there's also a rhythm and a pattern between the phenomena of nature, which isn't apparent to the eye, but only to the eye of analysis. And it's these rhythms and patterns which we call physical laws. What I want to talk about in this series of lectures is the general characteristics of these physical laws. That's even another level, if you will, of higher generality over the laws themselves. And it's really all I am talking about is nature as seen as a result of detailed analysis. But only the most overall general qualities of nature is what I mainly wish to speak about. Now, such a topic has a tendency to become too philosophical because it becomes so general that a person talks in such generalities that everybody can understand him, and it's considered to be some deep philosophy. However, I would like to be rather more special, and I would like to be understood in an honest way rather than in a vague way to some extent. And so, if you don't mind, I'm going to try to give, instead of only the generalities, in this first lecture, an example of physical law, so that you have at least one example of the things about which I'm speaking generally. In this way, I can use this example again and again to give an instance to make a reality out of something which would otherwise be too abstract. Now, I've chosen for my special example of physical law to tell you about the theory of gravitation, or the phenomena of gravity. Why I chose gravity, I don't know. Whatever I chose, you would have asked the same question. Actually, it was one of the first great laws to be discovered, and it has an interesting history. You might say, yes, but then it's old hat. I would like to hear something about science, more modern science. More recent, perhaps, but not more modern. Modern science is exactly in the same tradition as the discoveries of the law of gravitation. It is only more recent discoveries that we would be talking about. And so I do not feel at all bad about telling you of the law of gravitation, because I am, in describing its history and the methods, the character of its discovery and its quality, talking about modern science, completely modern. This law has been called the greatest generalization achieved by the human mind. And you can get already from my introduction, I'm more interested not so much in the human mind as in the marvel of nature who can obey such an elegant and simple law as this law of gravitation. So our main concentration will not be on how clever we are to have found it all out, but on how clever she is to pay attention to it. Now, what is this law of gravitation that we're going to talk about? The law is that two bodies or bodies exert a force upon each other, which is inversely as the square of the distance between them and varies directly as the product of their masses. And mathematically, we can write that great law down in formula, some kind of a constant times the product of the two masses divided by the square of the distance. Now, if I add the remark that a body reacts to a force by accelerating or by changing its velocity every second to an extent inversely as its mass. It reacts, changes velocity more if the mass is lower and so on, inversely as the mass. Then I have said everything about the law of gravitation that needs to be said. Everything else is a consequence, a mathematical consequence of those two things that I said. That's a remarkable enough phenomenon in itself that the next lecture will consider this in more detail. Now, I know you're not all here. I know some of you are, but you're not all mathematicians. And so you cannot all immediately see all of the consequences of these two remarks. And so what I would like to do in this lecture is to briefly tell you the story of the discovery, tell you what some of the consequences are, what the effect of this discovery had on the history of science, what kinds of mysteries such a law entails, something about the refinements made by Einstein, and possibly the relation to other laws of physics. The history of the thing, briefly, is this, that the ancients first observed the way the planets seemed to move about in the sky and concluded that they all went around, along with the Earth, went around the sun. This discovery was later made independently by Copernicus after they had forgotten that people had forgotten that it had already been made. Now, the next question that came up to study was exactly how do they go around the sun? That is, exactly what kind of motion? Do they go with the sun at the center of a circle, or do they go in some other kind of a curve? How fast do they move, and so on? And this discovery took longer to make. The times after Copernicus were times in which there were great debates about whether the planets in fact went around the sun along with the Earth, or whether the Earth was at the center of the universe, and so on. And there were considerable arguments about this. When a man named Tycho Brahe got an idea of a way of answering the question, he thought that it might perhaps be a good idea to look very, very carefully and to record where the planets actually appear in the sky, and then the alternative theories might be distinguished from one another. This is the key of modern science and is the beginning of the true understanding of nature, this idea that to look at the thing, to record the details, and to hope that in the information thus obtained may lie a clue to one or another of a possible theoretical interpretation. So Tycho, who was a rich man and owned, I believe, an island near Copenhagen, outfitted his island with great brass circles and special observing positions, situation chairs that you could look through little holes, and recorded night after night the position of the planets. It's only through such hard work that we can find out anything. When all these data were collected, they came into the hands of Kepler, who then tried to analyze what kinds of motions the planets made around the sun. And he did this by a method of trial and error. At one stage, he thought he had it. He figured out that they went around the sun in circles with the sun off center, and noticed that one planet, I think it was Mars, but I don't know, was 8 minutes of arc off, and he decided that this was too big for Tycho Brahe to have made an error, and that this was not the right answer. So because of the precision of experiments, he was able to proceed and to go on to another trial, and found, in fact, ultimately this. 3 things. First, that the planets went in ellipses around the sun with the sun of the focus. An ellipse is a curve all artists know about because it's a foreshortened circle, or children know about because somebody told them that if you take a string and tie it to 2 tacks and put a pencil in there, it'll make an ellipse. These 2 tacks are the foci, and if the sun is here, the shape of the orbit of a planet around the sun is one of these curves. The next question is, and going around the ellipse, how does it go? Does it go faster when it's near the sun, slower when it's further from the sun, and so on? We take away the other focus, we have the sun then and the planet going around. And Kepler found the answer to this too. He found this, that if you put the position of the planet down at 2 times separated by some definite time, let's say 3 weeks, and then at another place in the orbit, put the positions of the planets again separated by 3 weeks, and draw lines from the sun to the planet, technically called radius vectors. But anyway, lines from the sun to the planet, then the area that's enclosed in the orbit of the planet and the 2 lines that are separated by the planet's position 3 weeks apart is the same no matter what part of the orbit the thing is on. So that it has to go faster when it's closer in order to get the same area as it goes slower when it's further away, and in this precise manner. Some several years later, he found the 3rd rule, and that had not to do with the exactly motion of a single planet around the sun, but related the various planets to each other. And it said that the times that it took the planet to go all the way around was related to the size of the orbit, and that the times went as the square root of the cube of the size of the orbit, and for the size of the orbit is the diameter all the way across the biggest distance on the ellipse. So he has these three laws, which are summarized by saying it's an ellipse, and that equal areas are swept in equal times, and that the time to go around varies as a 3/2 power of the size, the square root of the cube of the size. So there's three laws of Kepler, which is a very complete description of the motion of the planets around the sun. The next question was, what makes them go around? Well, how can we understand this in more detail? Or is there anything else to say? In the meantime, Galileo was investigating the laws of motion. Incidentally, at the time of Kepler, the problem of what drove the planets around the sun was answered by some people by saying that there were angels behind here beating their wings and pushing the planet along around the orbit. As we'll see, that answer is not very far from the truth. The only difference is that the angels sit in a different direction and the wings go in a different direction. But the point that the angels sit in a different direction is the one that I must now come to. Galileo, in studying the laws of motion and doing a number of experiments to see how balls roll down inclined planes and pendulums swung and so on, discovered an idealization, a great principle called the principle of inertia, which is this: that if a thing has nothing acting on it, if an object has nothing acting on it and is going along at a certain velocity in a straight line, it will go at the same velocity at exactly the same straight line forever. Unbelievable though that may sound to anybody who has tried to make a ball roll forever, the idealization is correct, and that if there were no influences acting, such as the friction on the floor and so on, the thing would go at a uniform speed forever. The next point was made by Newton, who discussed the next question, which is, when it doesn't go in a straight line, then what? And he answered this way, that a force is needed to change the velocity in any manner. First, for instance, if you're pushing it in a direction that it moves, it will speed up. If you find that it changes direction, then the force must have been sideways. And that the force can be measured by the product of two effects. First, how much does the velocity change in a small interval of time? How fast is the velocity changing? How much is it accelerating in this direction, or how much is the velocity changing when it changes direction? That's called the acceleration. And when that's multiplied by a coefficient called the mass of an object, or its inertia coefficient, then that together is the force. One can measure for instance, if one has a stone on the end of a string and swings it in a circle over his head, then one can measure, when one finds one has to pull, the reason is that the speed of the velocity, the speed is not changing as it goes around the circle, but it's changing its direction, so there must be perpetually an in-pulling force. And this is proportional to the mass, so that if we were to take two different objects, first swing one, and then swing another one at the same speed around the head and measure the force in the second one, that second one, the new force is bigger than the other force in the proportion that the masses are different. This is a way of measuring the masses, by how hard it is to change the speed. Now, then Newton saw from this that, for instance, to take a simple example, if a planet is going in a circle around the sun, no force is needed to make it go sideways tangentially. If there were no force at all on it, it would have just keep coasting this way. But actually, the planet doesn't keep coasting this way, but finds itself later not out here where it would go if there were no force at all, but further down toward the sun. In other words, its velocity, its motion, has been deflected toward the sun. So what the angels have to do is to beat their wings in toward the sun all the time. That the motion to keep it going in a straight line has no known reason. The reason why things coast forever has never been found out. The law of inertia is no known origin. So the angels don't exist, but the continuation of the motion does. But in order to obtain the falling operation, we do need a force. So it became apparent that the origin of that the force was toward the sun. As a matter of fact, Newton was able to demonstrate that the statement that equal areas are swept in equal times was a direct consequence of the simple idea that all of the changes in velocity are directed exactly to the sun, even in the elliptical case. And maybe I'll have time next time to show you how that works in detail. So from this law, he would confirm the idea that the force is toward the sun. And from knowing how the periods of the different planets vary with the distance away from the sun, it's possible to determine how that force must weaken at different distances, and he was able to determine that the force must vary inversely as the square of the distance. Now, so far, he hasn't said anything. Yes, because he only said two things which Kepler said in a different language. One is exactly equivalent to the statement that the force is toward the sun, and the other is exactly equivalent to the statement that the law is inversely as the square of the distance. But people had seen in telescopes the Jupiter's satellites going around Jupiter, and it looked like a little solar system. So the satellites were attracted to Jupiter. And the moon is attracted to the Earth, and this goes around the Earth, is attracted the same way. So it looks like everything's attracted to everything else. And so the next statement was to generalize this and to say that every object attracts every other object. If so, the Earth must be pulling on the moon, just as the sun pulls on the planet. But it's known that the Earth pulls on things because you're all sitting tightly in your seats in spite of your desires to float out of the hall at this time. The pull for objects on the Earth was well known in the phenomenon of gravitation. And it was Newton's idea then that maybe the gravitation which held the moon in the orbit also applied, was the same gravitation that pulled the objects toward the Earth. Now, it is easy to figure out how far the moon falls in 1 second. Because if it went in a straight line, you know the size of the orbit, you know it takes a month to go around, and if you figure out how far it goes in 1 second, you can figure out how far the circle of the moon's orbit has fallen below the straight line that it would have been in if it didn't go the way it does go. And this distance is 1/20th of an inch. Now, the moon is 60 times as far away from the Earth's center than we are. We're 4,000 miles away from the center, and the moon is 240,000 miles away from the center. So if the law of inverse square is right, an object at the Earth's surface should fall in 1 second by 1/20th of an inch times 3,600, being the square of 60, because the force has been weakened by 60 times 60 for the inverse square law in getting out there to the moon. And if you multiply a 20th of an inch by 3,600, you get about 16 feet. And lo, it is known already from Galileo's measurements that things fell in 1 second on the Earth's surface by 16 feet. So this meant, you see, that he was on the right track. There was no going back now. Because a new fact that was completely independent previously, which is the period of the moon's orbit and its distance from the Earth, was connected to another fact, which is how long it takes something to fall in 1 second. So this was a dramatic test that everything's all right. Further, he had a lot of other predictions. He was able to calculate what the shape of the orbit should be if the law were the inverse square, and found indeed that it was an ellipse. So he got 3 for 2, as it were. In addition, a number of new phenomena had their obvious explanations. One was the tides. The tides were due to the pull of the moon on the Earth. This had sometimes been thought of before, with the difficulty that if there's the pull of the moon on the Earth being here, the water's being pulled up to the moon, then there would only be one tide a day where that bump of water is under the moon. But actually, you know, there are tides every 12 hours roughly, and that's 2 tides a day. But there was also another school of thought that had a different conclusion. Their theory was that it was the Earth that was pulled by the moon away from the water. So actually, Newton was the first one to realize what actually was going on. That the force of the moon on the Earth and on the water is the same at the same distance and that the water here is closer to the moon, and the water here is further from the moon than the Earth, than the rigid Earth, so that the water is pulled more toward the moon here, and here is less toward the moon than the Earth, so that it's a combination of those two pictures that makes double time. Actually, the Earth does the same trick as the moon. It goes around a circle, really. I mean, the force of the moon on the Earth is balanced, but by what? By the fact that just like the moon goes in a circle to balance the Earth's force, the Earth is also going in a circle. Actually, the center of the circle is somewhere inside the Earth. It's also going in a circle to balance the moon. So the two of them go around a common center here. And if you wish, this water is thrown off by centrifugal force more than the Earth is, and this water is attracted more than the average of the Earth. At any rate, the tides were then explained in the fact that there were two a day. A lot of other things became quite clear. Why the Earth is round, because everything gets pulled in. And why it isn't round, because it's spinning so that the outside gets thrown out a little bit and it balances. And why the sun and moon are round, and so on. Now, as the science developed and measurements were made ever more accurately, the tests of Newton's law became much more stringent. And the first careful tests involved the moons of Jupiter. By careful observations of the way they went around over a long period of time, one could be very careful to check that everything was according to Newton. And it turned out not to be the case. The moons of Jupiter appeared to be first get sometimes to 8 minutes ahead of time and sometimes 8 minutes behind schedule, where schedule is the calculated values according to Newton's laws. It was noticed that they were ahead of schedule when they were close, when Jupiter was close to the Earth, and behind schedule when it was far away, a rather odd circumstance. And Mr. Römer, having confidence in the law of gravitation, came to an interesting conclusion, that it takes light some time to travel from the moons to the Earth, and that what we're looking at when we see the moons are not how they are now, but how they were the time ago that it took the light to get here. Now, when Jupiter's near us, it takes less time for the light to come, and when Jupiter's further, it takes longer time, so he had to correct the observations for the differences in time, and by the fact that they were this much too early or that much too late, was able to determine the velocity of light. This was the first demonstration that light was not an instantaneously propagating material. I bring this particular matter to your attention because it illustrates something. That when a law is right, it can be used to find another one. That by having confidence in this law, if something is the matter, it suggests perhaps some other phenomenon. And if we had not known the law of gravitation, we would have taken much longer to find the speed of light, because we would not have known what to expect of Jupiter's satellites. This process has developed into an avalanche of discoveries. Each new discovery permits the tools for much more discovery, and this is the beginning of that avalanche, which has gone on now for 400 years in a continuous process, and we're still avalanching along at high speed at this time. Another problem came up. The planets shouldn't really go in ellipses because, according to Newton's laws, they're not attracted only by the sun, but also they pull on each other a little bit, only a little bit, but a little bit is something, and will alter the motion a little bit. So Jupiter, Saturn, and Uranus were big planets that were known, and the calculations were made as to how slightly different than the perfect ellipses of Kepler the planets ought to be going, Jupiter, Saturn, and Uranus, by the pull of one on each other. And when they were finished, the calculations, and the observations, it was noticed that Jupiter and Saturn went according to the calculations, but that Uranus was doing something funny. Another opportunity for Newton's laws to be found wanting, but courage. Two men, both who made these calculations, Adams and Leverrier, independently and at almost exactly the same time, proposed that the motions of Uranus were due to an unseen as yet new planet. And they wrote letters to their respective observatories telling them to look. Turn your telescope and look there and you'll find a planet. How absurd, said one of the observatories, that some guy sitting with pieces of paper and pencils can tell us where we'd look to find something new planet. And the other observatory was the administration was different. And they found the Neptune. More recently, in the beginning of the 20th century, it became apparent that the motion of the planet Mercury was not exactly right. And this caused a lot of trouble and had no explanation until a modification of Newton's. This did show ultimately that Newton's laws were slightly off and that they had to be modified. I will not discuss the modification in detail. It was made by Einstein. Now the question is, how far does this law extend? Does it extend outside the solar system? And so I show on the first slide evidence that the law of gravitation is on a wider scale than just the solar system. Here is a series of 3 pictures of a so-called double star. There's a third star, fortunately, in the picture, so you can see that they're really turning around and that nobody just simply turned the frames of the pictures around, which is easy to do on astronomical pictures. But the stars are actually going around. And by watching these things and plotting the orbit, you see the orbit that they make on the next slide. It's evident that they're attracting each other and that they're going around in an ellipse. According to the way expected, these are a succession of pictures going for all these different periods of time. I think, yes, it goes around this way. They didn't see it well when it was too close, and here it is in 1905. My slide is very old. It's gone around maybe once more since. And you'll be happy except when you notice, if you have noticed already, that this center is not a focus of the ellipse, but it's quite a bit off. So something's the matter with the law. No. God hasn't presented us with this orbit face on. It's tilted at a funny angle. And if you take an ellipse and mark its focus and then hold the paper at an odd angle and look at it in projection, the focus doesn't have to be at the focus of the projected image. So it's because its orbit is tilted in space that it looks that way. It looks like it's not the right pattern. But it's all right, and you can figure everything out satisfactorily for that. How about a bigger distance? There's forces between the stars. Does it go any further than these distances which are not more than 2 or 3 times the solar system's diameter? Here's something in the next slide that's 100,000 times as big as the solar system in diameter. And this is a large number of stars. Tremendous number of stars. This white spot is not a solid white spot. It's just because of the failure of our instruments to resolve it. But are very, very tiny dots, just like the other stars, well separated from one another, not hitting each other, each one falling through and back and forth through this great globular cluster. It's one of the most beautiful things in the sky, as good as sea waves and sunset. And the distribution of this material, it's perfectly clear that the thing that holds this together is the gravitational attraction of the stars for each other. And the distribution of the material in the sense of how the stars peter out as you go out in distance permits one to find out roughly what the law is of force between the stars, and of course it comes out right that it is roughly the inverse square. The accuracy of these calculations and measurements is not anywhere near as careful as in the solar system. Onward, as gravity extends still further. This is a little pinpoint inside of a big galaxy, and the next slide shows a typical galaxy. And it's clear that this thing again is held together somehow, and the only candidate that's reasonable is gravitation. But when we get to this size, we haven't any way any longer to check the inverse square law. But there seems to be no doubt that these great agglomerations of stars and so these galaxies, which are 50 to 100,000 light years across, the solar system is, well, from the Earth to the Sun is only 8 light minutes. This is 100,000 light years that the gravity is extending even over these distances. And in the next slide is evidence that it extends even further. Here is what is called a cluster of galaxies. There's a galaxy here and here and here. There are galaxies here. They're all in one lump of galaxies, analogous to the cluster of stars, but this time what's clustered are those big babies that I showed you in this previous slide. Now this is as far as is about 1/10, or well, 100th maybe, of the size of the universe, and as far as we have any direct evidence that gravitational forces extend. So the Earth's gravitation, if we take the view, has no edge, as you may read in the newspapers, when the planet gets outside the field of the gravitation. It keeps on going, ever weaker and weaker, inversely as the square of the distance, dividing by 4 each time you're twice as far away, until it mingles with the strong fields and gets lost in the confusion of the strong fields of other stars, but altogether with the stars in its neighborhood pulls the other stars to form the galaxy, and altogether they pull on other galaxies to make a pattern, a cluster of galaxies. So the Earth's gravitational field never ends, but peters out very slowly in a precise and careful law, probably to the edges of the universe. The law of gravitation is different than many of the other, is very important in the economy or in the machinery of the universe. There are many places where gravity has its practical applications as far as the universe is concerned. But atypically, among all the other laws of physics, gravitation has relatively few practical applications. I mean, the new knowledge of the law, it has a lot of applications. It keeps people in their seats and so on. But the knowledge of the law has few practical applications, relatively speaking, compared to the other laws. This is one case in which I picked an atypical example. It is impossible, by the way, by picking one example of anything, to avoid picking one which is atypical in some sense. That's the wonder of the world. The only applications I could think of were first in some geophysical prospecting, in predicting the tides, nowadays, more modernly, in working out the motions of the satellites and planet probes and so on that we send up, and also modernly to calculate the predictions of the planet's position, which have great utility for astrologers to publish their predictions and horoscopes in the magazines. That's the strange world we live in, that all the advances in understanding are used only to continue the nonsense which has existed for 2,000 years. Now, that shows that gravitation extends to the great distances, but Newton said that everything attracted everything else. Do I attract you? Do I attract you? I was going to say, do I attract you physically? I didn't mean that. What I mean is, is it really true that two things attract each other? Can we make a direct test and not just wait for the planets and look at the planets to see if they attract each other? And this experiment, the direct test, was made by Cavendish on equipment which you see indicated on the next slide. If I got my slides right. Well, I made a mistake. I was talking about the importance of the gravitation. I was overwhelmed by my clever remark about astrologers and forgot to mention the important places where gravitation does have some real effect in the behavior of the universe. And one of the interesting ones is the formation of new stars. In this picture, which is a gaseous nebula inside our own galaxy, and there's not a lot of stars, but it's gas, there are places where the gas has been compressed or attracted to itself here. It starts, perhaps, by some kind of shock waves to get collected, but the remainder of the phenomenon is that gravitation pulls the cloud of gas closer and closer together. So big mobs of gas and dust collect and form balls, which, as they fall still further, the heat generated by the falling lights them up, and they become stars. And we have in the next slide some evidence of the creation of new stars. It is, unfortunately, harder to see than I thought it was when I looked at it before. But this is not exactly the same as this. This bump here is further out than here, and that this also has a new dot here. I have found better examples, but we're unable to produce a slide. There is one example of a star patch, a light that grew in a place within 200 days. So that when it was in the same kind of condition of a gas cloud, when the gas collects too much together by gravitation, stars are born. And this is the beginning of new stars. So the stars belch out dirt and gases when they explode sometimes, and the dirt and gases then collect back again and make new stars. Sounds like perpetual motion. I now turn to the subject I meant to introduce, which was the experiments on the small scale to see whether things really attract each other. And I hope now that the next slide does indicate, this is the second try, Cavendish's experiment. The idea was to hang by a very, very fine quartz fiber a rod with two balls, and then put two large lead balls in the positions indicated here next to it on the side. Then, because of the attraction of the balls, there would be a slight twist of the fiber. It had to be done so delicately because the gravitational force between ordinary things is very, very tiny indeed. And there it was. And it was possible then to measure the force between these two balls. Cavendish called his experiment weighing the Earth. We're pedantic and careful today. We wouldn't let our students say that. We would have to say they're measuring the mass of the Earth. But the reason he said that is the following. By a direct experiment, he was able to measure the force and the two masses and the distance and thus determine the gravitational constant. You say, yes, but we have the same situation on the Earth. We know what the pull is, and we know what the mass of the object pulled is, and we know how far away we are, but we don't know either the mass of the Earth or the constant, but only the combination. So by measuring the constant and knowing the facts about the pull of the Earth, the mass of the Earth could be determined. So indirectly, this experiment was the first determination of how heavy or how massive is the ball on which we stand. It's a kind of an amazing achievement to find that out, and I think that's why Cavendish named his experiment that way instead of determining the constant in the gravitational equation. Weighing the Earth. Oh. He incidentally was weighing the sun and everything else at the same time. Because the pull of the sun is known in the same manner. Now, one other test of the law of gravitation is very interesting, and that is the question as to whether the pull is exactly proportional to the mass. If the pull is exactly proportional to the mass and the reaction to forces, the motions induced by forces, the changes in velocity, are inversely proportional to the mass, that means that two objects of different mass will change their velocity in the same manner in a gravitational field. Or two different things, no matter what their mass, in a vacuum, will fall the same way toward the Earth. That's Galileo's old experiment from the Leaning Tower. I took my young son of 2.5 to the Leaning Tower of Pisa, and now every time a guest comes, he says, Leaning Tower. So, anyhow, it means, for example, that in a satellite, a man-made satellite, an object inside will go around the Earth in the same kind of an orbit as a satellite on the outside and thus float in the middle, apparently. So that this fact that the force is exactly proportional to the mass and that the reactions are inversely proportional to the mass has this very interesting consequence. The question is, how accurate is it? And it has been measured by an experiment by a man named Ertvoss in 1909 and very much more recently and more accurately by Dickey. And it is known that 1 part in 10,000 million, the mass is exactly proportional. The forces are exactly proportional to the mass. How it's possible to measure with that accuracy, I wish I had the time to explain, but I'm afraid I cannot. It's remarkably clever. I'll give a hint, Howard. I'll give one hint there. Suppose that you wanted to measure whether it's true for the pull of the sun. You know, the sun is pulling us all. It pulls the Earth, too. But suppose you wanted to know whether you had a piece of lead here and a piece of copper here, or polyethylene and lead. It was first done with sandalwood. Now it's done with polyethylene. Whether the pull is exactly proportional to the inertia. The Earth is going around the sun, so these things are thrown out by inertia. And they're thrown out to the extent that these two objects have inertia. But they're attracted to the sun to the extent that they have mass in the attraction law. So if they're attracted to the sun in a different proportion than they're thrown out by inertia, one will be pulled toward the sun and the other away. And so hanging on another one of those Cavendish quartz fibers, the thing will twist toward the sun. It doesn't twist to this accuracy. So we know that the sun's attraction for these two objects is exactly proportional to their centrifugal effect, which is inertia. So the force of attraction on an object is exactly proportional to its coefficient of inertia. In other words, its mass. I should say something about the relation of gravitation to other forces, to other parts of nature, other phenomena in nature, and I'll have more to say of a general quality later. But there is one thing that's particularly interesting, and that is that the inverse square law appears again. It appears in the electrical laws, for instance, that electricity also exerts forces inversely as the square of the distance, this time between charges. And one thinks perhaps inverse square of the distance has some deep significance. Maybe gravity and electricity are different aspects of the same thing. No one has ever succeeded in making gravity and electricity different aspects of the same thing. Today, our theories of physics, the laws of physics, are a multitude of different parts and pieces that don't fit together very well. We don't understand the one exactly in terms of the other. We don't have one structure from which all is deduced. We have several pieces that don't quite fit exactly yet. And that's the reason why in these lectures, instead of having the ability to tell you what the law of physics is, I have to talk about the things that are common to the various laws, because we don't understand the connection between them. But what's very strange is that there are certain things that are the same in both. But now let's look again at the law of electricity. The law goes inversely as the square of the distance. But the thing that is remarkable is the tremendous difference in the strength of the electrical and gravitational laws. People who want to make electricity and gravitation out of the same thing will find that electricity is so much more powerful than gravity that it's hard to believe they could both have the same origin. Now, how can I say one thing is more powerful than another? It depends upon how much charge you have and how much mass you have. I'm certainly, you can't talk about how strong gravity is by saying I take a lump of such and such a size, because you chose the size. If we try to get something that nature produces her own pure number that has nothing to do with inches or years or anything to do with our own dimensions, we can do it this way. If we take the fundamental particles, such as an electron, any different ones will give different numbers, but to get an idea of the number, take electrons. 2 electrons, a fundamental particle. It's an object. It's not something I don't have to tell you what units I measure in. It's 2 particles, the fundamental particles. And they repel each other inversely as the square of the distance due to electricity. And they attract each other inversely as the square of the distance due to gravitation. Question: what is the ratio of the gravitational force to the electrical force? And that is illustrated on the next slide. The ratio of the gravitational attraction to the electrical repulsion is given by a number with 42 digits. And goes off here. This is written very carefully out, so that's 42 digits. Now, therein lies a very deep mystery. Where could such a tremendous number come from? That means if you ever had a theory from which both of these things are to come, how could they come in such disproportion? From what equation has a solution which has, for one, 2 kinds of forces, an attraction and a repulsion, with that fantastic ratio? People have looked for such a large ratio in other places. They're looking for a large number. They hope, for example, that there's another large number. And if you want a large number, why not take the diameter of the universe to the diameter of a proton? Amazingly enough, it also is a number with 42 digits. And so an interesting proposal is made that this ratio is the same as the ratio of the size of the universe to the diameter of a proton. But the universe is expanding with time. And that would mean the gravitational constant is changing with time. And although that's a possibility, there's no evidence to indicate that it's in fact true, and there are several difficulties, partial indications that it doesn't, that the gravitational constant has not changed in that way. So this tremendous number remains a mystery. I must say, to finish about the theory of gravitation, 2 more things. One is that Einstein had to modify the laws of gravitation in accordance to with his principles of relativity. The first was, one of the principles was that effects cannot occur instantaneously, while Newton's theory said that the force was instantaneous. He has to modify Newton's laws. They have very small effects, these modifications. One of them is, all masses fall. Light has energy, and energy is equivalent to mass, so light should fall. And it should mean that light going near the sun is deflected. It is. And also the force of gravitation is slightly modified in his theory, so that the law is slightly changed, very, very slightly, and it is just the right amount to account for the slight discrepancy that was found in the movement of Mercury. Finally, with connection to the laws of physics on a small scale, we have found that the behavior of matter on a small scale obeys laws so different, very different than things on a large scale. And so the question is, well, how does gravity look on a small scale? What is called the quantum theory of gravity? There is no quantum theory of gravity today. People have not succeeded completely in making a theory which is consistent with the uncertainty principles and the quantum mechanical principles. I'll discuss these principles in another lecture. Now, finally, you will say to me, yes, you told us what happens, but what is this gravity? Where does it come from, and what is it? Do you mean to tell me that the planet looks at the sun, sees how far it is, takes the inverse of the square of the distance, and then decides to move in accordance with that law and move. In other words, although I've stated a mathematical law, I haven't given you no clue as to the mechanism. I will discuss the possibility of doing this in the next lecture, which is the relation of mathematics to physics. But finally, in this lecture, I would like to remark just at the end here to emphasize some characteristics that the gravity has in common with the other laws that we have mentioned as we passed along. The first is that it's mathematical in its expression. The others are that way too. We'll discuss that next time. Second, it's not exact. Einstein had to modify it. We know it isn't quite right yet because they have to put the quantum theory in. That's the same with all our other laws. They're not exact. There's always an edge of mystery. There's always a place that we have some fiddling around to do yet. That, of course, is not a property, probably not a property. It may or may not be a property of nature, but it certainly is common with all the laws as we know them today. It may be only a lack of knowledge. But the most impressive fact is that gravity is simple. It is simple to state the principle completely and have not left any vagueness for anybody to change the ideas about. It's simple and therefore it's beautiful. It's simple in its pattern. I don't mean it's simple in its action. The motions of the various planets and the perturbations of one on another can be quite complicated to work out. Or to follow how all those stars in the globular cluster move is quite beyond our ability. It's complicated in its actions, but not in the basic pattern or the system underneath the whole thing, because that's a simple thing. That's common in all our laws. They all turn out to be simple things, although complex in their actual actions. Finally comes the universality of the gravitational law, the fact that it extends over such enormous distances. That Newton, in his mind worrying about the solar system, was able to predict what would happen in an experiment of Cavendish, where Cavendish's little model of the solar system, the two balls attracting, has to be expanded 10 million times to become the solar system. And then 10 million times expanded once again, and we find the galaxies attracting each other by exactly the same law. Nature uses only the longest threads to weave her patterns, so that each small piece of her fabric reveals the organization of the entire tapestry. Thank you. I can see the audience tonight, so I can see also from the size of it, which last time was a black spot in front of my eyes, that there must be many of you here who are not thoroughly familiar with physics. And also a number that are not too versed in mathematics, and I don't doubt that there are some who know neither physics nor mathematics very well. That puts a considerable challenge on a speaker who is going to speak on the relation of physics and mathematics, a challenge which I, however, will not accept. I published the title of the talk in clear and precise language and didn't make it sound like it was something it wasn't. It's the relation of physics and mathematics. And if you find that in some spots it assumes some minor knowledge of physics or mathematics, I cannot help it. It was named. In thinking of the applications of mathematics to physics, it's perfectly natural that mathematics will be useful when large numbers are involved in complex situations. Although, for example, if we took biology, the action of a virus on a bacterium is, if you watch it under the microscope, unmathematical. A jiggling virus finds some spot on this odd-shaped bacterium, and they're all different shapes, and finds some spot, and maybe it pushes its DNA in, and maybe it doesn't, and so forth. And yet, if we do the experiment with millions and billions of bacteria and viruses, then we can learn a great deal about the viruses by taking averages and working with large numbers. And we can use the mathematics involved in the averaging. We can see whether the viruses develop in the bacteria some new strains and in what percentage, and so we can study the genetics, the mutation, and so forth. To take another more trivial example, you know, imagine an enormous board, a checkerboard to play checkers or drafts. And if the board is very large, the actual operation of any one step is not mathematical. It's very simple if it's mathematical at all. It either goes one side or the other on a diagonal, or it reaches and becomes a king and can go backwards when it reaches the end. In other words, the statement of the rules are very simple and do not really involve any mathematics. But you could imagine that on an enormous board with lots and lots of pieces, some analysis of the best move or good moves or bad moves might be made by a deep kind of reasoning which would involve somebody having gone off first and thought about it in great depth, and that becomes mathematics, this abstract reasoning. Another example is switching in computers. If you have one switch is either on or off, then there's nothing very mathematical about that, although mathematicians like to start there with their mathematics. But with all the interconnections and wires to figure out what a very large system will do, one requires a mathematics. And I would like immediately to say that a mathematics has its primary application, it has a tremendous application in physics in the discussion of the detailed phenomena in complicated situations, granting the fundamental rules of the game. And that is something which, if I were talking only about the relation of mathematics and physics, I would spend most of my time discussing. But since this is part of a series of lectures on the character of physical law, I do not have the time to discuss the applications of mathematics and physics to calculating what happens in complicated situations, but we'll go immediately to another question, which is the character of the fundamental law. If we go back to our checker game, the fundamental laws are the rules by which the checkers move. The mathematics may be applied in a complex situation to figure out what happens in the next move, what's a good move to make in a complicated situation, but very little mathematics is needed in the fundamental, simple character of the basic laws. Now, the strange thing about physics is that for the fundamental laws, we still need mathematics. For example, I give two examples, one in which we really do not and one in which we do. There's a law in physics called Faraday's law, which says that in electrolysis, the amount of material which is deposited is proportional to the current and to the time that the current is active. And that means that the amount of material is proportional to the charge which goes through the system. Sounds very mathematical. But what's actually happening is that electrons going through the wire each carry one charge. And to take an example, a particular example, it may be that to deposit one atom requires one electron to come. And so the number of atoms that are deposited is necessarily proportional to the number of electrons that flow, and thus to the charge that goes through the wire. So the mathematically appearing law has as its basis nothing very deep. requiring no real knowledge of mathematics, that one electron is needed for each atom in order for it to deposit itself. That's mathematics. I had to say number one. But it's not the kind of mathematics I'm talking about tonight. Now, if we take, on the other hand, Newton's law for gravitation, which has these aspects which I wrote down last time just to impress you with the speed at which mathematical symbols can carry information. We said that the force was proportional to the product of the masses of two objects and inversely is the square of the distance between them, and that bodies react to forces by changing their speeds or changing their motions in the direction of the force by amounts proportional to the force and inversely proportional to their masses. Now, that's words, all right, and I didn't have to write the equation, but nevertheless, it's kind of mathematical, and we would wonder, how can this be a fundamental law? How can this planet out there look, what does it do? It looks at the sun, and it sees how far away it is, and it decides to calculate on its internal adding machine the inverse of the square of the distance, and that tells it how much to move. This is certainly no explanation of the machinery of gravitation. So you might want to look further. And various people have tried to look further. Newton was originally asked, it doesn't mean anything, it doesn't tell us anything. He says, it tells you how it moves. It should be enough, I told you how it moves, not what. But people are often unsatisfied without a mechanism, and I would like to describe one theory which has been invented among others, of the type that you might want, that this is the result of large numbers. And that's why it's mathematical. And I give this theory, perhaps you've thought of it yourself. Every once in a while, some student comes running in, he suddenly explains gravitation. Suppose that in the world, everywhere, there are flying through us at very high speed a lot of particles that come equally in all directions. They're just shooting by, and once in a while hit us in a bombardment. But we and the sun are practically transparent for them, nearly. But some hit, and so it's not completely transparent. Then look what would happen. If the sun is here, and the earth is here, then if the sun weren't here, there would be particles bombarding from all sides, giving little impulses by the rattle of these bang, bang, the few that hit, which would not shake the earth in any particular direction, because there is many coming from one side as the other, from top, from bottom. However, when the sun is here, the particles which are coming in this direction are partly absorbed by the sun because some of them hit the sun and don't go through. Therefore, the number that are coming from this direction toward the earth is less than the number that are coming from the other side, because here they have no opposition from no sun there. And it's easy to see, after some mental effort, that the further the sun is away, the less in proportion of all of the particles are being taken out of the possible directions in which particles can come. The solar size appears smaller. And, in fact, inversely is the square of the distance. So there will therefore be an impulse toward the sun on the earth that's inversely as the square of the distance, and is the result of large numbers of very simple operations, just hit, one after the other from all directions. And therefore the strangeness of the mathematical relation will be very much reduced, because the fundamental operation is much simpler than calculating the inverse of the square of the distance. This machine does the calculating. These particles bounce. Only trouble with it is that it doesn't work for other reasons. Every theory that you make up has to be analyzed against all the possible consequences and to see if it predicts anything else. And this predicts something else. If the earth is moving this way, more particles will hit it from the front than from the back. If you're running in the rain, more rain hits you in the front of the face than in the back of the head, because you're running into the rain. And so as the earth is moving in this direction, it's running into the particles, rather, and running away from the ones that are chasing it from behind, so that more particles hit it from the front than from the back, and there would be a force also sideways whenever there was any motion. This sideways force would slow the earth up in the orbit, and it certainly would not have lasted the at least 4 billion years that it has been going around the sun. So that's the end of that theory. Well, you say that was a good one, though. It got rid of the mathematics for a while. Maybe I can invent a better one. And maybe you can, because nobody knows the ultimate. But up to today, from the time of Newton, no one has invented another theoretical description of the mathematical machinery behind this law, which does anything else but say the same thing over again or make the mathematics harder, and at the same time doesn't produce some wrong phenomenon. I mean, they have, like this model does it, but it produces something which isn't true. So there is no model of the theory of gravitation today other than the mathematical form. If this were the only law of this character, it would be interesting and rather annoying. But what turns out to be true is that the more we investigate and the more laws we find and the deeper we penetrate nature, this disease, that every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics. This is relatively simple mathematics. It gets more and more abstruse and more difficult as mathematics. And why? I haven't the slightest idea why. It is only my purpose in this lecture to tell you about this fact. In other words, it's my purpose in this lecture to explain, really, why I cannot satisfy you, if you do not understand mathematics too well, in trying to explain nature in any other way. It is the burden of this lecture, in fact, to just tell you the fact that it is impossible to answer honestly, the challenge of explaining in a way that a person can feel the beauties of the laws of nature without their having some deep understanding of mathematics. I'm sorry. It seems to be the case. You might say, all right, then there's no explanation of the law. At least tell me what the law is. Why not tell me in words instead of in the symbols? Mathematics is just a language, and I ought to be able to translate the language. And in fact, I can. And with patience, I think I partly did. I could go a little further and explain more details. That this means that if it's twice as far away, the force is 1/4 as much, and so on, and can convert all these into words. I would be, in other words, kind to the layman, as they all sit, hopefully that you will explain something. And various different people get different reputations for their skill at explaining to the layman, in layman's language, these difficult and abstruse subjects. The layman then searches for book after book with the hope that he will avoid the complexity which ultimately set in even by the best expositor of this type. He reads the things hoping that one after he finds, as he reads, a generally increased confusion, one complicated statement after the other, one difficult to understand thing after the other, all apparently disconnected from one another, and it becomes a little obscure, and he hopes that maybe in some other book there's some explanation the man almost made it, you see. Maybe another fellow makes it right. And I don't think it's possible because there's another feature. Mathematics is not just a language. Mathematics is a language plus reasoning. It's like a language plus logic. Mathematics is a tool for reasoning. It's, in fact, a big collection of the results of some person's careful thought and reasoning. By mathematics, it is possible to connect one statement to another. For instance, I can say that the force is directed toward the sun. I can also tell you, as I did before, that the planet moves so that if I draw a line from the sun to the planet and draw another one at some definite period, like 3 weeks later, the area that's swung out by the planet is exactly the same as it will be in the next 3 weeks and the next 3 weeks and so on as it goes around the sun. Now, I can explain both of those statements to you carefully, but I cannot explain why they're both the same. So that if you don't appreciate the mathematics, you cannot see that the great variety of facts, the enormous apparent complexity of nature with all its funny laws and rules, each of which have been carefully explained to you, are really very closely interwoven. That logic permits you to go from one up to the other. It may be unbelievable that I can demonstrate that equal times will be swept out if the forces are directed toward the sun. And just to, if I may try, I will show you one demonstration to show you that those two things really are equivalent. And so that you can appreciate that there's more to merely the statement of the two laws, that the two laws are connected such that reasoning alone will bring you from one to the other. And the mathematics is disorganized reasoning, and that it's good to know how to do that, so they will appreciate the beauty of the relationship of the statement. So I'm going to prove, if I may, the relationship that if the forces are directed toward the sun, then the equal areas are swept out in equal time. So we start, here's the sun, and we imagine that at a certain time, let's say the planet is here, and is moving in such a way that, let's say, 1 second later or 1 hour, pick any time, let's say 1 second later, it's moved in such a manner that it has gotten to the position 2. Now, if the sun did not exert any force on it, then by Galileo's principle, it would keep right on going in a straight line. So in the same interval of time, later, the next second, it'll move exactly the same distance in the same straight line to the position 3, were there no force. All right, now first we're going to show that if there's no force, equal areas are swept out in equal time. I remind you that the area of a triangle is half the base times the altitude, and that the altitude is the vertical distance to the base. And that if the triangle is sort of cockeyed, there's a name for it which I forget, obtuse, then the altitude is this vertical height here. See, I know about the triangles, I just don't know the name. Now let us draw the lines to these 2 points in the case that there was no motion whatsoever. The question, this doesn't draw very well, I'm not accurate. But these 2 distances are equal, remember. The question is, are these 2 areas equal? Well, consider the triangle made from the sun and the 2 points 1 and 2. It's this one. What's its area? It's this space multiplied by this height. And what about the other triangle, which is the triangle in motion from 2 to 3? It's this base times the same altitude. The 2 triangles have the same altitude and, as I indicated, the same base and have the same area. So far, so good. If there were no force from the sun, equal areas would be swept out in equal times. The 2 triangles have equal areas. But there is a force from the sun. And during this interval, 1 to 2 to 3, the sun is pulling and changing the motion in various directions, this way, that way. To get a good approximation to that, we'll take the central position or average position here and say that the whole effect during this interval was to change the motion by some amount in this direction toward the sun. That means that although the particles were moving this way and would have moved this way in the next second, because of the influence of the sun, the motion is altered by an amount that's poking in this direction. That's parallel to this, exactly parallel. These lines are parallel. It's the direction in which this new motion is. The new motion is a compound of what it wanted to do and the change that's been induced by the action of the sun. So it doesn't really end up at position 3, but rather at position 4. So now we would like to compare, it's getting complicated in the diagram, the triangle 2,4S and 2,3S. I'll show you that those are equal. Because they have the same base, those 2 triangles, this one here, and the one that happened when we had no force. The one with force and with no force have the same base. And do they have the same altitude? Sure, because they're included between parallel lines, and so they have the same altitude. And thus the area of the last triangle I drew is the same as the second one I drew, this 1, 2, 3, and that I had proved earlier was the same as the first one. So in the actual orbital motion of the planet, the area of the first, in second, and in the second are equal. So by reasoning, we can see a connection between the force, the fact that the force is toward the sun, and that the areas are equal. Not ingenious, no? This was, I borrowed this from Newton. It comes right out of the Principia, diagram and all. The letters are different, that's all, because he wrote in Latin. These are Arabic numerals. But, incidentally, Newton made his proof geometrical like this, and made all his proofs in his book geometrical of this type. Today we don't use that kind of reasoning. We use a kind of analytic reasoning with symbols, which this kind of reasoning requires an ingenuity to draw the right triangles, the correct triangles, to notice about the areas and to figure out how to do it. You have to be clever. But there have been improvements in the methods of analysis so that one can be quite more stupid. And I write much faster, you're much more efficient then. And I want only to show what it looks like in the notation of the more modern mathematics, where you don't do anything but write a lot of symbols to figure it out. First, we would like to talk about how fast the area changes, and we represent that by area dot. And the area changes because of when the radius is swinging, it's the component of velocity at right angles to the radius times the radius that tells how fast the area changes. So this is the component of the radial distance multiplied by the velocity or rate of change of the distance. Now the question is whether the rate of change of area itself changes. The principle is it's not supposed to change. The rate of change of area is not supposed to change. So we differentiate, so-called, this again, and we put, it'll mean some little trick about putting dots in the right place. And that's all. You have to learn the tricks. It's just a series of rules that people have found out that are very powerful for such a thing. And this says the component of the velocity at right angles to the velocity. It is none. There is none. The velocity is in the same direction as itself. And the acceleration, which is this thing, the second derivative, or the derivative of velocity, is the force divided by the mass. So this says that the rate of change of the area is the component of force at right angles to the radius. But if the force is in the direction of the radius, as Newton said, then there's no force at right angles to the radius, and that means that the rate of change of area doesn't change. I just wanted to illustrate the different kinds of notation. Now, Newton knew how to do this, more or less, a slight different notation, but he wrote everything this way because he tried to make it possible for people to read his papers. He invented the calculus, which is this kind of mathematics, and is a good illustration of the relation of mathematics to physics. When the problems in physics get difficult, we may often look to the mathematicians who have already studied such a thing and have reasoned about such an item before and have prepared a line of reasoning for us to follow. On the other hand, they may not have, in which case we have to invent our own line of reasoning, which will then pass back to the mathematicians, because everybody who reasons carefully about anything is making a contribution to the knowledge of what happens when you think about something. And if you abstract it away and send it to the Department of Mathematics, they put it in the books as a branch of mathematics. Mathematics, then, is a way of going from one set of statements to another. It's evidently useful in physics because we have all these different ways that we can speak of things, and it permits us to develop consequences and analyze the situations and change the laws in different ways and to connect all the various statements. So that, as a matter of fact, the total amount that a physicist knows is very little. He has only to remember the rules for getting from one place to another, and he's able to do it then. In other words, all of the various statements about equal times, the forces in a direction of the radius, and so on, are all interconnected by reasoning. Now an interesting question comes up. Is there some pattern to it? Is there a place to begin fundamental principles and deduce the whole works? Or is there some particular pattern or order in nature in which we can understand that these are more fundamental statements and these are more consequential statements? There are two kinds of ways of looking at mathematics, which for the purpose of this lecture I will call the Babylonian tradition and the Greek tradition. In Babylonian schools in mathematics, the student would learn something by doing a large number of examples until he caught on to the general rule. Also, a large amount of geometry, for example, was known. A lot of properties of circles, theorem of Pythagoras, for example, formulas for the areas of cubes and triangles and everything else. And some degree of argument was available to go from one thing to another. Tables of numerical quantities were available so that you could solve elaborate equations and so on. Everything was prepared for calculating things out. But Euclid discovered that there was a way in which all of the theorems of geometry could be ordered from a set of axioms that were particularly simple. And you're all familiar with that much geometry, I'm sure. But the Babylonian attitude was, if I make my way of talking what I call Babylonian mathematics, is that you know all these various theorems and many of the connections in between, but you've never really realized that it could all come up from a bunch of axioms. Modern mathematics, the most modern mathematics, concentrates on axioms and demonstrations within a very definite framework of conventions of what's acceptable and not acceptable as axioms. For example, in geometry, they take something like Euclid's axioms modified to be made more perfect and then to show the deduction of the system. For instance, it would not be expected that a theorem like Pythagoras' that the sum of the squares of the areas of squares put on the sides of the triangle will equal the area of a square on a hypotenuse should be an axiom. On the other hand, from another point of view of geometry, that of Descartes, the Pythagorean theorem is an axiom. So the first thing we have to worry about is that even in mathematics, you can start in different places. Because of all these various theorems are interconnected by reasoning, there isn't any real way to say, well, these on the bottom here are the bottom, and these are connected through logic. Because if you were told this one instead, or this one, you could also run the logic the other way if you weren't told that one, and work out that one. It's like a bridge with lots of members, and it's over-connected. If pieces have dropped out, you can reconnect it another way. The mathematical tradition of today is to start with some particular ones which are chosen by some kind of convention to be axioms and then to build up the structure from there. The Babylonian thing that I'm talking about, which is really not Babylonian, but is to say, well, I happen to know this, and I happen to know that, and maybe I know that, and I work everything out from there. And tomorrow I forgot that this was true, but I remembered that this was true, and then I reconstruct it again, and so on. I'm never quite sure of where I'm supposed to begin and where I'm supposed to end. I just remember enough all the time so that as the memory fades and the pieces fall out, I put this thing back together again every day. The method of starting from the axioms is not efficient in obtaining the theorems. In working something out in geometry, you're not very efficient if each time you have to start back at the axioms. But if you have to remember a few things in the geometry, you can always get somewhere else. It's much more efficient to do it the other way. And what the best axioms are not exactly the same, in fact, are not ever the same, as the most efficient way of getting around in the territory. In physics, we need the Babylonian method and not the Euclidean or Greek method, and I would like to say why. The problem in the Euclidean method is to make something about the axioms a little bit more interesting or important. But the question that we have is, in the case of gravitation, is it more important, is it more basic, is it more fundamental, is it a better axiom to say that the force is directed toward the sun, or to say that equal areas are swept in equal time? Well, from one point of view, the forces is better, because if I state what the forces are, I can deal with a system with many particles in which the orbits are no longer ellipses because of the pull of one on the other, and the theorem about equal areas fails. Therefore, I think that the force law ought to be an axiom instead of the other. On the other hand, the principle that equal times are swept out in equal areas are swept out in equal times can be generalized when there's a system of a large number of particles to another theorem, which I had prepared to explain, but I see I'm running out of time. But there's another statement which is a little more general than equal areas in equal time. Well, I have to state what it is. It's rather complicated to say, and it's not quite as pretty as this one. But it's obviously the son of this one. I mean, it's the offspring. If you look at all these particles, Jupiter, Saturn, the sun, and all these things going around, lots of stars or whatever they are, all interacting with each other, and look at it from far away and project it on a plane, like this picture, then everything is moving this way, and moving that way, and so on. Then take any point at all, say this point, and then calculate how much each one is changing its area, how much area is being swept out by the radius to every particle, and add them all together. But wait, those masses which are heavier count more strongly. If this is twice as heavy as this one, then this area counts twice as much. That's doing the sweeping, and the total of all of that is not changing in time. That's the generalization, obviously, of the other one. Incidentally, the total of that is called the angular momentum. And this is called the law of conservation of angular momentum. Conservation just means that it doesn't change. Now, one of the consequences of this is, just to show what it's good for, imagine a lot of stars falling together to form a nebula, a galaxy. As they come closer in, if they were very far out and moving slowly, so there was a little bit of area being generated, but on very long arms, distances from the center, then if the thing falls in, the distances to the center are shorter now. If all the stars are now close in, then these radii are smaller. And in order to sweep out the same area, they have to go a lot faster. So as the things come in, they swirl around. And thus we can roughly understand the qualitative shape of the spiral nebulae. You can also understand in the same way, exactly the same way a skater spins when you start with a leg out, moving slowly, and as you pull the leg in, it spins faster because when the leg is out, it's contributing, when it's moving slowly, a certain amount of area per second, and then when it comes in to get the same area, you have to go around faster. But I didn't prove it for the skater. The skater uses muscle force. Gravity is a different force, yet it's true for the skater. Now we have a problem. We can deduce often from one part of physics, like the law of gravitation, a principle, which turns out to be much more valid than the derivation. This doesn't happen in mathematics, that the theorems come out in places where they're not supposed to be. In other words, if we were to say that the postulates of physics were this law of gravitation, we could deduce the conservation of angular momentum, but only for gravitation. But we discover experimentally that the conservation of angular momentum is a much wider thing. Now, Newton had other postulates by which he could get the more general conservation law of angular momentum, but Newtonian laws were wrong. There's no forces, it's all a lot of baloney, the particles don't have orbits, and so on. Yet, the analog, the exact transformation of this principle about the areas, the conservation of angular momentum, is true with atomic motions in quantum mechanics and is still, as far as we can tell today, exact. So we have these wide principles which sweep across all the different laws. And if one takes too seriously his derivations and feels that this is only valid because this is valid, you cannot understand the interconnections of the different branches of physics. Someday, when physics is complete, then maybe with this kind of argument, we know all the laws, then we could start with some axioms, and no doubt somebody will figure out a particular way of doing it. And then all the deduction will be made. But while we don't know all the laws, we can use some to make guesses at theorems which extend beyond the proof. So in order to understand the physics, one must always have a neat balance and contain in his head all of the various propositions and their interrelationships, because the laws often extend beyond the range of their deduction. This will only have no importance when all the laws are known. Another thing that's interesting in the relation of mathematics to physics is this. A very strange thing. That by mathematical arguments, you can show that you can start from very many different apparent starting points and come to the same thing. That's pretty clear. If you have axioms, you can use some of the theorems. But actually, in the physical laws are so delicately constructed that the statements of them have such qualitatively different character that it's very interesting. So if you'll permit me, I'm going to state the law of gravitation in 3 different ways, all of which are exactly equivalent, it turns out. But they sound completely different. 1, there's a forces between the objects as described before, and each object, when it sees the force on it, accelerates or changes its motion, rather, at a certain amount per second, as I've described before. The regular way, I call it Newton's law. Now there's a completely different way. That law says that the force depends on something at a finite distance away. See, it has what we call a non-local quality. The force on this depends on where that one is over there. Now, you may not like the idea of action at a distance, but it can know what's going on over there. So then there's another way of stating the laws, which are very strange, and it's called the field way of representing the laws. And it's so very hard to explain, but I just want to give you some rough idea of what it's like. And it says, different thing, completely different thing, that there's a number at every point in space. I know it's a number. It's not a mechanism. It's the trouble with this whole physics, that it must be mathematical this way. There's a number at every point in space. Here's a number, and so on. And the number's changing. It changes, rather, when you go from place to place. If an object is placed at one of these points, at somewhere in space, the force on it is in a direction in which that number, I'll call it the name it's given, called a potential, is in a direction in which that potential changes as quick as it can. And the force is proportional to how fast it changes as you move. That's one statement. That's not enough yet, because I have to tell you now how to determine how the potential varies. I could say the potential varies as 1 over the distance from each object. But that's back to the action at a distance idea. However, the force is at a distance. But you can state the law in another way. It says the following. You don't have to know what's going on anywhere outside of a little ball. If you want to know what the potential is here, you tell me what it is on the surface of any ball, no matter how small. You don't have to look outside. You just tell me what is in the neighborhood and how much mass there is in the ball. The rule is this, that the potential at the center is equal to the average of the potential on the little ball surface minus the constant that's over there in the other equation, divided by twice the radius of the ball. Let's suppose the radius of the ball is called A, and then multiplied by the mass that's inside the ball, if the ball is small enough. Now you see that this law is different than the other one because it only tells what happens at one point in terms of what happens very close by. Newton's laws tell what happened at one time in terms of what happens in another instant. If It gives from instant to instant how to work it out. But in space, it leaps from place to place. But this thing is both local in time and also local in space, because it depends only on what's in the neighborhood. And there's another way of representing. That's another way. Now, there's a completely different way. See, there's a difference in the philosophy, in the qualitative ideas involved. You don't like action at a distance. You can get away without it. Now I'll show you one which is philosophically the exact opposite, in which there's no discussion at all about how the thing works its way from place to place, in which the whole thing is an overall statement, as goes as follows. When you have other particles around and you want to know how this one moves from one place to another, you do it as follows. You calculate a certain quantity you invent a possible motion that gets from one given place to some other place that you're interested in a given amount of time. Say it wants to go from here to here in an hour, and you want to know by what route it can get from there to there in an hour. By what curve? So what you do is you calculate a quantity guessing the curve. If you try this curve, you calculate a certain number for this quantity. I don't want to say what the quantity is, but for those who have heard of these terms, this quantity on this route is the average of the difference between the kinetic and potential energy. Now, if you calculate this quantity for this route and for another route, you'll get, of course, different numbers for the answer. But there's one route which gives the least possible number for that. And that's the route that the particle takes. Now we're describing the actual motion, the ellipse, by saying something about the whole curve. We have lost the idea of causality, that the particle's here, it sees the pull, it moves to here, it goes. Instead of that, in some grand fashion, it smells all the curves around here, all the possibilities, and decides which one to take. This is an example of the wide range of beautiful ways of describing nature. And that when people talk that nature must have causality, well, you could talk about it this way. Nature must be stated in terms of a minimum principle. Well, you can talk about it this way. Nature must have a local field. You can do that, and so on. And the question is, which one is right? Now, if these various alternatives are mathematically not exactly equivalent, and if for certain ones there will be different consequences than for others, then that's perfectly all right then, because we have only to do the experiments to find out which way nature actually chooses to do it. Mostly people come along and they argue philosophically they like this one better than that one, but we have learned from much experience that all intuitions about what nature's going to do philosophically fail. It never works. One just has to work out all the possibilities and just try all the alternatives. Now, in this particular case that I'm talking about here, these theories are exactly equivalent. The mathematical consequences in every one of the different formulations of the three formulations, Newton's laws, the local field method, and this minimum principle, give exactly the same consequences. What do we do then? You will read in all the books that we therefore cannot decide scientifically on one or the other. That's true. They're not equivalent. They are equivalent. Scientifically, it is impossible to make a decision. Because there's no experimental way to distinguish if all the consequences are the same. Psychologically, they're very different in two ways. First, philosophically, you like them or don't like them. Training is the only thing you can do to beat that disease. Second, psychologically, they're different because they're completely unequivalent when you go to guess at a new law. As long as the physics is incomplete and we're trying to find out the other laws and to understand the other laws, then the different possible formulations give clues as to what might happen in other circumstances. And they become not equivalent in psychologically suggesting to us to guess as to what the laws might look like in a wider situation. For instance, Einstein noticed that the law of gravity, he said that he realized that signals couldn't propagate faster than the speed of light, for electricity. He guessed that it was a general principle, the same guessing game as taking this angular momentum and extending it from one case where you proved it to the rest of the universe. He guessed that it was true of everything, and he guessed that it would be true of gravitation. If the signals can't go any faster than the speed of light, it turns out that the method of describing the forces instantaneously is very poor. And in the Einstein generalization, of gravitation. This method of describing physics is hopelessly inadequate and enormously complicated, whereas this one is neat and simple, and so is this one. So we haven't decided between those two yet. In fact, it turns out that the quantum mechanics says that, and exactly as I stated them, neither is right, but that the fact that a minimum principle exists turns out to be a consequence of the fact that on a small scale, particles obey quantum mechanics. And the fact is the best laws at present understood is really a combination of the two, in which we use minimum principles plus local force, local laws. And the present day believes that the laws of physics have to have the local character and also the minimum principle. But we don't really know. So, it's this way, that if you have a structure that's only partly accurate and something is going to fail, if you write it with just the right axioms, maybe only one axiom fails and the rest remains. Just change one little thing. But if you write it with another set of axioms, they all collapse because they all lean on that. But we can't tell ahead of time, without some intuition and guesswork, as to which is the best way to write it until we find out the new situation. So we must therefore always keep all of the alternative ways of looking at the thing in our heads. So the physicists do Babylonian mathematics and pay little attention to the precise reasoning from fixed axioms. One of the amazing characteristics of nature is this variety of interpretational schemes which is possible. It turns out that it's only possible because the laws are just so unspecial and delicate. For instance, that the law is the inverse square is what permits it to become local. If it were the inverse cube, it couldn't be done this way. That the other end of the equation, that the force is related to the rate of change of the velocity, that's a consequence that permits this kind of a way of writing the laws, the minimum principle, because if, for instance, if the force were proportional to the rate of change of position instead of velocity, you couldn't write it in that way. If you try to modify the laws much, you find you can only write them in a very much fewer ways. I always find that mysterious, and I don't understand the reason. Why it is that the laws of physics always seem to be possible to be expressed in such a tremendous variety of ways. They seem to be able to get through several wickets at the same time. Now I would like to make a number of remarks on the relation of mathematics and physics, which are a little more general. The first is that the mathematicians only are dealing with the structure of the reasoning, and they do not really care about what they're talking. They don't even need to know what they're talking about, or as they themselves say, or whether what they say is true. Now, I explain that. If you state the axioms, you say, such and such is so, and such is so, and such is so, what then? Then the logic can be carried out without knowing what the such and such words mean. That is, if the statements about the axioms are true, are carefully formulated and complete enough, it is not necessary for the man who's doing the reasoning to have any knowledge of the meaning of these words, and he'll be able to deduce in the same language new conclusions. If I use the word triangle in one of the axioms, there'd be some statement about triangles in the conclusion, whereas the man who's doing the reasoning might not know what the triangle is. But then I can read his thing back and say, oh, a triangle, that's just a three-sided what have you, that's so-and-so. And so I know this new fact. In other words, mathematicians prepare abstract reasoning that's ready to be used if you will only have a set of axioms about the real world. But the physicist has meaning to all the phrases. And there's a very important thing that a lot of people who study physics that come from mathematics don't appreciate. The physics is not mathematics, and mathematics is not physics. One helps the other. But you have to have some understanding of the connection of the words with the real world. It's necessary to, at the end, to translate what you figured out into English, into the world, into the blocks of copper and glass that you're going to do the experiments with to find out whether the consequences are true. And this is a problem which is not a problem of mathematics at all. I've already mentioned one other relationship that, of course, it's obvious how the mathematical reasonings which have been developed are of great power and use for physicists. On the other hand, sometimes the physicist's reasoning is useful for mathematicians. Mathematicians also like to make their reasoning as general as possible. If you say, I have a three-dimensional space, ordinary space, I want to talk about ordinary space. You know, you're in it and you measure distances and there are three numbers you need to tell where something is. You go breadth, width, and height. Three-dimensional space, and you begin to ask them about theorems. Then they say, now look, if you had a space of n dimensions, then here are the theorems. Well, I say, yeah, but I only want the case 3. Well, substitute n equals 3. And then it turns out that very many of the complicated theorems they have are much simpler because it happens to be a special case. Now, the physicist is always interested in the special case. He's never interested in the general case. He's talking about something. He's not talking abstractly about anything. He knows what he's talking about. He wants to discuss the gravity law. He doesn't want the arbitrary force case. He wants the gravity law. And so there's a certain amount of reducing because the mathematicians have prepared these things for a wide range of problems, which is very useful. And later on, it always turns out that the poor physicist has to come back and says, excuse me, when you wanted to tell me about the 4 dimensions. Now, another item that's interesting in this relationship is the question of how to do new physics. Is it important to have a feeling, a kind of I must mention one other item. When you know what it is you're talking about, that these things are forces, and these are masses, and this is inertia, and this is so on, then you can use an awful lot of common sense, seat-of-the-pants feeling about the world. You've seen various things. You know more or less how the phenomenon is going to behave. Well, the poor mathematician, he translates it into equations, and the symbols don't mean anything to him, and he has no guide but precise mathematical rigor and care in the argument. Whereas a physicist who knows more or less how the answer is going to come out can sort of guess part way and go right along rather rapidly. The mathematical rigor of great precision is not very useful in the physics, nor is the modern attitude in mathematics to look at axioms. Now, mathematicians can do what they want to do. One should not criticize them because they are not slaves to physics. It is not necessary that just because this will be useful to you, they have to do it that way. They can do what they will. It's their own job. And if you want something else, then you work it out yourself. The next point is the question of whether we should guess, when we try to get a new law, whether we should use the seat-of-the-pants feeling and philosophical principles. I don't like a minimum principle, or I do like a minimum principle, or I don't like action at a distance, or I do like action. The question is, to what extent models help? And it's a very interesting thing. Very often models help, and most physics teachers try to teach how to use these models and get a good physical feel for how things are going to work out. But the greatest discoveries, it always turns out, abstract away from the model. It never did any good. Maxwell's discovery of electrodynamics was first made with a lot of imaginary wheels and idlers and everything else in space. If you got rid of all the idlers and everything else in space, the thing was okay. Dirac discovered the correct laws of quantum mechanics for relativity quantum mechanics simply by guessing the equation. And the method of guessing the equation seems to be a pretty effective way of guessing new laws. This shows, again, that mathematics is a deep way of expressing nature, and attempts to express nature in philosophical principles or in seat-of-the-pants mechanical feelings is not an efficient way. I must say that there is possible, and I've often made the hypothesis, that physics ultimately will not require a mathematical statement, that the machinery ultimately will be revealed, just a prejudice like one of these other prejudices. It always bothers me that in spite of all this local business, what goes on in a tiny, no matter how tiny a region of space, and no matter how tiny a region of time, according to the laws as we understand them today, takes a computing machine an infinite number of logical operations to figure out. Now, how can all that be going on in that tiny space? Why should it take an infinite amount of logic to figure out what one stinky tiny bit of space-time is going to do? And so I made the hypothesis often that the laws are going to turn out to be, in the end, simple like the checkerboard, and that all the complexities is from size. But that is of the same nature as the other speculations that other people make. It says, I like it, you don't like it. It's not good to be too prejudiced about this thing. To summarize, I would use the words of Jeans, who said that the great architect seems to be a mathematician. And for you who don't know mathematics, it's really quite difficult to get a real feeling across up to the beauty, or the deepest beauty of nature. C.P. Snow talked about two cultures. I really think that those two cultures are people who do and people who do not have had this, people who have had and people who have not had this experience of understanding mathematics well enough to appreciate nature once. It's too bad that it has to be mathematics, and that mathematics for some people is hard. When one of the, it's reputed, I don't know if it's true, that when one of the kings was trying to learn geometry from Euclid, he complained that it was difficult. And Euclid said that there's no royal road to geometry. And there's no royal road. It's not the we cannot, as people who looked at this thing as physicists, cannot convert this thing to any other language. You have, if you want to discuss nature, to learn about nature and to appreciate nature, it's necessary to find out the language that she speaks in. She offers her information only in one form. We are not so unhumble as to say, demand that she change before we pay any attention. It seems to me that it's like all the intellectual arguments that you can make would not in any way, or very, very little, will communicate to deaf ears what music, the experience of music really is. And all the intellectual arguments in the world will not convince those of the other culture. The philosophers who try to teach you by telling you qualitatively about this thing. Me, who's trying to describe it to you, but it's not getting across because it's impossible. We're talking to deaf ears. And it's it's perhaps that the horizons are limited, which permit such people to imagine that the center of the universe of interest is man. Thank you. learning about the laws of physics, you find that there are a large number of complicated and detailed laws. The laws of gravitation, of electricity and magnetism, nuclear interactions, and so on and so on. But across the variety of these detailed laws, there sweep great general principles, which all the laws seem to follow. Now, these principles are, for instance, the principles of conservation, certain qualities of symmetry, the general form of quantum mechanical principles, and unhappily or happily, as we spoke about last time, the fact that all the laws of mathematics. And tonight I want to talk about the conservation principle. Now, a principle of the physicist uses all ordinary words in a peculiar manner. It's unfortunate. For example, conservation law means this, the way he uses the word, is that there is a number which you can calculate at one moment, and as nature undergoes its multitude of changes, this number doesn't change. That is, if you calculate again this quantity, it'll be the same as it was before. An example is the conservation of energy. There's a quantity that you can calculate according to a certain rule, and it comes out the same answer after no matter what happens. Now you can see that such a thing is possibly useful. It's analogous to this. Suppose that the physics or the nature is made analogous to a great chess game that we're watching with millions of pieces on it, and we're trying to discover the laws or the rules by which the pieces move. And the great god who play the chess play it very rapidly. It's hard to watch. It's difficult to see, and we're catching on to some of the rules. But there are some rules which we could work out which do not require that we watch every move. For instance, if there's one bishop only on the board, since the bishop moves diagonally, it never changes its color. So if there's a red bishop on the board and we look away for a moment while the gods play for a few minutes, look again, we can expect that there's a red bishop on the board. Maybe in a different place, but the same the same color, square. And this is in the nature of a conservation law. We don't need to watch the inside, but we at least know something about the game anyway. It's true that in chess, this particular law is not necessarily perfectly valid. If we watch long enough, it could happen that the bishop is captured while we weren't looking. A pawn went down to queen, and the god decided that it was better to put a bishop instead of a queen in the place of that pawn, and it was on a black square. And so, unfortunately, it may well turn out that some of the laws which we see today may not be exactly perfect, but I'll tell you how it looks now. I said that we use words in a technical fashion, and another word in this title is the great conservation principles. This is not a technical word. It was merely put in to make the title sound more dramatic. Just as well call them the conservation law. If you wish, there are a few conservation laws that don't work, that are only approximately right, that are kind of useful, and we might call those the little conservation laws. I'll mention one or two of those. But the other ones that I'm going to mention are, as far as we can tell today, absolutely accurate. The easiest one to understand is the one I'll start with, and that's the conservation of electric charge. There's a number, the total electric charge on a thing, which, no matter what happens, doesn't change. Of course, the total electric charge in the world, rather, is what doesn't change. The charge may go from one place to another, but if you lose it here, you'll find it over there. So the conservation is of a total of the electric charge. This was discovered experimentally, or demonstrated experimentally, by, I am embarrassed to say, I don't remember whether it was, I think it's Faraday, but it might have been Franklin. Anyway, it's somebody whose name begins with F. And I know at least this much, that it isn't Feynman anyway. But at any rate, the experiment consisted of getting inside of a great globe of metal, on the outside of which was a very delicate galvanometer to look for charge on the globe, because small amounts of charge would make a big effect. And then inside the globe, this experimenter, whose name began with F, built all kinds of weird electrical equipment of every kind. He made charges by rubbing glass rods with cat's fur, and he made big electrostatic machines run inside and so on, so that the inside of this thing looked like those horror movie laboratories. And during all these experiments, no charge developed on the surface. There was no net charge made. When a glass rod was charged up with the cat's fur, although the rod may have been, I forget, say, positive, then the cat's fur would be the same amount of charge negative. Because the total charge was never anything. If there were any charge developed on the inside, it would have appeared as an effect in the galvanometer on the outside. So the total charge is conserved. Now, this one is an easy one to understand because a very simple model that's not mathematical at all will explain it. Suppose that the world is only made of two kinds of particles, electrons and protons. There was a time when it looked like it was going to be as easy as that. And that the electrons carry a negative charge and the protons a positive charge, so we can separate them. We can take a piece of matter and put more electrons on or less electrons. But suppose that electrons are permanent. They do not disintegrate. They never disappear. And that's all. Now, that's not even mathematical. That's a simple proposition. And now you see that the total number of electrons take away, or the protons rather, take away the number of electrons won't change. As a matter of fact, the total number of protons won't change, and the total number of electrons won't change in this particular model. But we're concentrating now on the charge. And the difference, the contribution of the positive, of the protons is positive and the electrons is negative. And if these objects are never created or destroyed alone, then the total charge will be conserved. I want to list later on the number of properties of conserved quantities, and I start with the one about charge that we're talking about, and we mark down here that it is conserved. And that's the beginning. This goes yes. So that's the first. The chart will expand as we go along. This theoretical interpretation is very simple, but it was later discovered that electrons and protons are not permanent. For example, a particle called a neutron can disintegrate into a proton and an electron, plus something else that we'll come to. But the neutron, it turns out, is electrically neutral. So although protons are not permanent, nor are electrons permanent in the sense that they can be created from a neutron, the charge still checks out, because starting before we had zero charge, and afterwards we have +1 and -1, so when added together, you get zero charge. So that the rule is, now another example of a similar trouble, not trouble, but fact, is this, that there exists another particle which is positively charged besides a proton called a positron, which is a kind of an image of an electron. It's just like the electron in most respects, except it has the opposite sign of charge, and more important, it's called an antiparticle because when it meets with an electron, the two of them can disintegrate, they can annihilate each other, and nothing but light come out. So electrons are not permanent, even by themselves. An electron plus a positron will just make light. Or actually, the light is invisible as gamma rays, but it's the same thing for a physicist. Just the wavelength is different. So a particle and the antiparticle can annihilate. The light has no electrical charge, but we remove one positive and one negative charge, so we haven't changed the total charge. Therefore, the theory of this conservation of charge is a little slightly more complicated, but still very unmathematical. It's simply this. How many positrons do you have? How many protons? Take away the number of electrons. And there are other particles, it turns out, in the world that you have to check. For instance, there are antiprotons. They contribute negatively. There are positive pi mesons. They contribute positively. Each particle in nature has, fundamental particles have charges, and all we have to do is add the total number, and whatever happens in any reaction, the total amount of charges on one side has to balance on the other side. That's one aspect of the conservation of charge. Now comes an interesting question. Is it sufficient to say only that charge is conserved, or do we have to say more? If charge were conserved because it was a real particle which moved around, it would have a very special property. The total amount of charge in a box might stay the same in two ways. It may be that the charge moves from one place to the other in the box and just stays in the box. But another possibility is this. Charge here disappears. And simultaneously over here, charge arrives. In such a manner, instantaneously related, so that the total charge is never changing. This possibility for the conservation is a different kind than the other one in which if anything happens that the charge goes away here, something has got to go through the in between. Something goes past you. If you stood there and watched, something would go by. The second form of charge conservation is called local charge conservation and is far more detailed than the simple remark that the total charge doesn't change. So you see, we've been proving our law, if in fact it's true, that charge is locally conserved. It is true. That it must be true, of course, nothing can be proved without some other things, but as I desire to show you from time to time as much as possible some of the possibilities of reasoning interconnecting one idea with another, I would like to show you an argument which is fundamentally due to Einstein, which indicates that if anything is conserved, in this case I apply it to charge, it must be conserved locally, provided one thing, provided that if two fellows are passing each other in a spaceship, the argument about which guy is doing the moving and which one is standing still cannot be resolved by any experiment. That's called the principle of relativity, that the motion is relative and that we can look at any phenomenon from either point of view, either from the point of view that the one is moving and that this one is standing still and this one is moving, or the other way around. Now, suppose I take this point of view that this one is the one that's moving past him. Don't forget, that's just temporary. You can also look at it the other way, and you must get the same phenomena of nature. Now, suppose that this man who's standing still wants to argue whether or not he sees a charge over here disappear and a charge over here appear at the same time. In order to make sure that it's the same time, he can't sit in the front of the ship because he'll see one before he sees the other on account of light. So let's suppose that he's very careful. He's dead center in the middle of the ship, right here, and look, he's right in the middle, halfway in between. Incidentally, I'm going to have another man doing the same kind of observation in the other ship. And now, a lightning bolt strikes and charge at this point A is created at a certain instant. And at the same instant, back over here, at this place B, on the other side, at the other end of the spaceship, funny-looking spaceship, the charge is annihilated, disappears. At the same time, which is perfectly consistent with our idea that charge is conserved, because if we lose one electron, we get one electron here and lose one here, but nothing went in between. Now, see. He says at the same time, he watches, he sees it's exactly the same time, because the light which comes from the bolt which created the A reaches him at the same time as the light which comes from the flash of disappearance. We suppose that when it disappears, it's a flash, and when it's created, it's a flash, so we can see what happened. And then we see the two flashes at the same time, and since he knows he's in the middle of the ship, he says, yes, when one disappeared, the other was created. But what happens to our friend in the other ship? He says, no, you're wrong, my friend. I saw A was created before B. Because the light is coming out of A, but the man is moving toward it because he's moving. And the light hits him from the front before the light can reach him from the back because he's moving away from the light. So by the time the light gets here, he's got moved over. So he says, no, A, you see, was created first, and then B disappeared. So for a short time, after I saw A was created, B hadn't yet disappeared, and I got some charge. That's not the conservation of charge against the laws. So the other fellow says, yeah, but you're moving. He says, how do you know? And so on. I think you're moving. So if we are unable by any experiment to see a difference in the physical laws, whether we're moving or not, if the conservation of charge were not local, we could tell when we were, see, if it were not local, only a certain kind of man would see it work right, namely the guy who's standing still in an absolute sense. But such a thing shall be impossible according to Einstein, and therefore it's impossible, according to the relativity principle, to have non-local conservation of charge. This conservation, the locality of the conservation of charge is consonant with the theory of relativity, and it turns out that locally, that this is true of all the conservation laws, not just the charge. As you can appreciate, if anything is conserved, it's the same principle. Now, another interesting thing about charge, which has nothing to do with the conservation law and is independent of that, is a very strange one for which we have no real explanation today. And that is that the charge always comes in units. When we have a particle that's charged, it's got one charge or two charge or -1 or -2. It's a nice little lumpy unit and has nothing to do with the conservation of charge, but I can't help writing down that to find out it comes in units, the thing that's conserved. And it's very nice that it comes in units because that makes the theory of conservation of charge very easy to understand. It's just a thing which we count, which goes from place to place. Finally, it turns out technically that the total charge of a thing is very easy to determine electrically because the charge has a very important characteristic. It's the source of the electric and magnetic field. Charge is a measure of the interaction of an object with electricity, with electric field. And so the other item that we should put here on the list is that this is the source of a field. In other words, the electricity is related to the charge. So this particular quantity which is conserved here has two other aspects which are not connected with the conservation directly, but are interesting in either way. One is that it comes in units, and the other that it's the source of a field. Are there other examples? There are many conservation laws. I give some more examples of conservation laws of the same type as the charge in the sense that it's merely a matter of counting. There is a conservation law called the conservation of baryons. A neutron can go into a proton. If we count each of those as one tien, then we don't lose the number of tiens. The word tien is actually substituted by baryon, which is equally mysterious and meaningless. The neutron carries one baryonic charge unit, or represents one baryon. Then a proton represents one baryon. All we're doing is counting and making big words. And so the total number, if this reaction occurs, the total number of baryons doesn't change. It does turn out, however, that there are other reactions in nature. For example, a proton plus a proton can produce rather a great variety of strange objects. A lambda, a proton, and a K plus, for instance. These lambda and K plus are names for peculiar particles. Now, from this one, you know you put two baryons in, you see one come out, so possibly one or the other is one. But if you'll study the lambda later, you'll discover that it very slowly, this is easy for it, easy, this is hard for it to do, it disintegrates into a proton and a pi, and ultimately the pi disintegrates into electrons and whatnot. But what you've got here is the baryon coming out again. So we think that the lambda has a baryon number, but the K does not, has 0. And so in counting these other numbers, we have a similar situation with baryons. So we have charge, and then we have baryon number, with a special rule that the baryon number is the number of protons, plus the number of neutrons, plus the number of lambdas, minus the number of antiprotons, minus the number of antineutrons, and so on. It's just a counting proposition. It's conserved. It comes in units. And nobody knows, but everybody wants to think, by analogy, that it's the source of a field. We are trying to guess at the laws of nuclear interaction. And the reason we make these kind of tables is this is one of the trick ways of guessing at nature. If this is the source of a field and this does the same thing, it ought to be the source of a field too. Too bad so far it doesn't seem to be, or for sure isn't anyway. We don't know. Sometimes people think it is, sometimes not. We don't know enough to be sure about that question. Now it turns out that there is a very peculiar thing. I would like to mention, there are one or two more of these counting propositions called lepton number and so on, but you learn nothing new, the same idea. Just counting. There is one, however, which is slightly different, is that there are, in nature, characteristic rates, apparently, with these strange particles. There are rates of reactions which are very fast and very easy reactions to do, and others that are very slow. I don't mean easy and hard in a technical sense. It's actually doing the experiment. It's got to do with the rates at which these reactions occur when the particles are present. Anyway, there's a clear distinction between this kind of a reaction and this. And it turns out that if you take only the faster, easy reaction, that there's one more counting law in which the lambda gets a -1 and the K plus gets a +1, and it's called the strangeness number, or hyperon charge, rather. And the proton gets 0. And in that particular rule is right for every easy reaction, but it's wrong for the slow reaction. And then we have a conservation law called the conservation of strangeness, or the conservation of hyperon number, which is nearly right, which is very peculiar. So we see why the stuff has been called strangeness, the number. It's nearly true, and nearly true. But in trying to understand the strong interactions which are involved in nuclear forces, since as far as the strong interactions are involved, the thing is conserved, that has made people propose that for the strong interactions, that's again a source of a field, but we don't know. But it's just, I bring these matters up to show you how the conservation laws are used to guess new laws. Now, there are other conservation laws that have been proposed from time to time of the same nature as counting. For example, chemists once thought that no matter what happened, the number of sodium atoms stayed the same. But sodium atoms are not permanent. It's possible to transmute atoms from one to another, so that one is just true. Another law, which was for a while believed to be true, was that the total mass of an object stays the same. It depends on how you define mass and whether you get mixed up with the energy nowadays, and I will disregard this mass law until we come to the conservation of energy. But the mass conservation law has been contained in the next one, which I'm going to discuss now, which is the law of conservation of energy. The law of conservation of energy is the most difficult, abstract one, and the most useful, as a matter of fact, of all the conservation laws. It's more difficult to understand than the charge in these other ones, because in the charge in these other ones, it's obviously merely, the mechanism is perfectly clear. It's the conservation of the object, sort of. I mean, not quite, because of this problem that we get some new things from old things, but it's really a matter of counting. But the conservation of energy is a little more difficult. Here we have a number which is not changed in time, but the number doesn't represent the number of any particular thing. I would like to make a kind of silly analogy to explain a little bit about it. And I want you to imagine that a mother has a very difficult child. Well, not necessarily difficult, but she has a child who she leaves alone in a room with 28 blocks. The indestructible, absolutely indestructible blocks, like the charge. And the child plays with the blocks during the day, and when the mother comes back, she discovers, indeed, there are 28 blocks. She checks all the time the conservation of blocks. Well, this goes on for a few days until one day when she comes in, there are only 27 blocks. One block she finds later outside the window. He threw one out the window. So first we must appreciate the conservation laws involved, that you watch out that the stuff that you're trying to check doesn't go out through some water. And the same thing could happen the other way if a boy came to play with him and brought in some blocks. Of course, those are obvious technical matters that you have to be careful of when you talk about a conservation law. But now suppose, however, that when the mother comes to count the blocks, she finds there are only 25 blocks, but suspects that in a little toy box, in a box that the boy has, he has hidden the blocks. So she says, I'm going to open the box. He says, no, you cannot open the box. How can she tell? She's a very clever mother, unlike most. She would say, the box weighs, I know when it's empty, 16 ounces, and each block weighs 3 ounces, so what I'm going to do is I'm going to weigh the box. So she would have another thing, number of blocks seen plus weight of box minus 16 ounces divided by 3 ounces. And that adds always the same to 28. Goes on for a while until it doesn't check. But you notice that the dirty water in the sink is changing its level. So we have the water level. Height of water in sink. Minus 6 inches, which it is when there's no block in it. Divided by 1/4 of an inch, which is the height that the water rises when a block is in the dirty water. Now, as the boy becomes more ingenious and the mother continues to be ingenious, more and more terms must be added on here, which all really represent blocks. But from a mathematical standpoint, are abstract calculations, which the blocks are not seen. Now, I would like to draw my analogy and tell you what is common to this and the conservation of energy and what is different. Suppose that you never saw the blocks at all, that in any one of the situations there were never any blocks. Then the mother would be always calculating a whole lot of terms, which is called blocks in the box, blocks in the water, blocks and so on. But there are other differences that there aren't any blocks as far as we can tell. and that the numbers that come out here are not integers, unlike the case of the blocks with the child. Suppose, it could happen to the poor lady that when she calculates this number, it comes out 6 1/8 blocks. And when she calculates this number, it comes out 7/8 of a block, and the rest of them give 21, still 28. That's the way it looks. So what we discover is that we have a scheme in which we can find a sequence of rules, and from the rules, each one of the different kinds of calculations we call calculating the same thing, number of blocks, or energy, by different rules. And then we add all the numbers together from all the different forms of energy, it always adds up to the same total. But as far as we know, there are no real units. It's not made out of little ball bearings. So it's abstract. It's purely mathematical. There exists a number such that you can calculate and it doesn't change. I cannot interpret any better than that. And this energy has all kinds of forms, analogous to the blocks in the box and blocks in the sink water and so on. There is energy due to motion. It's called kinetic energy. There's energy due to gravitational interaction. The gravitational potential energy, it's called. There's a thing called thermal energy, electrical energy, light energy, elastic energy, and springs and so on, chemical energy, nuclear energy, and there is also an energy that a particle has from its mere existence, an energy that depends on its mass directly. That's the contribution of Einstein, as you undoubtedly know. E equals mc squared is what I was talking about, which is a famous equation, this mystic law. Now, actually, although I mentioned a large number of energies, I would like to explain that we're not completely ignorant about the thing and that we understand the relationship of some of them. For example, what we call thermal energy is to a large extent merely the energy, the kinetic energy of motion of the particles inside an object. What we call elastic energy and chemical energy both have about the same origin, namely the forces between the atoms. When the atoms rearrange in a new pattern, some energy is changed. That quantity changes. That means that some other quantity has to change. So, for instance, if the chemical energy changes, then heat energy is changed. So that in a burning something, the chemical energy changes, and you find heat where you didn't have the heat before, because it all has to add up to that. And but elastic energy and chemical energy are both interactions of atoms, and we now understand the interactions of the energies of the atoms, or those chemical interactions, or those interactions of the atoms, to be a combination of two things. One is electrical energy, and the other is kinetic energy, again, only the formula for it is quantum mechanical instead of the usual, it's a little different one. Light energy is nothing but electrical energy because light has now been interpreted as an electric and magnetic wave. The nuclear energy has is not represented in the terms of the others, but as the result of what we say, due to nuclear forces. Well, we didn't say anything. But nuclear energy is not connected yet to the others. I'm not just talking about the energy released. In the uranium nucleus, there's a certain amount of energy, and then when the thing disintegrates, it changes the amount of energy in the nucleus, but the total amount of energy in the world doesn't change, so a lot of heat and stuff is generated in the process in order to balance that thing out. Now, this conservation law is very useful in many technical ways, and I wish I could give you a number of them. I'll give you some very simple ones to show you how, from the conservation of energy and knowing the formulas for the energy, which are not those, you can calculate, you can see what some certain things have to happen. In other words, many laws are not independent laws, but are just secret ways of talking about the conservation of energy, or better. Knowing the conservation of energy, you can understand a lot of laws. The simplest one is a lever. If this is a lever on a pivot, and let's say this distance is 1 and this distance is 4 times, 1 foot and 4 feet, then first I must give you the law for gravity energy. And the law for gravity energy is to take, if you have a lot of weight, you take the weight of each weight and multiply it by the height above the ground and add this together for all the weights, and that gives all the gravity energy. Now let's put the ground right here. I have a 1 pound weight here, just to make it, or say to make it more complicated, 2 pound weight here. And I have an unknown mystic weight on the other side. X is always the unknown. So let's call it W to make it look more, that we've advanced above the usual. Now, the question is, how much must W be so that it just bounces and swings quietly back and forth without any trouble? That means that the energy, if it swings quietly back and forth without any trouble, when it's set this way, and when it's tilted up a little bit, say, for instance, if this has gone up 1 inch, the energy is the same. If it is the same, then it doesn't care much which way, and it doesn't fall over. So if this goes up 1 inch, how far down does this go? If you think about it quite a long time, this being 1 inch and that being 4 feet, you can figure out by proportion that this being 1 foot, this is 1/4 of an inch. So that the rule says this, that before anything happened, all the heights were 0, so the total energy is 0. After the thing has happened, we multiply the weights, unknown, by the height minus 1/4 of an inch, add the other weight, 2, by the height, 1 inch, and this should add up to the same energy as before. So that 1/4 of W taken away from 2 is 0, and W must be 8. So that's how we find the laws. I mean, that's one way we can understand the easy law that you know, of course, the law of the lever. But it's interesting that not only this one, but hundreds of others of the physical laws can all be closely related to the various forms of energy. So I illustrate that only to illustrate how useful it is. The only trouble is, of course, it doesn't really work. I mean, if you did that, it wouldn't swing like this on account of friction in the fulcrum. If I had something moving, for instance, it has kinetic energy like a rolling ball, and it's on a constant height, and it rolls along, and then it stops. That's on account of friction. But what happened to the energy of the ball? And the answer is that the energy of the ball has gone into the energy of the jiggling of the atoms in the floor and in the ball. The world that we see on a large scale looks so nice when we polish a nice round ball and so on. It's really quite complicated when you look at it on a little scale. Little billions of tiny atoms with all kinds of irregular shapes looked at in detail. It's like a very rough boulder, really, when looked at finely enough, because it's made out of these little balls. And the floor is the same way, as a bumpy business made out of balls. And you roll this monster thing over the other, you can see that the little atoms are going to go snap, jiggle, and after the thing has rolled across, the ones that are left behind are still shaking a little bit from the pushing and snapping that they went through. So there is left in the floor a jiggling motion or thermal energy. And although at first it looks like the law of conservation is false, energy has a tendency to hide from us, and we need thermometers and other instruments to make sure that it's still there. The first demonstration of the conservation of energy, the energy is conserved no matter how complex the process, or no matter what, even when we don't know the detailed laws. The first demonstration of the law of conservation of energy, in fact, was not by a physicist, but by a doctor, a medical man. He demonstrated with rats that the total energy of the food put in before and the heat generated when you burn food and you find out how much heat is generated, and then you feed the rats the food, and it's converted an oxygen and it's converted to carbon dioxide the same way as in burning, and measure the energy in that case, and you find out that living creatures do exactly the same thing as non-living creatures. That the law of conservation of energy is exactly as true for life as not. As a matter of fact, it was discovered by this. Incidentally, it's interesting that every overall principle that we know that we can test on the great phenomena of life work just as well as for dead things. That is, there is no evidence yet that what goes on in living creatures is necessarily different, or maybe more complicated, but that is necessarily different than what goes on in non-living things. I mean in the physical, as far as the physical laws are concerned. Incidentally, this amount of energy that's in the food, it'll tell you how much heat and mechanical work and everything that's generated is what you read. When you read up here about calories, you're not eating something called calories, but you're eating that measure of the amount of heat energy that's in the food. For people who physicists always feel so superior and smart and so on, that people would just like to get them once on something. And so I'll give you something to get them on. They should be utterly ashamed of themselves, because they take the same thing, energy, and they measure it in a host of different ways with different names. Absolutely absurd. Energy can be measured in calories, in ergs, in electron volts, in foot-pounds, in BTU, in horsepower hours, in kilowatt hours. All exactly the same thing. It's like having money, in dollars and in pounds and so on. But unlike the economic situation where the ratio can change, these dopey things have an absolutely guaranteed proportion. If anything could be analogous to it at all, the only hope would be to say that there are 20 shillings to a pound, and that you have shillings and pounds, with one complication that the physicist allows, in that instead of saying he has 20 shillings to a pound, he says he has irrational ratios like 1.6183178 shillings to a pound. So, in addition to that, you'd think that the more modern, high-class theoretical physicists would at least use a common unit, but you can find papers with degrees Kelvin for measuring energy, megacycles, inverse Fermis is the latest invention. We don't need any more inventions. We should all measure the energy in exactly the same. We should measure the energy in one unit and let it be done instead of having all these different names. And it just shows that people are often also, they want to say, see, I should bring my little boy to show on the screen so that the audience will understand that I'm human. Well, the proof that physicists are human is the idiocy of all the different units which they use in measuring energy. Now, we have a number of interesting phenomena in nature which present us some curious problems with energy. Has recently been discovered things called quasars, which are very far away and emit a lot of light. They're enormously far away, emit a lot of light and a lot of radio waves, and have radiating so much energy that the question is, where does it come from? That is, after it's radiated this enormous amount of energy, the condition must be different than it was before, if the conservation of energy is right. Question, is the thing collapsed gravitationally? Is it different condition gravitationally? Is it coming from gravity energy, this big emission? Or is it coming from nuclear energy and so on? And nobody knows. Would you like to propose that maybe the law of conservation of energy is not right? Well, when a thing is investigated as poorly, I don't mean as incompletely as is the quasars, because they can't see so easy at such a large distance, it very rarely is, when a thing looks difficult, that the fundamental laws are wrong. It's usually that the details are unknown. Another interesting example of the use of the conservation of energy is in this reaction. It was first thought that neutrons turn to protons plus electrons. But the energy of a neutron is fixed, and that of a proton could be measured, and the energy of an electron did not add up correctly to the energy of the neutron. If you proton and electron together, didn't add up to the neutron. Two possibilities existed. One was the law of energy conservation is not right. In fact, it was proposed by Bohr for a while that maybe the conservation law worked only statistically on the average for large scale. But it turns out that Pauli suggested no, that the fact that the energy doesn't check out is because there's something else coming out, which we now call an antineutrino, and that this other thing coming out takes out the energy. You say the only reason for the antineutrino is to make the conservation of energy right. Well, it takes a lot of other things right. Conservation of momentum and other conservation laws are fixed up right because the piece came out that we weren't worrying about. And very recently it has been directly demonstrated that such neutrinos indeed exist. That illustrates a point. Why are we able to extend our laws to regions that we're not sure? How is it possible? Why are we so confident? Because we check the energy conservation here. Then when we get a new phenomenon, we say it's got to satisfy the conservation of energy. And every once in a while you read in the paper that the physicists have discovered one of their favorite laws is wrong. It's not a mistake to say that it's true in a region where you don't look yet, where you haven't looked yet. If you will not say that it's true in a region that you haven't looked yet, you don't know anything. If the only laws that you find are those which you just finished observing, then you can't make any predictions, and the only utility of the science is to go on and to try to take guesses. You see, the most likely thing is that the energy is conserved in other places. So what we do always is to stick your neck out. People like this, and that of course means that the science is uncertain. The moment that you make a proposition that about a region of experience that you haven't directly seen, then you must be uncertain. But we always must make statements about the regions that we haven't seen, or there's no use in the whole business. For instance, in early experiment, the mass of an object changes when it moves. Because of the conservation of energy, the energy associated with the motion appears as an extra mass because of the relation of mass and energy. So things get heavier when they move. It was first believed by Newton that this wasn't the case, that the masses stayed constant. And so when it was discovered that that was false, everybody say it was a terrible thing that physicists found out they were wrong. Why did they think they were right? The effect is very small. Only when you get near the speed of light does it make any difference. If you spin a top, it weighs the same as if you don't spin it within millions, very, very fine fraction. So you could say, oh, they should have said, if you do not move any faster than so-and-so, then the mass doesn't change. That would then be certain. No. The experiment happens to be done only with tops made out of wood, copper, steel, and so on. So we should have said that tops made out of copper, steel, wood, and so on were not moving any faster. You see, we do not know all the conditions that we need for an experiment. It is not known whether a radioactive top would have a mass that's for certain. But we have to take a guess. So in order to have any utility at all to the science, in order not simply to describe an experiment that's just been done, we have to propose laws beyond their range, and there's nothing wrong with that. That's the success. That's the point. And that makes the science uncertain. If you thought before that science was certain, well, that's just an error on your part. Now there are so we have here the energy, which we can put in our list. And it's conserved perfectly, as far as we know. But it does not come in units. And now the question is it the source of a field? And the answer is yes. Einstein understood gravitation as being generated by energy. Energy and mass are equivalent, and Newton's interpretation that the mass is what produced the gravity has been modified to being the energy that produces the gravity. There are other laws that are similar to the conservation of energy in the sense that they're numbers. I haven't very much time to describe them, but I'll mention what they are. One of them is the momentum. It means if you take all the masses in an object and multiply them by the velocities, for instance, and add it together, that's the momentum of the particles in it anyway. And that total amount of momentum is conserved. The energy and the momentum are now understood to be very closely related, and so I should be in the same column in this conservation law. Another example of a conserved quantity is angular momentum, an item which we discussed some time before. The angular momentum is the area generated per second by objects moving about. For example, if an object is here and is moving, and we take any center whatsoever, then the area, the rate of change, the speed at which this area increases, multiplied by the mass of the object, and added together for all the objects, is called the angular momentum. And that quantity doesn't change either. So we have conservation of angular momentum. Incidentally, at first sight, if you know too much physics, you might think that the angular momentum is not conserved. Like the energy, it appears also in different forms, although most people think it only appears in motion. But it does appear in other forms, and I will illustrate that. You know that if you have a wire and move a magnet up into it, increasing the magnetic field through the flux through the wire, there'll be an electric current. That's how electric generators work. So now imagine that I have, instead of a wire, a disk on which there are electric charges analogous to the electrons in the wire. And then I bring up a magnet dead center along the axis from far away very rapidly up to here. So then now there's a flux change through here. Then, just as in the wire, these will start to go around. And so if this were on a wheel, it would be spinning by the time I brought the magnet up. Well, that doesn't look like conservation of angular momentum, because when it's down here, nothing's turning. And when it's up here, it's spinning. And so we got turning for nothing. And that's against the rules. Oh, yes, you say, I know, there must be another kind of interaction that makes the magnet spin the opposite way. It's not the case. There is no electrical force on the magnet tending to twist it the opposite way. The explanation is that angular momentum appears in two forms. One of them is angular momentum of motion, and the other is angular momentum in electric and magnetic field. And there is angular momentum in the field here, although it doesn't appear as motion, and has the opposite sign to the spin. If we take the opposite case, it's even more clear. If we have just these particles and the magnet here, and everything standing still, I say there's angular momentum there. There's a rotational effect. There's an angular momentum in the field. There's a hidden form of angular momentum that doesn't appear as actual rotation. When you pull this magnet down and take the instrument apart and all the fields separate, then the angular momentum that's in the field has to appear now, and this thing will spin from and the law that makes it spin is the law of induction of electricity. Now, the question as to whether it comes in units is very difficult for me to answer. At first sight, you'd say it's absolutely impossible that angular momentum come in units because angular momentum depends upon the direction in which you project the picture. I said that in another lecture, that you have to look at this thing and see how the area changes. If you look at an angle, if you had something turning this way and you looked at it sideways, you wouldn't see any area changing. And if you looked at it not quite vertical, but just a little bit off, you see that the area changes a little bit different. A little bit different if you come at a small angle. So if angular momentum came in units, 8 units, and then you look not exactly down at the 8, but at a slight angle, it should look like a little bit less than 8. Now, 7 is not a little bit less than 8, it's a definite amount less than 8. So the darn thing can't possibly come in units. This proof, however, is evaded by the subtleties and peculiarities of quantum mechanics. If we measure the angular momentum about any axis, amazingly enough, it's always a number of units. So what to say about this is yes. But it's not the kind of unit like electric charge that you can count them inside. The angular momentum, although it does come in units in the mathematical sense that the number that we get in any measurement is a definite integer times a unit, we cannot interpret that in the same manner that we interpret this in the case of electricity, that there's this one and I see another one. You see those little 6 little units in there? You can't see the units, you see, but it comes out always integer anyway, which is very peculiar. Now, there are a number of other conservation laws which are more, that I should include in the list, and I'll just illustrate the type. They're not as interesting as these. They're not numbers exactly. If the laws of physics are nice, and if we were to start some kind of a device off with particles moving which had a certain definite symmetry, suppose that we had some objects that were like this, and that the exact way that they were moving was such that it was bilaterally symmetrical. Then as the laws of physics go on, and all the collisions and so on, you would probably expect, and rightly so, that if you look at this same picture later, it will be bilaterally symmetrical. So there is a kind of conservation, a conservation of the symmetry character, which should be in the list there. But it's not like a number that you measure, it's just a symmetry character. And below I will discuss it in much more detail in the next lecture. The reason it's not very interesting in classical physics, because the times in which you get such a nicely symmetrical initial conditions is very rare, and it's not a very important or practical conservation law. But in quantum mechanics, when we deal with very simple systems like atoms and so on, their internal constitution often has this kind of symmetry of some sort, like bilateral symmetry or other, and then the symmetry character is maintained, and it's an important law for understanding quantum phenomena. But I should include it in the list of all the important conservation laws, but I will discuss it next time. An interesting question is as to whether there is a deeper basis for these conservation laws or whether we have to take them as they are. And that, again, I will reserve for next time. Finally, I would like, however, to mention, to remind you that in making a popular speech on these subjects, there seem to be a lot of independent things. But with a deeper understanding of the physics, of the various principles, there are deep interconnections between the things so that one implies the other in some way. For example, the relation between relativity and the necessity for local conservation, which if I said that without the demonstration would appear to come kind of a miracle. That the statement that you can't tell how fast you're moving implies that if something is conserved, it must be done not by jumping from one place to another. And here, I would like to show you that the conservation, or indicate how the conservation of angular momentum, the conservation of momentum, and a few other things are to some extent related. The conservation of angular momentum has to do with the area swept by particles moving. Now, if the radius, if you had a lot of little particles here, and you took the center very far away, then the distances are almost the same for every object. And it doesn't make much difference. So the only thing that counts in the area sweeping, or in the conservation of angular momentum, is the component of motion vertically, say, in this case. So what we would discover is that each mass multiplied by its velocity vertically, added together, must be a constant. because the angular momentum is a constant about any point, and if that point is far enough away, then it must be only that the sum of the masses times velocities is constant. And therefore, the angular momentum implies the conservation of momentum. The conservation of angular momentum implies the conservation of momentum. And that in turn implies another thing, which is the conservation of another item which is so closely connected that I don't put it in the list, which is the principle about the center of gravity. That a mass in a box cannot just move, disappear here and move over here by itself. That's nothing to do with conservation. If you think, well, you still got the mass, and I moved it from here to here. Charge could do that, but not a mass. Let me explain why. Suppose, since the laws of physics are not affected by motions, that this box was drifting slowly upwards. And take a point not far away. Now, as it's drifting upwards, if the mass were here, quiet in the box, in the beginning it has a mass here going up and producing an area at a certain rate. After the mass has moved over here, if it's going up at the same speed because the box is drifting, then the area would be increasing at a greater rate because there's a bigger length this way, although the altitudes are the same. But by the conservation of angular momentum, you can't change the rate at which the area is changing, and therefore you simply can't move one mass from one place to the other if you don't push on something else and get rid of the momentum or angular momentum. And that's the reason why the rockets in empty space can't go. But they do go. That's because we have, the rocket is what the center of gravity, that is, if you figured it out with a lot of masses, if you move one forward, you got to move the others back so that the total motion back and forth of all the masses is nothing. Now, the way a rocket works is that here's a rocket which shoots some gas out of the back, and here's a gas. You see, beforehand, the rocket's standing still, say, in empty space, and afterwards it shoots some stuff out the back, and then the rocket's going forward. And the point is that of all of the stuff in the world, the center of mass, the average of all the mass, is still right where it was before. But the interesting part has moved out here, and an uninteresting part that we don't care about has moved out here. It is no theorem that says that the interesting things in the world are conserved, only the total of everything. The discovering the laws of physics is like trying to put the pieces together of a jigsaw puzzle. And we have all these different pieces, and today they're proliferating rapidly. And they're lying about. Many of them can't be fitted with other ones. Now, how do we know that they belong together? How do we know that they really are parts of one picture, one at present incomplete picture? We're not sure, and it worries us to some extent, but we get encouragement from the common characteristics of several pieces. They all show blue sky, or they're all made out of the same kind of wood. Thank you very much. Symmetry seems to be absolutely fascinating to the human mind. We like to look at symmetrical things in nature, such as balls, which are perfectly symmetrical, spheres, like planets and the sun and so on, or symmetrical crystals, snowflakes, flowers, which are nearly symmetrical, and so on. But it's not the objects in nature, the symmetry of the objects in nature that I want to talk about tonight. It's rather the symmetry of the physical laws themselves. Now, how can a physical law have a symmetry? It's easy to understand how an object has a symmetry. Of course, it can't. But physicists delight themselves by using ordinary words for something else. And so, in this case, they have a thing about the physical laws which is very close to symmetry of objects. And they call it the symmetry of the laws. And that's what I'm going to talk about. To show how close it is, I ask for a definition of symmetrical. What is a symmetry? If you look at me, I'm symmetrical right and left, apparently at least. A vase can be symmetrical that particular way or in other ways. How can you define it? Well, Professor Weil, a mathematician, gave an excellent definition of symmetry. It's this. As I am left and right symmetric, that means that if you put everything that's on this side, and vice versa, if you just exchange the two sides, it'll look exactly the same. Or, for instance, a square has a symmetry because if I turn a special kind, if I turn it around to 90 degrees, it still looks exactly the same. So, Weil said, a thing is symmetrical if there's something that you can do to it so that after you finish doing it, it looks the same as it did before. And then that is the sense in which we say that the laws of physics are symmetrical. That there are things that we can do to the physical laws or to our way of representing the physical laws which make no difference and leave everything unchanged in its effect. And this aspect of physical laws are what's going to concern us tonight. And we will take a number of examples. The simplest example of all of a kind of symmetry, as you'll see, it's not the same as you would have thought, left and right symmetric or anything like that. There's a symmetry called translation in space. That has the following meaning. If you build any kind of apparatus or do any kind of experiment with some things, and then go and build the same apparatus or do the same kind of experiment with similar things, but put them here instead of there, merely translate it from one place to the other in space, then the same thing will happen in the translated thing that would have happened in the original thing. It's not really true, actually. If I actually built such an apparatus and then displaced it 20 feet in that direction, it would get into the wall and there would be difficulties. It's necessary in defining this idea to take into account everything that might affect the situation, so that when you move the thing, you move everything. For example, if the system involved a pendulum, and I moved it 20,000 miles to the right, it wouldn't work right anymore because the pendulum involves the attraction of the Earth. But if I imagine I move the Earth and the equipment, then it will behave the same way. So the situation is that you must translate everything which may have any influence on the situation. Now, that sounds a little dopey because it sounds like, well, just translate it. And if it doesn't work, then you didn't translate enough stuff, and you're bound to win. Actually not. You see, it's not self-evident that you're bound to win. The remarkable thing about nature is that it is possible to translate enough stuff so that it does behave the same way. That's a positive statement. Now, I would like to illustrate that such a thing is true from the statement of the law of gravitation, for example, in which said that the forces between the objects was inversely as the square of the distance between them. And I remind you that a thing responds to force by changing its velocity as time goes on in the direction of the force. Now, if I move something from here to here, or a pair of objects like this planet going around the sun, and move the whole pair over, then the distance between the objects, of course, doesn't change, and so the forces don't change. And further, if they use when they're moved over a situation the same speed, then all the changes will remain in proportion. Everything will go around in two systems exactly the same way. So because the law said the distance between the objects, rather than some absolute distance from the central eye of the universe, but it talked about distance between the objects, then it means that the laws are translatable in space. I give another example of symmetry. That first symmetry is translation in space. The next one could be called translation in time, if you like, but better just to say a delay in time makes no difference. If we start a planet going around the sun in a certain direction, it goes around, and if we start it all over again 2 hours later, or say 2 years later, with another beginning, starting the planet and the sun going in the same way, it'll behave in exactly the same way. Because again, the law of gravitation, as stated, talks about the velocity and never talks about the absolute time and when you were supposed to start measuring things. In this particular example, we are really not sure. When we discussed gravitation, we talked about the possibility that the law of the force of the gravity changed with time. Now, this would mean that the translation in time was not a valid proposition, because if the constant of gravitation is weaker 1 billion years hence than now, then it isn't true that the motion will be exactly the same for an experimental sun and planet 1 billion years from now as it is now. But as far as we know today, all the law, I've discussed only the laws as we know them today. I wish I could discuss the laws as we will know them tomorrow, but I cannot. But as far as we know, a delay in time makes no difference. Actually, we know that isn't really true. That's true for what we now call the physical laws. But one of the facts of the world, which is very different, well, which is maybe very different and maybe not different than a physical law, is the fact that it looks like the universe had a definite time of beginning, that everything is exploding apart. Now that you might call a condition of geography, analogous to the situation that if I say I translate, I don't translate everything I have to move that wall if it's going to make any difference. And in the same sense, you would say, oh, I see, he means the laws are the same. The universe expanded and everything else, but we could have made another analysis in which we start the universe later. But we don't start the universe, and we have no control on the situation, and we have no way to define that idea experimentally. Therefore, as far as the science is concerned, there really is no way to tell. And the fact of the matter is that the conditions of the world are changing in time. As we know, apparently, at least the galaxies are all separating from one another. So if you were to awake in some science fiction story at an unknown time, by measuring the distances, the average distances to the galaxies, you could tell when it was. And that means that the world will not look the same if delayed in time. Now, it is conventional today to separate the physical laws which tell how things will move if you start them in a given condition from the statement of how the world actually began, because we know so little about that. And it is usually considered that astronomical history or cosmological history or whatever you want is a little different than physical laws. But if put to a test of how would you define a difference, I would be hard-pressed. The best characteristic of physical law is its universality. And if there's anything universal about the thing, it's the universal expansion of all the nebulae. So I have no way of defining that. But if I restrict myself to disregard that matter, then as far as the other physical laws are known, and the law that determines how the thing expands, the cause of it and so on, is not known. If you take only the physical laws that are known, a delay in time makes no difference. Now we take some other examples, and another is a rotation in space, a fixed rotation. If I build a piece of equipment and do some experiment with a piece of equipment built here, and then take another one, better translate it so it doesn't get in the way, here, but turn it so that all the axes are a different direction, it'll work the same way. Again, we have to turn everything that's relevant. If the thing is a grandfather clock and you turn it this way, well, the pendulum will just sit up against the wall of the can and won't work. But if you turn the Earth too, as is going on all the time, it still keeps working all right. The mathematical description of this possibility of turning is a rather interesting one, because to describe what goes on in the situation, we like to use numbers to tell where something is. They're called the coordinates of a point, and we use, for instance, sometimes 3 numbers to do it. How high it is above some plane, how far it is in front of me, say, and back is the negative numbers, and how far to the left. Suppose I did that, and I'm not going to worry about up and down, because for rotations I just have to use 2 of these 3. Let's call the distance this way x, in front of me, and y is how much to the left. And I can locate any body by telling how far he is in front, how far to the left. Those who come from New York City will know that the street numbers work that way very neatly. But until they began to change the name of 6th Avenue. Now, the mathematical idea about the turning is this, that if I'm set at a somewhat different angle and make my calculations, then what's directly in front of me at distance x is a mixture. Let's say there's a man over here, you, who's standing this way and making his analysis, and me standing this way and making my analysis. When I measure distance x, if I go straight out at x and don't change to the right or to the left, you see that that line is a mixture of some of your xy business and some of the y. So that the connection, the transformation is that x gets mixed into x and y gets mixed into y and x, and that the laws of nature shall be so written that if you make such a mixture and resubstitute it in the equations will not change their form. That means that's the mathematical way in which the symmetry appears. If you write in mathematical form, the symmetry appears this way. You write the equations with certain letters, then there's a way of changing the letters from x and y to a different x prime, and a different y prime, which is some formula in terms of the old x and y, and the equations look the same, only have primes all over them. That just means that the man will see the thing behaving in this apparatus the same way as I see it in mine, which is turned the other way. I give another example. This example is very interesting. It's a question of uniform velocity in a straight line. It is believed that the laws of physics are unchanged under the symmetry, under the operation of making a uniform velocity in a straight line. This is called the principle of relativity. If we have, for instance, a spaceship, and we have an equipment in it that's doing something, and we have another equipment down here on the ground, and the spaceship is going along at a uniform speed, then inside the spaceship, somebody watching what's going on can see nothing different than the man that's standing still in his apparatus in there, because he looks outside, or he bumps into an outside wall, or something like that. It doesn't matter. But insofar as he's moving at a uniform velocity in a straight line, the laws of physics look the same to him as they do to me, who is not moving. Since that's the case, I cannot say who's moving. Now, I insist and emphasize here something before we go any further, that in all of these transformations and all of these symmetries, we are not talking about moving the whole universe. Just like the case of the time, I could imagine I moved all the times in the whole universe, but that doesn't make any difference. There'd be no content to the statement that if I took everything in the whole universe and moved it over, it would all behave the same way. The very remarkable thing is that if I take a piece of apparatus and move it over, then if I make sure about a lot of conditions and include enough apparatus, I can get a piece of the world and move it relative to the average of all the rest of the stars, and it still doesn't make any difference. And in this case, it means that someone coasting at a uniform velocity in a straight line relative to the average of the rest of the nebulae sees no effect. It is impossible to determine by experiments inside a car without looking out by any effects that you're moving relative to all the stars if you want. This proposition was first stated by Newton. Let's take his law of gravitation, for instance. It said that the forces are inversely as a square. So let's see, what else? Yes. And that the force produces changes in velocity. Now, suppose that I watch a moving thing. If, for instance, I have worked out what happens when a planet goes around a fixed sun. And now I want to work out what happens when a planet's going around a drifting sun. Well, then all of the velocities that I had in the first case are different than in the second case. I just add a constant velocity on. But the laws are stated in terms of changes in velocity. So that what happens is that the pull of this planet for this changes this one's speed, and on the other case changes its speed by the same amount. So anything that I started with, any initial speed that I started with, just keeps on going, and all the changes are accumulated on top of that. That's not very good description, but the net result of the mathematics is that if you add a constant speed, the laws will be exactly the same, so that we cannot, by studying the solar system and the way the planets go around the sun, figure out whether the sun is itself drifting through space. There's no effect of such a drift through space on the motion of the planets around the sun, according to Newton's law, so that Newton said, the motion of bodies among themselves is the same in a space whether that space is itself at rest relative to the fixed stars or moving at a uniform velocity in a straight line. Now, it turns out that as time went on, new laws were discovered after Newton, and those were the laws of electricity by Maxwell. And one of the consequences of the laws of electricity was that there should be waves, electromagnetic waves, light, in fact, as an example, which should go at 186,000 miles a second flat. I mean by that, 186,000 miles a second, come what may. So then it was easy to tell where rest was, because a law like if light goes 186,000 miles a second is certainly not one, or at first sight, is certainly not one which is quite right, which will permit one to move and get the same law, because it's evident, is it not, that if you're in a spaceship going 100,000 miles a second in that direction, and I'm standing still and shoot a light beam at 186,000 miles a second, you look out the window, or if I shoot the beam through a little hole through your ship, as it goes through your ship, since you're going 100,000, the light's going 186,000, the light is only going to look like it's passing you at 86,000 miles a second. But if you do the experiment, it looks like it's going 186,000 miles past you and past me. The facts of nature are not so easy to understand. And the fact of the experiment was so obviously counter to common sense that there are some people who still don't believe the result. But experimentally, time after time, experiments indicated that the speed is 186,000 miles a second, no matter how fast you're moving. And now the question, how could that be? Poincaré proposed that one take as one of the principles of nature that the Maxwell's principles of Maxwell's equations are right, and that the mathematical changes needed to compare a system moving and a system standing still that come in that case should be, well, I'm making it sound too complicated. I'll come back and change the way of stating it. Einstein realized, and Poincaré too, and it's hard to get the history right while you're trying to explain the idea at the same time, that the only possible way in which a person moving and a person standing still could measure the speed to be the same was that their sense of time and their sense of space are not the same, that the clicking clocks inside the spaceship are ticking at a different speed than they are in the ground, and so forth. Of course, you say, yeah, but if the clock is ticking, I look at the clock in the spaceship and I see it's going slow. No, your brain is going slow, too. So by making sure that everything went just so inside the spaceship, it was possible to cook up a system by which in the spaceship it would look like 186,000 spaceship miles per spaceship second, whereas it looks like 186,000 my miles in my seconds at the same thing. It was a very ingenious thing to be able to do. It turns out remarkably enough to be possible. I mentioned already one of the consequences of this principle of relativity, that you cannot tell how fast you're moving in a straight line, in which we had two cars, and there was an event. It happened at each end of this car. A man was standing in the middle of the car, and there was an event that happened at each end of this car at a certain instant, which this man claimed was the same time, because standing in the middle of the car, he saw the light from both of these things at the same time. Whereas a man in another car, who happened to be moving this way with a velocity, saw these same two events, not at the same time, but in fact saw the one here first, because the light reached him before the light from here, because he's moving forward. So you see that one of the consequences of the principle of symmetry for a uniform velocity in a straight line, that symmetry means you can't tell who's right, is that when someone talks about something like, when I talk about everything that's happening in the world now, that doesn't mean anything. If you're moving along at a uniform velocity in a straight line, everything that happens at now, simultaneously, is not the same events as my now, even though we're passing each other in our instant. Here is the same, but somewhere else, we cannot agree what now means at a distance. So this means a profound transformation in our ideas of space and time in order to maintain this principle that you can measure, that uniform velocity in a straight line cannot be detected. Actually, what's happening here is that a little bit, that the time, from one point of view, two things that are simultaneous seem from another point of view to be not at the same time, provided they're not at the same place, that they're far apart in distance. that's very much like my x and y. Two things which seem to me to be at the same horizontal, well, let's say the same distance in front. 0 distance in front. Well, from somebody this way, he'll say one of them is in front of me and one of them is in back. See, consider, from my point of view, they're both even with me. That wall and that wall is even with me. But if I stand and turn like this and look at the same pair of walls but from a different point of view, that one's in front of me and that one's behind. And so it is that the two events which from one point of view seem to be at the same time, from the other point of view seem to be at different time, and the generalization of the two-dimensional rotation that I'm talking about into space and time was made, so that the time was added to the space to make a four-dimensional world. And it's not merely an artificial addition to say, well, we add time to space because, as it sees in most of the popular books, you can not only locate a point, but you have to say when. That's all true, but that doesn't make it real space. That just puts two things together. Real space has, in a sense, the characteristic that looked at from a different, it's possible to look at it from a different point of view, that has an existence that is not, that it has an existence that's independent of the particular point of view, that there's a commonness, that a certain amount of time can get mixed up with a certain amount of space. So that space and time must be completely interlocked. And after this discovery, Minkowski said that space of itself and time of itself shall sink into mere shadows, and only a kind of union of the two shall survive. I bring this particular example up in such detail because it is really the beginning of the study of symmetries in physical laws. It was Poincaré's suggestion to make this analysis of what you can do to the equations and leave them alone. It was Poincaré's attitude to pay attention to the symmetries of physical laws. The symmetries of translation, space, delay, and time, and so on, were not very deep. But the symmetry of uniform velocity in a straight line is very interesting and has all kinds of consequences. Furthermore, by these consequences were extendable into laws that we did not know. By guessing that this principle is true with the disintegration of a mu meson, we don't know why the mu meson disintegrates in the first place. We can tell a lot about it by the proposition that we can't use mu mesons to tell how fast we're going in a spaceship either. And that tells us something, at least, about the mu meson disintegration. There are many other symmetries of some of them are of different kinds. I just mentioned there and others. Another one is that you can replace one atom by another of the same kind, and it makes no difference to any phenomenon. Now, you say, yeah, what do you mean by the same kind? You mean one way, you replace it by the other one, it doesn't make any difference. It looks like physicists are always talking nonsense in a way, isn't it? Because there are many different kinds, and if you replace one by one of a different kind, it makes a difference, but if you replace one of it by the same kind, it doesn't make any difference, and that just seems like a circular definition. But the meaning of the thing is that there are atoms of the same kind. That it is possible to find classes of atoms, that you can replace one by another of the same kind, and it doesn't make any difference. There are such things. Since the number of atoms in any little tiny piece of material is 1 followed by 23 noughts or so, it's very important that they're the same, that they're not all different kinds. And it's really very interesting that we can classify them into a limited number of a few hundred atoms, so that the statement that we can replace one atom by another of the same kind has a very great amount of content. It has the greatest amount of content in quantum mechanics, and it is impossible for me to explain how, partly, but only partly because this is an audience that is mathematically untrained. It's quite subtle anyhow. But in quantum mechanics, the proposition that you can replace one atom by the same kind has marvelous consequences. It produces peculiar phenomena in liquid helium, the liquid that flows through pipes without any resistance, just coasts on forever. It has all kinds of consequences. In fact, it's the origin of the whole periodic table of the elements and the force that keeps me from going through the floor. But I can't go into that particular thing, but I want to emphasize the importance of looking at these principles. By this time, you're probably convinced that all the laws of physics that are symmetric under any kind of change whatsoever. So I have to give a few ones that don't work. First one, change of scale. It is not true that if you build an apparatus and come over here and build one twice as big, every part made exactly the same kind of stuff, but twice as big, that it will work exactly the same way. You who are familiar with atoms are aware of this fact, because if I made it 10 billion times smaller, I would only have 5 atoms in it. And I can't make a machine tool, which this thing is with screw threads and so on, out of 5 atoms. So it's perfectly obvious if we go far enough that we can't change the scale. But even before the complete awareness of the atomic picture was developed, it became apparent that this law isn't right. You've probably seen in the newspapers from time to time somebody who's made a cathedral with matchsticks. Several floors and beautifully delicate and everything, just more Gothic than any Gothic cathedral has ever been. More delicate. Why don't we build big ones like that with great logs, with the same degree of ginger cake, the same enormous degree of detail? The answer is, if we did, it would be so high and so heavy it would collapse. You say, yeah, but you forgot when you're comparing two things, you must change everything that's in the system. The little cathedral made with matchsticks is attracted to the earth. So to make the comparison, I should make the big cathedral attracted to an even bigger earth. Too bad. A bigger earth would attract it even more, and the sticks would break even more surely. This fact that the laws of physics were unchanged under scale was first discovered by Galileo. He argued in discussing the strength of rods and bones. He argued that if you need a bone for a bigger animal, say an animal is twice as high, wide, and thick, you need 8 times the weight. So you need a bone that can hold the strength 8 times. But what a bone can hold depends on its cross-section. And if you made the bone twice as big, it would only have 4 times the cross-section, would only be able to support 4 times the weight. And in Galileo's book called The Two New Sciences, you'll see pictures of imaginary bones of enormous dogs way out of proportion. Galileo felt that the discovery, I suppose he felt, I don't know, but the discovery of the fact that the laws of nature are not unchanged on the change of scale was as important as his laws of motion, because they're both put together in a tome called On Two New Sciences. Now I go on to another example of something that is not a symmetry law, and that is, it is not true that if you're spinning at a uniform angular speed in a spaceship, you can't tell that you're going around. You can't. Everything gets thrown to the walls. I was going to say you get dizzy, but that soon passes. There are a lot of effects, however. Things do get thrown to the walls from the centrifugal force, or however you wish to describe it. I hope that there's no teachers of freshman physics here to correct me. But it is possible to tell that the Earth is rotating by a pendulum or by a gyroscope. And you're probably aware in various observatories and museums and so on, have these so-called pendulums that proves the Earth is rotating without looking at the stars. So it is possible to tell that we are going around at a uniform angular velocity on the Earth without looking outside, because the laws of physics are not unchanged by that. Many people have proposed that really you're rotating relative to the galaxies, see? And if you would turn the galaxies too, it wouldn't make any difference. Well, I don't know what would happen if we would turn the whole universe, and we have at the moment no way to tell. Nor at the moment do we have a theory which describes the influence of a galaxy on things here, so that it comes out of this theory in a straightforward way, and not by cheating or forcing or anything like that, in a straightforward way, that the inertia for rotation, that the effects of rotation, the fact that a spinning bucket of water has a shape in the surface like this, that this is the result of a force from the objects around. That's not known to be the case. That this should be the case was called Mach's principle, but that it is the case has not yet been demonstrated. But the real question is, the more direct experimental question is that if we're rotating at a uniform velocity relative to the nebulae, do we see an effect? The answer is yes. If we're moving in a spaceship at a uniform velocity in a straight line relative to the nebulae, do we see an effect? The answer is no. 2 different things. So don't say all motion is relative. That's not the content of relativity. Relativity says that uniform velocity in a straight line is undetectable. Relative to the nebulae is undetectable. Now, the next symmetry law that I would like to discuss is an interesting one that has an interesting history, and that's the question of reflection in space. If I build a piece of apparatus, let's say a clock, And then I come over here and I build another clock exactly the same way, but like this one looks in a mirror. I don't mean I look at this one in a mirror only. I mean I build another clock, which is built to be a Chinese copy of what the other one looks like in a mirror. In other words, I have the number 2 painted neatly on the dial here, then I paint the number 2 on the other way around over here. So I got an opportunity to make a drawing. 2 on one clock, 2 on the other clock. Which is wound one way in one clock is wound in the corresponding opposite way in the other clock. They match each other like 2 gloves, right and left. Now we wind up the 2 clocks. We set them in corresponding positions. I was going to say the same, but we set them to the mirror positions, and we let them tick. Question, will they always agree with each other? Will all of the machinery of the clock go in the mirror image of the other one? And I don't know what you would guess about that. You probably guess it's true, and most people did guess it was true. Of course, we're not talking about geography. We can distinguish right and left by geography. We can say that if we stand in Florida and look at New York, the ocean is on the right, and that distinguishes right and left. And and if the clock involves the water of the sea and then New York and so on, then it wouldn't work if you built it the other way because its tickler wouldn't get in the water. But what we have to imagine, of course, is that the geography of the earth is turned around too on the other clock. Anything that's involved must be turned around. Nor are we interested in history. For example, if you pick up a screw in a machine shop, the chances are it's right-hand thread. And you might argue the other clock isn't going to be the same as this one because it's harder to get the screws. But that's just a question of what kind of things we make. So that altogether, the first guess is that it doesn't make any difference. And it turns out that the laws of gravitation are such that it wouldn't make any difference if it worked by gravity. The laws of electricity and magnetism are such that if in addition it had electric and magnetic guts, currents and wires and whatnot, it would still vote. The corresponding clock would run the same. And if the clock involved nuclear reactions, ordinary nuclear reactions, to make it run, it wouldn't make any difference either. But it does make a little bit of difference. I'll come to what makes a difference in a minute. But the first possibility that may suggest itself to you, if you know anything much, you may have heard that it's possible to measure the concentration of sugar in water by putting polarized light through the water. If you put the piece of Polaroid that lets light through in a certain axis through the water, then you'll find in order to, when you watch the light as it goes through deeper and deeper sugar water, you have to turn the Polaroid another piece of Polaroid at the other end of the water more and more to the right as the stuff goes through. Maybe it's to the left. I can't remember, but let's say to the right as you go through deeper, deeper solution. And if you make the water light go the other way through the solution, it's still to the right. So there's a right-hand way, there's a difference for right and left. So if we put sugar water in the clocks and light, then if we put, say, in one tank of water and make the light go through and turn and put the Polaroid so it can just get through, and make the corresponding image on the other side, hoping the light would turn this way, it'll turn the other way, and it won't go through right. So by using sugar water, our 2 clocks can be made different. So it's a very remarkable fact. And it isn't true, therefore, at first, that the 2 clocks that the physical laws are symmetric for reflections. However, it's possible to make sugar in the laboratory. The sugar that we got that time might have been from sugar beets, but sugar isn't a complicated molecule. And it's possible to make sugar in a laboratory out of carbon dioxide and water and going through lots and lots of stages in between and make artificial sugar. When you put the artificial sugar in there, which is chemically and measured every way, it seems to be the same, it doesn't turn the light. Then, if you put bacteria in the water, in the sugar water, bacteria eat the sugar. And when you let the bacteria eat the sugar, and then try with what's left, it turns out, first, they only eat half the sugar. The artificial sugar. Second, when you're all done, it turns to the left, the stuff that's left. And now you find the explanation to all this is the following. A sugar is a complicated molecule, a set of balls, atoms, in some complicated arrangement. If you make exactly the same arrangement, but left as right, like if the arrangement is complicated like this, then you make one the same way. Then every distance between every pair of atoms is the same in one as in the other. The energy of the molecules is exactly the same. And for all chemical phenomena not involving life, they're the same. But living creatures find a difference. The bacteria eats one kind and not the other. The sugar that comes from sugar beets is only one kind, all left-hand molecules. And so, or right-hand, and so it turns the light one way. The bacteria can only eat that kind of molecules. When we manufacture the sugar from substances which themselves are not asymmetrical, simple gases, we make both kinds in equal number. Then, if we let the bacteria eat, they'll eat the kind they can eat, and the other is left, and that's why it comes out the other way. It's possible to separate the two by looking through magnifying glasses at the crystals and separating them and so on, as Pasteur discovered, and so forth, so that we can definitely show that all this makes sense, and even our artificial sugar, then we can separate ourselves. We don't have to wait for the bacteria. But the interesting thing is that the bacteria can do this. Does that mean that the living processes don't obey the same laws and so on? Apparently not. It seems that in the living creatures there are many, many complicated molecules, and they all have a kind of thread to them. One of the most characteristic molecules in living creatures are proteins, and it takes a little while to explain the details, but let's put it very simply. They have a corkscrew property, and they go, let's say, to the right. Now, as far as we can tell chemically, if we could make this chemically, the same thing to the left, it would not function biologically because it wouldn't, when it met the other proteins, fit the same way. That is, a left-hand thread will fit a left-hand thread, but a left and right don't fit very well the same way. So the bacteria, having a left-hand thread in their chemical inside, can distinguish the left and right sugar. How did they get that way? Physics and chemistry cannot distinguish the molecules. It can only make both kinds, but biology can. It's easy to believe that the explanation is that in a long, long ago, when the life processes first began, some accidental molecule got started and propagated itself by reproducing itself, and so on, until after many, many years, these funny-looking blobs with the prongs sticking out yak at each other. But they are nothing but the offspring of the first few molecules, and then the accident of the first few molecules that it happened to form one way instead of the other. It has to be one or the other. So the thing that reproduces itself is either left or right, and then it goes on and propagates this on and on. It's much like the screws in the machine shop. Use right-hand thread screws to make new right-hand thread screws and so on. So this is probably one of the deepest demonstrations of the fact that the protein molecules are exactly the same in all life. They all have exactly the same kind of thread. Is probably one of the deepest demonstrations of the uniformity of the ancestry of life, the common ancestry of all life, and from back, in fact, to the completely molecular level. Now, in order to test better this question about whether the laws of physics are the same right and left, we can put the problem to ourselves this way. Suppose that we were in telephone conversation with a Martian or an Arcturian or something. We don't know where he is, and we would like to describe things to him. We want to tell him about things. We say, well, how is he going to understand the words? Well, that's been studied very much by Professor Morrison here. And he has pointed out that one way would be to start out and say, tick, tick, 2, tick, 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 3, and so on. And pretty soon the guy would catch on to the numbers. And then as you understand your number system, then you could write lots of numbers, and you could, for example, write a whole sequence of numbers that represents the weights, the proportional weights of the different atoms in succession. And then say hydrogen, 1.00, deuterium, and so on. And he would, after he sat down with all those numbers and piddled around a while, would discover that the mathematical ratios were the same as the ratios of the weights of the elements, and therefore those names must refer to elements. And so gradually you could, in talking to him, have a common language. In many ways, common. There are many. Now comes the problem. Suppose that he says, you fellas, after we get familiar with him, he says, you're very nice. Now I'd like to know what you look like. And you start out, well, we're about 6 feet tall. He says, 6 feet. How big is a foot? It's very easy, you say. A foot, 6 feet tall, is 170,000 million hydrogen atoms high. Well, it's not a joke. It's a possible way of describing 6 feet to someone that has no measure, assuming that we cannot send them any samples, nor can we both look at the same object. We have to tell them how big we are, we can do it. That's because the laws of physics are not unchanged under a scale change. So we can use that fact, to use the properties of the scale to determine, you can use that fact to determine the scale. Well, here we describe ourselves after telling us 6 feet tall and with so-and-so bilateral on the outside, and we look like this, and there are these prongs sticking out and all this. And he said, that's very interesting. What do you look like on the inside? So we describe the heart and so on, and we say, now put the heart in on the left side. Now the question is, how can we tell him which side is the left side? By what possible, you say, you take beet sugar, see, and you put it, in water, and it turns. Only trouble is he has no beets up there. Or we have no way of knowing whether the evolution, if it was even corresponding to the same proteins on Mars as here, whether the accidents of the evolution would have started with maybe the wrong-handed threads. So there's no way to tell. So after much thought, you see you can't do it. And so you conclude it's impossible. However, about 5 or 6 years ago, certain experiments indicated that they got reduced all kinds of puzzles. I won't go into detail. We got into tighter and tighter difficulties, more and more paradoxical situation, until somebody proposed, Li and Yang proposed, maybe the principle that right and left symmetry, that nature is the same for right and left, is not right. And that would help to explain a number of mysteries. And Li and Yang proposed some more direct experiments to demonstrate this, and I'll just mention the most direct of all the experiments, the easiest way to tell, or experiment done. Well, there were several first experiments which were quite clear, but the one that's easiest to explain is this. That when we have a radioactive disintegration, in which an electron and a neutrino are emitted. For example, this is one that we talked about before, electron and antineutrino. Or this is a neutron disintegrating into a proton, electron, and an antineutrino. Or the corresponding thing can happen to a neutron and a nucleus. Anyway, there are many radioactivities in which the charge of the nucleus increases by 1 and an electron comes out. The thing that's interesting is that if you measure the spin, electrons are spinning as they come out. If you measure the spin, you find out that they're spinning to the left. That is a definite significance, that the electron, when it comes out of the disintegration, is turning this way. And that helical description is a left-hand thread. It's as though, in the beta decay, the gun that was shooting out the electron were a rifled gun. And there's 2 ways to rifle a gun, because there's a direction, out. And then there's a question, do you turn it this way or that way as you go out? And the experiment is that the electrons come from a rifled gun, rifled, twisted to the left. And so, using this fact, we can call up the Martian and say, listen, take radioactive stuff. Now, I ought to prepare a particular example, a neutron. And look at the electrons, which come from such a beta decay. And then you define left by this screw thread, and let's see, it'll take me some while to figure out how to do it in detail. Say the electron's going up, and the direction of motion of the way it's spinning is into the body on the left side, and that's where the heart goes. Something like that. I'd have to think a little bit more of it. But anyway, it is possible to tell right from left, and thus the law of this, that the world was symmetrical for left and right, has collapsed. Every conservation law has, well, the next thing I would like to talk about is the relationship of conservation laws to symmetry laws. We last time talked about conservation principles, conservation of energy, of momentum, angular momentum, and so on. Now we're talking about symmetry laws. It's extremely interesting that there seems to be a deep connection between the conservation laws and the symmetry laws. This connection has its proper interpretation, at least as we understand it today, only in the knowledge of quantum mechanics. Nevertheless, I will show you the following, that try to explain the following, that if we will assume that the laws of physics are describable by a minimum principle, that the paths are taken so that some quantity is least, an idea I described once before. If we add that the laws of nature come from a minimum principle, then we can show that if the law is such that you can move all the equipment to one side, in other words, if it's translatable in space, then there must be conservation of momentum. that there's a deep connection between the symmetry principles and the conservation laws, but that connection requires that the minimum principle be assumed. You remember at one time we discussed the one way of describing physical laws by saying that a particle goes from one place to another in a given length of time by trying different paths, and the actual path taken has this property, that there's a certain quantity, which unfortunately happens to be called the action, which is not to be taken to signify anything because it's got nothing to do with action. Anyway, there's a certain quantity called the action, which you calculate on this path. And if you will calculate it for any other path, the answer is bigger. It's least for the real path. And that one way of describing the laws of nature is to say that the action, a certain mathematical quantity, is least for the actual path than for any other path. Now, another way of saying the thing is least is to say this, that if you move the path a little bit, at first it doesn't make any difference. Suppose you were walking around in a wood, on mountains, on hills, but smooth hills, please. Smooth. The mathematical things that were involved here correspond to smooth hills. Walking around on hills and valleys, and we come to a place where we're lowest. Then I say, if you take a small step forward, you won't change your height. When you're at the lowest, or at the highest point, a step doesn't make any difference in the altitude in first approximation. Whereas if you're on a slope, you can walk down the slope with a step. And then if you take the step in the opposite direction, you walk up. And that's the key to the reason why, when you're at the lowest place, taking a step doesn't make much difference, because if it did make any difference, if you took the step in the opposite direction, you'd go down. I mean, if it went up one way, it would go down the other way. But since this is the lowest point and you can't go down, in first approximation, the step doesn't make any difference. So we therefore know that if we move this path a little bit, in first approximation, it doesn't make any difference to the action. Now I want you to consider the following possible other path. First, we jump immediately over to another place here nearby. Then we go along. This sticks out too far to make the diagram clear, so if you permit me to just change the shape of the path. Then we move on exactly the corresponding path to another point here, which is displaced the same amount, of course, because it's the corresponding path to this side. Now, we have just discovered that the laws of nature are such that the action, the total amount of action going on this path is the same in first approximation to that path. That's from the minimum principle, when it's the real motion. Now I show you something else, that the action on this path is the same as the action from this little cross to that little cross if the world is the same when you move everything over, because the difference of these two is only that you moved everything over. So if the symmetry principle of translation in space is right, if that's right, then a total action between the crosses is the same as between the dots. But for the true motion, the total action on this cockeyed path here is very closely the same as for the original one. So subtracting equals from equals and so on and so on. Anyway, you can probably see, therefore, that the contribution from this little section and from this little section are equal. But in making this little motion, we're going this way, and making this one, we're going the other way. So if we make the contribution of this taken as the effect of moving that way, and the contribution of this thinking of it as an effect of moving that way, but taking it the other side because it's the other way, we see that there is a quantity here which has to match the quantity here to cancel out, which is the effect on the action of a little tiny step in the x direction. So there is that quantity, the effect on the action of a small step in the x direction is the same at the beginning as at the end. There is a quantity, therefore, that doesn't change as time goes on, provided minimum principle works and symmetry principle of displacement in space is right. Now, this quantity, which doesn't change, is in fact exactly the momentum we discussed last time. A corresponding argument for the displacement in time, the delay in time, comes out as the conservation of energy. The case that if we rotate in space doesn't make any difference, comes out as the conservation of angular momentum, and so on. That we can reflect and it makes no difference doesn't come out to be anything simple in the classical sense, and it hasn't therefore got a simple classical interpretation, and people have called it the parity, and they have a conservation law called the conservation of parity, but those are just complicated words in the case of the quantum mechanics. All we're saying is that the right and left symmetry law is not valid. But I have to mention that conservation of parity because you may have read in the papers that the law of conservation of parity has been proved wrong. It should have been written because it's much easier to understand. The principle that you can't distinguish right and left has been proved wrong. Now, I would like to say, as we go on about other symmetries, that there are a few problems, new problems. For instance, for every particle, like an electron, there's an antiparticle, a positron. For a proton, there's an antiproton. And we can make in principle, what we call antimatter, in which every atom has its corresponding anti-pieces put together. For example, a hydrogen atom is a proton and an electron. If we take an antiproton, which is electrically negative, and a positron and put them together, they will also make a kind of hydrogen atom, an anti-hydrogen atom, in principle. It's never been made, in fact, but this is figured out that we could make this. And so we could make all kinds of antimatter in the same manner. Now the question is whether the matter works the same as the antimatter. And as far as we know, it does. And one of the laws of symmetry is that if we make stuff out of antimatter, it'll behave the same way as we make the corresponding stuff out of matter. Of course, if they come together, they annihilate, there are big sparks and everything else. And it was believed that this is true, that matter and antimatter have the same laws. Now, the next question is this. Once it's found that the left and right is wrong, the left and right symmetry is wrong, an important question comes. If I look at this integration but with antimatter, an anti-neutron goes into an anti-proton plus an anti-electron, that's an positron, plus a neutrino. The question is the antimatter behave like the matter in the sense that it comes out left-hand thread, or does it behave the other way? And it turns out, we think up until a few months ago, that it behaves the opposite way, and that the antimatter behaves like it goes to the right, where matter goes to the left. And so there was another principle that, in fact, we really can't tell the Martian which is right and left, because if he happens to be made out of antimatter, he'd get the thing the other way, because when he does his experiment, his positrons are coming out, puts the heart on the wrong side. And so you can see that if you telephone the Martian, explain how to make a man, and suppose he makes one and it works. Well, let's make it, and he explained to him also all our social conventions and so on. Then when we go finally to meet this man, after he tells us how to build a sufficiently good spaceship, we go to meet this man and you walk up to him, and if you put out your right hand to shake hands, if he puts out his right hand, okay, but if he puts out his left hand, watch out, because the two of you... the two of you will annihilate with each other. These are all the symmetries that I have time to tell you about. I wish I could tell you about a few more, but they become more difficult technically to explain. And there are some very remarkable things, which are the near symmetries. The remarkable feature of this effect that we can distinguish right and left is that we can distinguish right and left only with a very weak effect, with this beta disintegration. What it means that nature is 99.99 indistinguishable right from left, but that there's just one little piece, one little characteristic phenomenon which is completely different in the sense that it's absolutely lopsided, is a mystery that no one has the slightest idea about yet. Thank you.
tree.
The distinction of past and future.
Now, it's obvious to everybody that the phenomena of the world are evidently irreversible. By that I mean things happen that don't happen the other way. You drop a cup and it breaks, and you can sit there a long time waiting for the pieces to come together, to come back into your hand. If you watch the waves breaking at the sea, you stand there and wait for the great moment when the foam collects together, rises up out of the sea, and falls back further out from the shore. Would be very pretty. As a matter of fact, the demonstration of this in such lectures is usually made by having a section of moving picture in which you take a number of phenomena and running the thing backwards and then see all the laughter. The laughter just means this ain't going to happen in the real world. But actually, that's a kind of a weak way to put something which is so obvious and deep as the difference between the past and the future. Because even without an experiment, our very experiences inside are completely different for past and future. We remember the past, we don't remember the future. We have a different kind of awareness about what might happen than we have of what most likely has happened. And the past and future look completely different psychologically and so forth. And the questions of memory, of apparent freedom of will, in the sense that we feel that we can do something to affect the future, but none of us, or very few of us, believe that there's anything you can do to affect the past. And remorse and regret and hope and so forth are all words which distinguish perfectly obviously the past and the future. Now, if the world of nature is made of atoms, and we too are made of atoms and obey physical laws, there's obvious distinction between what happened, the past and the future, and this obvious irreversibility of all phenomena, you would think would most likely have obviously its interpretation in that some laws, some of the motion laws of the atoms are going one way, that the atom laws are not such that they can go either way, that there's somewhere in the works some kind of a principle that wuxels only make wuxels and never vice versa, and so the world is turning from wuxely character to wuxely character all the time. And that this one-way business of the interactions of things is the thing that makes the whole phenomena of the world seem to go one way. And yet we haven't found it yet. That is, in all the laws of physics that we've found so far, there doesn't seem to be any distinction of the past and the future. That the moving picture should work the same way going both ways, and the physicist who looks at it should not laugh. Details now to be explained. Let us take the law of gravitation as our standard example. If I have a sun and a planet that I started off in some direction going around to here, and then take a moving picture of this, say it gets to here. Now take a moving picture of this backwards. Take a moving picture of it, and run the movie backwards and look at it. What happens? Planet goes around the sun in an ellipse. The speed of this way, of course. Starts here, goes to here, keeps on going around. Goes in an ellipse. The speed of the planet is such that the area swept out by the radius is always the same in equal time. Just does exactly the way it ought to do. Perfectly satisfactory. It cannot be distinguished from the one going the other way. So the law of gravitation is of such a kind But it doesn't make any difference. If you show the phenomenon running, any phenomenon involving just gravitation running backwards on a film, it'll look perfectly satisfactory. Put it precisely more this way. If at a given instant the particle moving this way, if all the particles in a more complicated situation would have every one of their speeds reversed suddenly, then the thing will just unwind through all the things that it wound up into. That is, if you have a lot of particles doing this, then you suddenly reverse the speeds, they will completely undo what they did before. Now this is in the laws of gravitation, which say that the velocity changes as a result of the forces and so on. If I reverse the time, the forces are not changed, and so the changes in velocity are not altered at corresponding distances. And so each velocity then has its succession of alterations made in exactly the reverse way that they were made when it went out before, and it's easy to prove that the law of gravitation is time reversible. The law of electricity and magnetism, time reversible. The laws of nuclear interaction, time reversible as far as we can tell. The laws of beta decay that we talked about at a previous time, also time reversible. The difficulty of the experiments of a few months ago, which indicate that there's something the matter with some unknown about the law, suggests the possibility that, in fact, it may not be also time reversible, but we shall see. But at least the following is true. This beta decay that we're talking about, which may not be time reversible, but I don't know, is a very unimportant phenomenon for most ordinary circumstances. The possibility of my talking to you does not depend on that happening. It does depend on chemical interactions. It depends on electrical forces. It doesn't actually depend much on nuclear forces at the moment, but it depends also on gravitation. But I am one-sided. I speak and the voice goes out into the air and doesn't come sucking back into my mouth when I open it. And this irreversibility cannot be hung on the phenomenon of beta decay. In other words, we believe that there are in the world most of the ordinary phenomena which are produced by atomic motions which, according to laws, which can be completely reversed. So we have to look some more to find the explanation. If we look at this more carefully, and a planet's moving around the sun more carefully, you soon find that it isn't quite right. For example, the Earth's rotation on its axis is slightly slowing down. It's due to tidal friction. And you see that friction is something which is obviously irreversible. If I took a heavy weight on the floor here and pushed it, it would slide and stop. I stand and wait for it. It doesn't suddenly start up and speed up and come into my hand. So a frictional effect seems to be irreversible. But a frictional effect, as we discussed at another time, is the result of enormous complexity of the interactions of the block with the wood. The jiggling of the atoms inside, that the organized motion of the wood, of the block, is changed into disorganized, irregular wiggle-waggles of the atoms in the wood. So that, therefore, we should look at the thing more closely. As a matter of fact, we have here the clue to the apparent irreversibility. I take a simple example of, for example, if we have blue water, say ink, and white water, that's water without ink, in a tank with a little separation and pull out the separation very delicately, then it starts separate. Blue on one side, white on the other side. Wait a while. Gradually the blue mixes up with the white. And after a while, the water is Luke blue. I mean, it's sort of 50-50 a color uniformly distributed throughout. Now, if we wait for a long time and watch this for a long time, it does not by itself separate. Or you can do something. You can get the blue separated again. You can evaporate the water and condense it somewhere else and collect the blue dye and dissolve it in half the water and put back this thing and so on. While you're doing all that, however, you yourself are causing irreversible phenomena somewhere else. So by itself, it doesn't go the other way. And that gives us some clue. Let's look at the molecule. Suppose that we took a moving picture of the water, of the blue and the white water mixing. It would look funny if we ran it backwards, because we'd start with uniform water and gradually the thing would separate and would be obviously nutty. Now we magnify the picture so that every physicist can watch atom by atom to find out what happened irreversibly, where the laws of balance of forward and backward broke down. And so you start and you look at the picture and you have blue atoms. That's ridiculous, but we'll call it that. We have atoms of one kind and atoms of another kind jiggling all the time in thermal motion, wiggling, bouncing. And if we were to start at the beginning, we would have mostly atoms of one kind on one side and atoms on the other kind on the other side. Now these atoms are jiggling around. It's too small a box. You need more to get this effect. Billions and billions of these atoms. Now these atoms are jiggling around. I just put one more, but I'm getting tired of making the equation. Now these atoms are jiggling around, and if we start all on one side and all on the other, we see, of course, that in their perpetual irregular motions, they'll get mixed up. And that's why it gets to be more or less uniformly blue. But let's watch any one collision. Here's a particular collision selected from that picture. Here's this molecule moving this way and this one moving this way. And they come together, say, in the moving picture, and they bounce off this way. Now you run that section of the film backwards, and you find a pair of molecules moving this way, bouncing off that way. And the physicist looks with his keen eye and measures everything and says, that's all right, that's according to the laws of physics. If two molecules came this way, they would bounce that way. And if they came that way, they would bounce this way. It's reversible according. The laws of molecular collision are reversible. So if you watch too carefully, you can't understand it at all. Because every one of the collisions is absolutely reversible, and yet the whole moving picture shows something absurd, which is that the molecules start in the reverse picture. The molecules start in this condition. Blue, white, and blue, white, and so on, all mixed up. And as time goes on, through all the collisions, the blues separate from the whites. And they can't do that. But that's not natural, that the accidents of life will be such that the blues will separate themselves from the whites. Yet, if you watch this reverse movie very carefully, every collision is okay. Well, you see that all there is to it, that the irreversibility is caused by the general accidents of life. That if you start with a thing that's separated like this and just make irregular changes, it gets more uniform. But if you start with something that's uniform and make irregular changes, it doesn't get separated. It could get separated. It's not against the laws of physics that these things bounce around so that they separate. It's just unlikely. It never happened in a million years. And that's the answer. The things are irreversible only in the sense that going one way is likely to go, but going the other way, although is possible and is according to the laws of physics, wouldn't happen in a million years. It's just ridiculous to expect that if you sit there long enough, the jiggling of the atoms will separate a uniform mixture of ink and water into ink on one side and water on the other. Now, if I had put a box around here so that this was all the molecules that there were, as time went on, they would get mixed up. But if you're patient, I think you could believe that in the perpetual irregular collisions of these molecules, after some time, not necessarily a million years, maybe only a year, when you keep watching, accidentally they get back more or less like this. In the sense, at least, they get back far enough to say that if I drew a line through all the whites on one side and all the blues on the other, it's not impossible. However, the actual objects with which we work have not only 4 or 5 blues and whites, but they have 4 or 5 million atoms. And it's just not likely that 4 or 5 million are all going to get separated like this. And so the apparent irreversibility of nature does not come from the irreversibility of the fundamental physical laws. It comes from the characteristic that if we start with an ordered system and have the irregularities of nature bouncing, then the thing goes one way. Therefore, the next question is, how did it get ordered in the first place? That is to say, why is it possible to start with the ordered? You see, the difficulty is that we start with an ordered thing, we don't end with an ordered thing. One of the rules of the world is that the conditions at the beginning, that the thing goes from an ordered condition to a disorder. Incidentally, this word order and disorder is another one of those terms of physics which aren't exactly the same as it is in ordinary life. The order need not be interesting to you, human beings. It's just a question that there's a definite situation. They're all on one side and all on the other, or they're mixed up. And that's the order to disorder. Maybe you like it better mixed up, but that's not more ordered anyhow. Now, The question is then, how does the thing in the first place get ordered? And why, when we look at any ordinary situation, which is only partly ordered, we can conclude that it probably came from more order. If I look at a tank of water, in which it's very dark blue on this side, and very clear white water here, and sort of bluish water in between, and I know that that thing has been left alone for 20, 30 minutes, then I will guess that it got this way because it was bluer before. For instance, if I find, that the separation was more complete in the past. If I find, for example, two objects, this is a good example of any. If I wait longer, then the blue and white would get more intermixed. And if I know that this thing has been left alone for a sufficiently long time, I can conclude something about the past condition. The fact that it's smooth in here could only arise because it was much better in the past, much more satisfactorily separated. Because if it weren't more satisfactorily separated in the past, in the time since then, it would have gotten more mixed up than it is. So, it is therefore possible to tell from the present something about the past. Although physicists are really not do this much, physicists usually like to think that all you have to do is say, these are the conditions and what happens next. But all our sister sciences have a completely different problem. In fact, all the other things that are studied, history, geology, and astronomical history, all have a problem of this kind. I find they're able to make predictions of a completely different type than a physicist. A physicist says, in this condition, I'll tell you what will happen next. But a geologist will say something like this. I have dug in the ground and I found certain kinds of bones. I predict that if you dig in the ground, you'll find a similar kind of bone. Historian, although he talks about the past, can do it by talking about the future. When he says Napoleon exists, or Napoleon was, or that the French Revolution was in 1783, he means that if you look in another book about the French Revolution, you'll find the same date. 1789, maybe. That's pretty accurate for a physicist to have the third decimal figure. The three figures. Now, the thing that he says is that he makes a kind of prediction about something he has never looked at before. Documents that have still to be found. He predicts that the documents, if there's something written about Napoleon, will coincide with what is written in the other documents. And the question is how that's possible. And the only way that that's possible is to suggest that the past of the world was more organized in this sense than the present. Some people have proposed at one time, the physicists only have proposed this, some physicists, that the way it got ordered was this, that the whole universe is just irregular motions like this. And then if you wait long enough with 5 atoms, of course it can get separated accidentally. And all that has happened is that in the world has been going on and going on and going on and going on and going on, and it fluctuated. That's what this is called. When it gets a little bit out of ordinary, it fluctuated, and now we're watching the fluctuation undo itself again. How do we know that isn't the case? You say, oh, how long you would have to wait? I know, but if it didn't fluctuate far enough to be able to produce evolution, to be able to produce an intelligent person, we wouldn't have noticed it. So we had to keep waiting until we were alive to notice it. So we have to have at least that big a fluctuation. But this is incorrect, I believe. I think that's a ridiculous theory for the following reason. That if the world were much bigger, and there were atoms all over the place, and they started from a completely mixed up condition, all over, and I happen only to look at the atoms here, and I find that the atoms here are separated, I have no way to conclude that the atoms anywhere else are separated. In fact, if the thing were a fluctuation, and I noticed something odd, the most likely way that it got there is that there's nothing odd anywhere else. That is, I have to borrow odds, so to speak, to get this thing lopsided. And there's no use on borrowing too much. It's much more likely, of all the possible ways in which these 6 atoms can be on one side and these 7 on the other side, of all of the possibilities, the most likely condition of the rest of the world is mixed up. And therefore, an astronomer looking at a star that he's never, although when we look at the stars and we look at the world, we see it's ordered. There could be a fluctuation. The prediction would be that if we look at a place that we haven't looked at before, it'll be disordered in a mess. That the separation of the matter into stars which are hot and space which is cold, which we've seen, although if you say it could be a fluctuation, then in places that we haven't looked, we would expect that the stars are not separated from the space. And since every time we make a prediction that in a place that we haven't looked, we'll see the same statement about Napoleon, or we'll see stars in a similar condition, or that we'll see bones like the bones that we've seen before, the success of all those sciences indicate that the world did not come from a fluctuation, but came from a condition which was more separated, more organized in the past than at the present time. And therefore, I think it's necessary that to add to the physical laws the hypothesis that in the past the universe was more ordered in a technical sense, less mixed up, than it is today. And that this statement is the added statement that's needed to make sense and to make an understanding of the irreversibility. That statement, of course, is itself lopsided in time. It says something about the past is different than the future. But it comes outside of the province of what we ordinarily call physical laws, because we try today to distinguish, maybe someday we won't do that, but we do today distinguish between the laws which tell how something moves if you start it in a certain way, and those statements about how the universe got the way it gets, or has been, what it was in the past, and what it's going to get to be. The statement of the physical laws which govern the rules by which the universe develops, and the law which states the condition that the world was in the past. That's considered to be astronomical history. Perhaps someday that will also be a part of physical law. Now, there are a number of interesting features of irreversibility that I think I would like to illustrate. One of them is to see how exactly an irreversible machine really works. Suppose that we build something that we know ought to work only one way. And what I'm going to build is a wheel with a ratchet on it. A ratchet means just this, that we have a notched wheel with steps. So, I've gone the wrong way for what I'm used to thinking about it. No, I had it right. This way, there's another notch, and a sawtooth wheel like this with sharp up notches and relatively slow down notches all the way around. And then, this is a wheel on a shaft. And then on this thing, there's a little piece of pawl, a thing called a pawl, which is on a pivot here, and which is held down by a spring. It gets in the way of the wheel, but that's small technical difficulty. It's just two-dimensional, and actually it's set a little bit below. Now, this wheel can only turn one way. If you try to turn it this way, then these straight-edge part of the teeth get jammed against the pawl, and it doesn't go. Whereas if you turn it the other way, it just goes right over the finger, snap, 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 snap. This they use them in clocks, so when you wind watches, they have this kind of a thing inside so that you only can wind it one way. And after you wind it, it holds the spring. And now we want to discuss, you see, it's completely irreversible in the sense that the wheel can only turn one way. Now this irreversible machine, this wheel that can only turn one way, has been imagined that you could use it for a very useful thing, a very interesting thing. Because of molecular irregularities, because of molecular motion, perpetual motion, there's a perpetual motion of molecules. And if you build a very delicate instrument, it'll always jiggle because it's being bombarded irregularly by the air molecules in the neighborhood. So what's very clever, we'll connect this with a shaft, which is hard to illustrate in 3 dimensions. It goes way out here. We connect this to it with a shaft, with a vein, with a wheel that has 4 veins. Actually, my angles of things have gotten a little bit mixed up. Look down on the shaft. This thing's got 4 veins like this. And those are bombarded. They're in a box of gas here. And they're bombarded all the time by the molecules irregularly. So the thing is pushed sometimes one way, sometimes the other way. But when it's pushed one way, this thing gets jammed. But when it's pushed the other way, it goes around. So we find the wheel perpetually going around, and we have a kind of perpetual motion. That's because this wheel is irreversible. But actually, we have to look into the details. The way this works is that when the wheel goes one way, it lifts the pawl up, and then the pawl snaps down against the next tooth. and it will bounce. If it's perfectly elastic, it'll go bounce, 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 bounce all the time, and the wheel can just go down around the other way when the pole accidentally bounces up. So this will not work unless it's true that when the pole comes down, it sticks, or stops, or bounces and cuts out. If it bounces and cuts out, there must be what we call damping or friction again. And then the falling down and bouncing and stopping, which is the only way this will work one way. Heat is generated by the friction. So this part of the wheel over here will get hotter and hotter. But however, when it begins to get quite warm, something else happens. Just as there's Brownian motion or irregular motions in the gas here, so whatever this is made out of, the parts that this is made out of are getting hotter and are becoming more irregular. So a time comes when this is hot enough that the pole is simply jiggling because of the molecular motions of the things on the inside. And so it bounces up and down on here because of molecular motion, the same thing that was making this vane turn around. And in bouncing up and down on here, it is up as much as it is down. And when it is up as much as it is down, a tooth can go either way. As a matter of fact, the thing will be driven backwards. If this one was hot and this one was cold, the wheel that you thought would go only one way will go the other way. Because in the terrible bouncing up and down of this wheel, every time it comes down on an inclined plane. And so pushes the wheel this way. Then it bounces up again, comes down on another inclined plane, and so on. And so if this side is hotter than this side, it'll go around this way. What's it got to do with the temperature of this side? Suppose I didn't have that at all. Oh. Then, if it's pushed forward by falling on an inclined plane, the next thing will happen is it'll bounce against that tooth, and the wheel will bounce back. But in order to prevent the wheel from bouncing back, we put a damper on it. We put vanes in the air so it can't go back. And then it will go one way, but the wrong way. And so it turns out that no matter how you design it, a wheel like this will go the one way if this side is hotter, and go the other way if this side is hotter. But after there's a heat exchange between the two and everything is calmed down, it will neither go one way or the other. And so that's the technical way in which the phenomena of nature will go one way as long as they're out of equilibrium, as long as one side is quieter than the other, or one side is bluer than the other. The conservation of energy would let us think that we have as much energy as we want. Nature never loses or gains energy. Yet the energy of the sea, for example, the thermal motion of all the atoms in the sea is practically unavailable to us. In order to get that energy organized, herded, used, make it useful, make it available for use, we have to have some place that's at a different temperature. We have to use a difference in temperature, or else we'll find that although the energy is there, we cannot make use of it. There's a great difference between energy and availability of energy. The energy of the sea, for example, is a large amount, but it's not available to us. I think I can give an analogy to give some idea of what the difficulty is this way. The conservation of energy means that the total energy in the world is kept the same. But in the irregular jiggling, that energy can be spread about so uniformly that there's in a certain circumstances, that there's no way to make more go one way than the other. There's no way to control it anymore. I don't know if you've ever had this experience, but I have had going to the beach with many towels and so on, and sitting happily on the beach and having a tremendous downpour suddenly come, picking up the towels as quickly as you can and running into the bathhouse. Then you start to dry yourself, and you find that this towel's a little wet, but it's drier than you are. And you keep drying this one, then you find that one's too wet. It's wetting you as much as it's drying you, and you try another one, and pretty soon you discover a horrible thing. All the towels are damp, and so are you. And then you keep picking them up and putting them down and rearranging them, and there's no way to get any drier, no matter how many towels, you know you have many towels. Because there's no difference, in some sense, between the wetness of the towel and the wetness of yourself. I could invent a kind of a quantity which I could call ease of removing water, or, let's call it the ease of removing water. The towel has the same ease of removing water from it as you have. And so when you touch the towel to you, as much water comes off of you from the towel to you as it goes from you to the towel. It doesn't mean there's the same amount of water in the towel as there is on you. A big towel will have more water in it than a little towel, but they have the same dampness. So when things get to the same dampness, then there's nothing you can do any longer. Now, the water is like the energy because the total amount of water isn't changing. But if we had a world which was limited, see, if the bathhouse door is open and you can run into the sun and get dried out, or find another towel, you see, okay, that's different. Then you got saved. But if you have everything closed and you can't get away from these towels, you can't get any new towels. So if you imagine a part of the world that was closed, wait long enough, and in the accidents of the world, the energy, like the water, will be distributed all over all of the parts evenly. And there's nothing left of one-wayness. There's nothing left of the real interest of the world as we experience it. Thus, in this situation here, which is a limited one, in which nothing else is supposed to be involved, the temperatures gradually become equal on both sides, and the wheels doesn't go around either one way or the other. And in the same way, this situation is that there is, if you leave a system long enough, it gets the energy thoroughly mixed up in it, and no more energy is really available to do anything. Incidentally, the thing that corresponds to the dampness is called the temperature. And although when I say two things at the same temperature, when things get balanced, it doesn't mean they have the same energy in them. It just means it's just as easy to pick energy off of one as to pick it off the other. So if you put them next to each other, nothing apparently happens. They pass energy back and forth. The net result is nothing. So when things have become all at the same temperature, then there's no more energy available to do anything. And the principle of irreversibility is that if things are at a different temperature and are left to themselves, as time goes on, they become more and more at the same temperature. And that the availability of energy is perpetually decreasing. This is another name for what's called the entropy law, which says entropy is always increasing. But never mind the word. To state it the other way, the availability of energy is always decreasing. And that's a characteristic of the world in the sense that it's due to the chaos of molecular irregular motions. Things of different temperature, left to themselves, tend to become of the same temperature, but a piece of, if you have two things at the same temperature, like water on an ordinary stove without a fire, the water isn't going to freeze and the stove get hot. But if you have a hot stove with ice, it goes the other way. So the one-wayedness is always the loss of the availability of energy. Well, that's all I want to say on the subject, but I want to make a few remarks about some characteristics. Here we have an example in which an obvious effect, the irreversibility, is not an obvious consequence of the laws, but that the effect is rather far from the basic laws. It takes a lot of analysis to understand why this effect, and that the effect is of first importance in the economy of the world, in the real behavior of the world, in all obvious things, that my memory, my characteristics, the difference between past and future are completely involved in this, and yet the understanding of it is not prima facie available by knowing about the laws. It takes a lot of analysis. It is often this way, that the laws of physics are different, or the laws of physics do not have a direct relevance, obvious relevance to the experience, but that the laws are abstract from the experience to varying degrees. In this particular case, the fact that the laws are reversible, although the phenomena are not, is an example. There are often great distances between the detail laws, and the main aspects of real phenomena. For example, it's something of this kind, that if you watch a glacier from a distance and you see the big rocks falling into the sea and the way the ice moves and so forth and so on, it isn't really essential to remember that it's made out of little hexagonal ice crystals, that the ice crystals are hexagonal. And yet, the character of the little hexagonal ice crystals, if understood well enough, is in fact the consequence of this is in fact the motion of the glacier. But it takes quite a while to understand. In fact, nobody knows enough about ice, no matter how much they study the crystal yet, to really understand all the behavior of the glacier. But the hope is that if we do understand the ice crystal, we'll ultimately understand the glacier. But there's a large, in fact, although we've been talking in these lectures about the fundamentals of the physical laws, I must say immediately that one does not, by knowing all the fundamental laws as we know them today, immediately obtain an understanding of anything much. It takes a while, and even then it's only partial. Nature, as a matter of fact, seems to be so designed that the most important things in real world seem to be a kind of complicated accidental result of a lot of laws. To give an example, nuclei, which involve several nuclear particles, protons and neutrons, are very complicated. They have what we call energy levels. They can sit in states or conditions of different energy. And various nuclei have various energy levels. And it's a complicated mathematical problem, which we only can partly solve, to find the position of the energy level. Now, it's not, you can understand that it's complicated, and therefore there's no particular mystery about the fact that nitrogen with 15 particles inside happens to have a level at 2.4 million volts, and another level at 7.1, and so on. And the exact position of the levels is obviously a consequence of an enormous complexity. But the remarkable thing about nature is that the whole universe in its character depends upon precisely the position of one particular level in one particular nucleus. In the carbon-12 nucleus, there's a level at 7.82 million volts. It so happens. And that makes all the difference in the world. The situation is the following, that if we start with hydrogen, and it appears that in the beginning or in the earliest times, the world was practically all hydrogen. Then, as the hydrogen comes together under gravity and gets hotter, nuclear reactions can take place and it can form helium. And then the helium can combine only partially with the hydrogen and produce a few more elements, a little heavier, but they disintegrate right away back into helium. So that it was for a while a great mystery about where all the other elements in the world came from, because starting with hydrogen, the cooking processes inside the stars would not make much more than helium and a few others, half a dozen other, less, as a matter of fact, other elements. And faced with this problem, Professor Hoyle said that there is one way out. I think saltpeter also. He's here, so I have to be very careful. If three helium atoms could come together to form carbon, we could easily calculate how often that should happen in a star. And it turned out it should never happen much, except for one possible accident. If there happened to be an energy level at 7.82 million volts in carbon, then the three helium atoms would come together, would stay a little longer than they ought to, on the average, if there were no level there, before they come apart. And staying there a little longer, there's enough time for something else to happen and to make other elements. And if there was a level of 7.82 million volts in carbon, then we could understand where all the other elements in the periodic table come from. And so, by a backhanded, upside-down argument, was predicted that there is in carbon a level at 7.82 million volts, and then experiments in the laboratory with carbon show indeed that there is. And therefore, the existence in the world of all these other elements is very closely related to the fact that there is this particular level in carbon. But the position of this particular level in carbon seems to us, after knowing the physical laws, to be a very complicated accident of 12 complicated particles interacting. So I wish to illustrate by this example that an understanding of the physical laws doesn't give you an understanding in a sense of understanding significance of the world in any way. The details of real experience are very far often from the fundamental laws. There are, in a way of speaking in the world, we have a way of discussing the world which you could call, we discuss it at various hierarchies or levels. Now, I don't mean to be very precise, just as a level is another level and another level, but I will indicate by describing a set of ideas to you, just one after the other, what I mean by hierarchies of ideas. For example, at one end, we have the fundamental laws of physics. Then we invent other terms for concepts which are approximate, who have, we believe, their ultimate explanation in terms of the fundamental laws. For instance, heat. Heat is supposed to be the jiggling, and it's just a word for a hot thing is just a word for a mass of atoms which are jiggling. For all that, fundamentally, we should think of the atoms jiggling. But for a while, if we're talking about heat, we sometimes forget about the atoms jiggling. Just like when we talk about the glacier, we don't always think of the hexagonal ice, the snowflakes, which originally fell. Another example of the same thing is a salt crystal. Looked at fundamentally, a lot of protons, neutrons, and electrons. But we have this concept, salt crystal, which carries a whole pattern already of fundamental interactions, or idea like pressure. Now, if we go higher up from this, in another level, we have properties of substances like refractive index, how light is bent when it goes through something, or surface tension, the fact that the water tends to pull itself together, is described by a number. I remind you that we have to go through several laws down to find out that it's the pull of the atom and so on. But we still say surface tension, and don't worry when we're discussing surface tension of the inner workings, always. Sometimes we do, sometimes we don't. Go on, up in the hierarchy. With the water, we have the waves, and we have a thing like a storm. We have a word for storm, which represents an enormous mass of phenomena. Or sunspot, or star, which is an accumulation of things. And it's not worthwhile always to think of it way back. In fact, we can't, because the higher up we go, we have too many steps in between, each one of which is a little weak, and we haven't thought them all through yet. And we go up in this hierarchy of complexity, we get to things like frog, or nerve impulse, which you see is an enormously complicated thing in the physical world, involving an organization of matter in a very elaborate complexity. And then we go on, we come to things, words, and concepts like man, and history, or political expediency, and so forth, which is a series of concepts that we use to understand things at an ever higher level. And going on, we come to things like evil and beauty and hope. Now, which end is nearer to the ultimate creator, or the ultimate? Or if I make a religious metaphor, which end is nearer to God? Beauty and hope, or the fundamental laws? I think that the right way, of course, is to say that the whole structural interconnections of the thing is the thing that we have to look at, and that the sequence of hierarchy, that all the sciences and all the efforts, not just the sciences, but all the efforts of intellectual kind, are to see the connections of the hierarchies is to connect beauty to history, is to connect history to man's psychology, the man's psychology to the working of the brain to the neural impulse to the chemistry, and so forth, up and down, both ways. And today we cannot, and there's no use making believe we can, draw carefully a line all the way from one end of this thing to the other. In fact, we've just begun to see that there is this relative hierarchy. And so I don't think either end is nearer to God. And it's to stand at either end and to walk out off the end of the pier only, hoping out in that direction is the complete understanding, is a mistake. And to stand with evil and beauty and hope, or to stand with the fundamental laws, hoping that way to get a deep understanding of the whole world with that aspect alone, is a mistake. And it is not sensible either for the ones who specialize at one end and the ones who specialize at the other end to have such disregard for each other. They don't, actually, but the people say they do. So. But that actually the great mass of workers in between, connecting one step to another, are improving all the time our understanding of the world, both from working at the end and working in the middle. And in that way, we are gradually understanding this connection, this tremendous world of interconnecting hierarchies. Thank you.
10, 9, 8, 7, 6, 5, 4, 3.
In the beginning of the history of experimental observation or any other kind of observation on scientific things, it's intuition, which is really based on just experience with everyday objects, that suggests reasonable explanations for things. But as we try to widen and make more consistent our description of what we see, as it gets wider and wider and we see a greater range of phenomena, the explanations become what we call laws instead of simple explanations. But the one important odd characteristic is that they often seem to become more and more unreasonable, more and more intuitively far from obvious. To take an example is the relativity theory, in which, for instance, the proposition is that if you think that two things occur at the same time, that's just a subjective opinion. Someone else could conclude that those two events, one was before the other, and that simultaneity is merely a subjective impression. Now, there's no reason why this should be otherwise, really. The things of the direct everyday experience involve large numbers of particles, or involve things moving very slowly, or involve other conditions that are very special and represent, in fact, a very limited experience with nature. It's a small section only that one gets of natural phenomena from a direct experience. It's only through the refined measurements and careful experimentation that we can get a wider vision. And then we see unexpected things. We see things that are far from what we would guess. We see things that are very far from what we could have imagined. And so our imagination is stretched to the utmost, not as in fiction to imagine things which aren't really there, but our imagination is stretched to the utmost just to comprehend those things which are there. And it's this kind of a situation that I want to talk about tonight. Start, for instance, with the history of light. At first, light was seen to behave, it would appear to behave very much like a rain of particles, of corpuscles, like rain. Bullets from a gun, same idea. Then with further research, it was clear that it was not right, but that light actually behaved like waves, like water waves, for instance. And then in the 20th century, on further research, it appeared that light actually behaved in many ways, again, like particles. In the photoelectric effect, you could count these particles. They're called photons now, and so forth. Again, electrons, when they were first discovered, behaved exactly like particles, bullets, very simple. Further research showed, in electron diffraction experiments and so on, that they behaved like waves. And as time went on, there was a growing confusion in the question of how the things really behave, the waves or particles or waves, but everything looked like both. Now, this growing confusion was resolved in 1925 or 26 with the advent of the correct equations for quantum mechanics. And now we know how the particles, how the electrons and how light behave. But what can I call it? I can say they behave like a particle wave, or they behave in typical quantum mechanical manner. There isn't any word for it. If I say they behave like particles, they give the wrong impression. If I say they behave like waves, they behave in their own inimitable way, which technically could be called the quantum mechanical way. They behave in a way that is like nothing that you have ever seen before. Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different. They do not behave just like particles. They do not behave just like waves. Atoms do not behave like weights hanging on a spring and oscillating, nor do they behave like miniature representations of the solar system with little planets going around in orbits. Nor does it appear to be somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you've seen before. Well, there's one simplification. At least electrons behave exactly the same in this respect as photons. That is, they're both screwy, but in exactly the same way. How they behave, therefore, takes a great deal of imagination to appreciate, because we're going to describe something which is different than anything you know about. This, in that respect at least, makes this perhaps the most difficult lecture of the series, in the sense that it's abstract, in the sense that it is not close to experience. And I cannot avoid that. Were I to give a series of lectures on the character of physical law, and to leave out from this series the description of the actual behavior of particles on a small scale, I would certainly not be doing the job, because this thing is completely characteristic of all of the particles of nature and is a universal character. And it is, if you want to hear about the character of physical law, essential to talk about this particular aspect. So it will be difficult. But the difficulty really is psychological and exists in the perpetual torment that results from your saying to yourself, but how can it be like that? Which really is a reflection of an uncontrolled, but I say utterly vain, desire to see it in terms of some analogy with something familiar. I will not describe it in terms of an analogy with something familiar. I'll simply describe it. There was a time when the newspapers said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, if you appreciate this, and don't take the lecture too seriously, that you really have to understand in terms of some model what I'm going to describe, and just relax and enjoy it, I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing. So that's the way to look at the lectures, not to try to understand. Well, you have to understand in English, of course. But in any sense, in terms of something else, don't keep saying to yourself, if you can possibly avoid it, but how could it be like that? Because you'll get down a drain. You'll get down into a blind alley in which nobody has yet escaped. Nobody knows how it can be like that. So then just let me describe to you the behavior of electrons or of photons in their typical quantum mechanical way. Now, the way I'm going to do this is by a mixture of analogy and contrast. If I made a pure analogy, we would fail. So it must be by analogy and contrast to things that you're familiar with. And so I make it by analogy and contrast first to the behavior of particles, for which I will use bullets, and second to the behavior of waves, for which I will use, say, water waves or sound waves. So we begin first to discuss in a particular, what I'm going to do is I'm going to invent a particular experiment, and first tell how it would behave, what the situation would be in that experiment using particles, what you would expect to happen if the waves were involved, and then what happens when there are actually electrons or photons in the system. And I will just take this one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature 100%. Any other situation in quantum mechanics, it turns out, can always be explained afterwards by saying, you remember the case of the experiment with the two holes? It's the same thing. And so I'm going to tell you about the experiment with the two holes, which is the general mystery, does contain the general mystery. I am avoiding nothing. I am bearing nature in her most elegant and difficult form. So I start with bullets. And all the experiments are going to be in the same general design, so I'll draw it this way. Suppose that we have some source of bullets, which is just represent the source, which we call the source, and is in fact, in the case of bullets, a machine gun. And we have a plate in front here with a hole in it for the bullets to come out of, and this plate, in the case of bullets, is armor plate. Then a long distance from here, we have another plate, which I'm drawing only a short distance because I haven't got room on the blackboard for everything, but this distance is supposed to be much longer in proportion to the width. Please expand that. That's a small point. And it has two holes in it. That's the famous two-hole business. I am going to talk a lot about these holes, so I'll talk about this hole as number one hole and the other hole as number two. And I'm only drawing it in two dimensions. You can, if you wish to imagine these as round holes in three dimensions, but just say this is a cross-section. And then again a long distance away, but we'll draw it relatively short distance because of the limitations of this blackboard. We have another screen here, which is just a backstop of some sort, on which we can put in various places what I will call a detector. And we'll mark that detector. Which in the case of the bullets is a box of sand into which the bullets will be caught, and we can count them. That's the detector for bullets. I don't want to have to redraw the experiment each time, so I'll label everything in this way, and then we'll be able to catch on to situations for different cases. And also, I'm going to do experiments in which I count how many bullets come into this detector or box of sand when the box is here, or here, or here, or here. And to describe that, I'll measure the distance of the box from somewhere down here and call that X. And I talked about what happens when we change X. It means only you move the doggone thing up and down. All right. Now, first, I would like to make a few modifications from real bullets into idealizations. The first is that the machine gun is very shaky and wobbly, and that the bullets go in various directions, not just exactly straight on and bounce back. And they can ricochet off the edges of the holes in these armor plates. And finally, well, let's say, for instance, that the bullets have all the same speed or energy if you want, but that's not very important. But the most important idealization in which it differs from real bullets is I want these bullets to be absolutely indestructible. So that what we find in the box is not pieces of lead of some bullet that's broken half, but we get the whole bullet, please. So imagine indestructible bullets, or hard bullets and soft armor plate or something. And now the first thing that we will notice about bullets is that the things that arrive come in lumps. When the energy comes, it's all in one bulletful of bang. If you count the bullets, there's 1, 2, 3, 4 bullets. The things come in lumps. They're equal in size, we suppose, in this case. And when a thing comes into the box, it's either all in the box or it's not in the box. It comes in lumps. More. If I put up two boxes here, I never get two bullets in the boxes at the same time. Well, if the gun isn't going off too fast and I have enough time between things, you see, slow down the gun so they go off very slowly. Bing, 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 bing. Then put the two things here and look very quickly in the two boxes. You'll never get two bullets at the same time in the two boxes because a bullet is a single, identifiable lump. I call that characteristic of the object that it comes in lumps. So the first thing about bullets is that they come in lumps. And now what I'm going to measure is how many bullets arrive here on the average in a long period of time. So you wait an hour and you count how many bullets are in the can, in the sand, and average that. Now, we call that, if you want, let's say we take a definite time like per hour and say the number of bullets that arrive per hour. And sometimes you could call that what's called the probability of arrival, because it just gives the chance that a bullet going through this thing arrives in this particular box. At least it's proportional to the chance. One way to measure is to measure the average number of bullets that arrive over a period of time. Now, the number of bullets that arrive in this box here will vary as I vary x. And I'm going to make a graph here in which I plot horizontally the number of bullets that I get if I hold this thing here for an hour. And I'll get a curve that will probably look more or less like this. Because when the box is behind one of these holes, it gets a lot of bullets. The ones that went through this hole, and otherwise it gets them that went through this hole. And if it's a little bit out of line, it doesn't get as many. They have to bounce a little off the edges of the hole. And so it disappears like this. And this is the number that we get in an hour when both holes are open. And I call that, by an abbreviation, N12, which merely means the number which arrive when hole number 1 and hole number 2 are both open. Looks like that, say. Now, I must insist that the number that we're plotting here doesn't come in lumps. You can have any size it wants. For example, there can be 2.5 bullets in an hour. In spite of the fact that the bullets come in lumps, what I mean by 2.5 bullets in an hour is that if you run a long time, like 10 hours, you get 25 bullets. So it's on the average 2.5 bullets. The N can have any size. It doesn't have to be in lumps because it's an average. I'm sure you're all familiar with the joke about the fact that the average family in the United States seems to have 2.5 children. It doesn't mean that there's a half a child in any family, whatever. The children come in lumps. But nevertheless, when you take the average number per family, it can be any number whatsoever. And so this number N, which is the number that arrive in this container per hour on the average, need not be an integer. It can be a tenth, which would mean under those circumstances that you have to wait on the average 10 hours, more or less, per bullet. So what we measure then is the probability of arrival, which is a technical measure of the probability of arrival, which is a technical term really for the average number that arrive in a given length of time. And now finally, if we go to analyze this curve N12, we can interpret it very nicely. We can interpret it as a sum of two curves, which I will draw here. You see, that's why I need the blackboard, so I got several cases. So I draw two curves here. One which would represent what I call N1, the number which would come if hole number 2 is closed by another piece of armor plate in front, and so they all come through number 1. And N2 would be the number that come through hole number 2 alone. So N1 is the number that comes through hole number 1 alone, and N2 is the number that comes through hole number 2 alone, those numbers being determined by closing the respective holes. And then we discover a very important law, which is that the number that arrive with both holes open is the number that arrive by coming through number 1 hole plus the number that comes through number 2 hole. And this proposition, the fact that all you have to do is add these two together, I call nice, or no interference. That is, what you get from the two holes open is the same as you get by simply adding each hole separately. That's for bullets. Done. We're done with bullets. All right, I begin again. This time with water waves. Here is standing some kind of a big mass of stuff which is being shaken up and down. This is a long line of barges or jetties with a gap in the water in between. Perhaps it's better to do with ripples than it is to do it with big ocean waves that sound more sensible. Wiggle my finger up and down here, and I have a little piece of wood here, and ripples start out here, and then I've arranged in a tank to put boards in the way here so that I have these two holes. And then I have this so-called detector, and then what I do with the detector, what the detector detects is how much the water is jiggling. For instance, I put a cork in the water and measure how it moves up and down. And what I'm going to measure, in fact, is the energy of the agitation of the cork, which is exactly proportional to the energy carried by the waves. Also, I forgot to say that this jiggling is made very regular and perfect so that the waves are all of the same spacing from one another, and then I'll describe what we get under those circumstances. For that, I first remark, well, let's see. First, we can measure the energy of the cork, but then another thing is important for light, or for water waves, water waves, is that the thing that we're measuring can have any size at all. We're measuring the intensity of the waves or the energy in the cork. And if the waves are very quiet, if the fellow over here is only jiggling a little bit, then there'll be very little motion of the cork, and so on. No matter how much it is, it's proportional. So it can have any size. It doesn't come in lumps. It's not all there or nothing. And what we're going to measure is the intensity of the waves, which, to be precise if you want, is the energy generated by the waves at a point. And now what happens if we measure the intensity, which I'll draw on a third curve here, which I'll call I to remind you it's an intensity and not a number of particles of any kind, and I12, when both holes are open, is a curve that looks something like this. Another an interesting, complicated-looking curve, which ought to be symmetrical. I didn't do too badly, actually. Very complicated-looking curve. That is, if we put the thing in different places, we get a very, very different intensity, which varies very rapidly in a peculiar manner. And you're probably all familiar with the reason for that. The reason is that the ripples, as they come out of here, have crests and troughs spreading from here. And they have crests and troughs spreading from here. Now, if we're at a place which, say, is exactly in between these two things, so that the two waves arrive at the same time, the crests will come on top of each other, and there'll be plenty of jiggling, which is the exact opposite of this curve. So I'll have to put, there should be another bump. We have a lot of jiggling right in dead center. On the other hand, if I were to move to some point here, since I'm further from hole 2 than hole 1, it takes a little longer for the waves to come from 2 than from 1. And when 1 has a crest arriving, the crest hasn't quite reached there yet from 2. In fact, it's a trough from 2. So the water tries to move up and it tries to move down from the influences of the waves coming from the 2 holes. And the net result is it doesn't move at all, or practically not at all. And so we have these low bumps at that place. And then if you move still further over, you get enough delay that when a crest is here, this other crest is in fact one whole wave behind. So in fact, it's a crest that is, 2 crests are coming on top of each other, but not the same crest, so to speak. The 4th crest from here and the 5th crest from there on top. So you get a big one again, and a small one, a big one, small one, depending upon the way the crests and troughs interfere, as we say. The word interference, again, is used in science in a funny way because we'll have what we call constructive interference. When they both interfere here, it makes it stronger. Well, they call it interference anyway, but the very important thing is that I12 is not the same as I1 plus I2, and we say it shows interference. Yes, interference. That's a funny term. We use it. Constructive and destructive interference. I didn't mention what I1 and I2 look like, but we can find out by closing this, for instance, to find I1. The intensity that you get here, if the hole is closed, is simply the wave from one hole for which there's no interference, and that's this curve. N1 is the same as I1, and the same way otherwise I2, and this curve is quite different than the sum of these two. As a matter of fact, the mathematics of this curve is rather an interesting one. What is true is this, that the height of the water when both holes are open is equal to the height that you would get from number 1 open plus the height that you get from number 2 open. Thus, if it's a trough, the height from 2 is negative and cancels out the height from 1. So you can represent it by talking about the height of the water. But it turns out that the intensity in any case, for instance, when both holes are open, is not the same as the height, but is proportional to the square of the height. And it's because of this fact that we're dealing with the squares that we get these very interesting curves. All right. Now, we erase the machinery and start over. This time, we start with electrons. We have a filament here, tungsten plate, holes in a tungsten plate, and for a detector, any electrical system which is sufficiently sensitive to pick up the charge of an electron arriving with whatever energy the source has. Or if you would prefer, we could use photons, and this is a black paper with a hole in it, 2 holes in another sheet of black paper. Paper isn't very good because the fibers don't make a sharp hole, so use something better. And here, for a detector, a photomultiplier that can detect the individual photons arriving. Now, what happens with either case, and I'll discuss only the electron case, the other case is exactly the same, the case with photon, is this. First, that what we receive in this electrical detector with a sufficiently powerful amplifier behind it are clicks. Click, 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 and so on with the source here. Lumps. Absolutely lumps. When the click comes, it's a certain size, and the size is the same. If you turn the source weaker, the clicks come further apart, but it's the same size click. If you turn it up, they go quicker, quicker, and it jams the amplifier. So you have to turn it down enough that there aren't too many clicks for the machinery that you're using to detect. Next, if you will to put up another detector here and listen to both of them, you never get 2 clicks at the same time, at least if the source is weak enough so that, because of the precision with which you measure at the same time. If you cut down the intensity of the source so they come few and far between, they never come a click in both detectors. So that means that the thing which is coming comes in lumps. It has a definite size, and it only comes to one place at a time. All right, so for electrons, or for photons, we'll just use it. It comes in lumps. And therefore, what we can do is the same thing as we did with the bullets. We measure how many come, we measure the probability of arrival. What we do is we hold the detector in a certain place. Actually, if we wanted to, although it's expensive, we could put detectors all over at the same time and make the whole curve simultaneously. But let's suppose we put it in a certain place and we measure at the end of an hour how many electrons came, and we average it. By the way, if I put detectors all along the back here, when one comes, it comes into one, but not from others. It just one goes off, and the other goes off, and this goes off, and that one goes off. Just like with bullets. And we measure then the probability of arrival of the electrons. And what do we get? The number of electrons that arrive. The same kind of an N12 as before. This is what we get for N12. N12 is this is what we get with both holes open. And that's the phenomenon of nature. That she produces the curve, which is the same as you would get from an interference of waves. But she produces a curve for what? Not for the energy in a wave, but for the probability of arrival of one of these lumps. The mathematics is simple. You change I to N, and you have to change H to something else, which is new. You call it something because it's not the height of anything, but in order, this curve has a simple mathematical form. There's an A, which can be represented as an A1 plus an A2, which we call a probability amplitude, because we don't know what it means. Which to arrive from hole 1 plus the probability amplitude to arrive from hole 2, and you add the two together to get the total probability amplitude to arrive and square it. Just direct imitation of what happens with the waves, because we've got to get the same curve out, so we use the same mathematics. Let's find out, I better check on one point, though, about the interference. I forgot to say, what happens if we close one of the holes? Let's try to analyze this interesting curve, which now, for electrons, I erase all the stuff with the light. Well, everything with light is erased. And now we're talking about electrons. This curve isn't important in our case. This is the number which arrives. Now, we would like to analyze this curve. And we try this. We say maybe it comes, we can analyze this by thinking that the electrons come through this hole or through the other. So we can close one hole and measure how many come through hole number 1, and we get that curve. Or we can close this hole and measure how many come through hole number 2, and we get that curve. And these two added together is not this, and so this is not the same as N1 plus N2. And it does show interference. It shows interference. And in fact, the mathematics is given by this funny formula that the probability of arrival is the square of an amplitude, which itself is the sum of two pieces. Now, her question is, how can that come about? That when they go through hole 1, they would be distributed this way. When they go through hole 2, they would be distributed that way. How could it be that when both holes are open, you don't get the sum of the two? Instance. If I hold the detector at this point here, I get practically nothing. If I close one of the holes, I get plenty. If I close the other hole, I get something. If I leave both holes open, I get nothing. If I let them go through both holes, they don't come anymore. Or take the point in the center. You can show that that's higher than the sum, than it was in the other case, than the sum of these two. I get more here when both holes are open than I would get with either one of the two closed. Now, you might think that if you were clever enough, you could argue that they have some way of going around through the holes back and forth, and they do something complicated, or it splits in half and goes through the two holes, and so forth, in order to explain this phenomenon. But nobody, however, has succeeded to get an explanation of this that's satisfactory, because the mathematics in the end is so very simple. The curve is so very simple. I will summarize then by saying that electrons arrive in lumps, like particles. But the probability of arrival of these lumps is determined like the intensity of waves would be. And it is in this sense that the electron behaves, as you might say, sometimes like a particle and sometimes like a wave. It behaves in these two different ways at the same time. And that's all there is to say. I give a mathematical description to figure out the probability of arrival of electrons under any circumstances and so on, and that would, in principle, be the end of the lecture, except that there are a number of subtleties involved in the fact that nature works this way. There's a number of peculiar things. And I would like to discuss those peculiarities because they may not be self-evident at this point. So to discuss the subtleties, we begin by discussing a proposition which we would have thought to use since these things are lumps. Since what comes is always one complete, which I'll call an electron, one complete lump, one complete electron, it's obvious that it's reasonable that either an electron arrives or goes, let's say, that either an electron goes through hole number 1 or it goes through hole number 2. That seems like it goes through hole number 2. That seems very obvious that it can't do anything else if it's a lump. And I'm going to discuss this proposition, so I have to give it a name. I'll call it Proposition A. Now, we've already discussed a little bit what happens with Proposition A. If it were true that an electron either goes through hole number 1 or it goes through hole number 2, then the total number which arrive here would have to be analyzable as a sum of two contributions. The total number which arrive here will be the number that come here via hole 1 plus the number that come via hole 2. And since this curve cannot easily be analyzed as a sum of two pieces in such a nice manner, and since the experiments which determine how many would have arrived, if only hole number 1 were open, don't give the result that this number is the sum of these two, it is obvious that we should conclude that this proposition is false. It is not true that the electron either comes through hole number 1 or hole number 2. Maybe it divides itself in half temporarily and so on. So Proposition A is false. That's logic. Unfortunately, or otherwise, we can test logic by experiment. And so we just have to do to find out whether it's true or not that the electrons come through hole 1 and hole 2, or maybe they go around through both holes or they split up and so on. All we have to do is watch them. Watch them, we need light. So we put back here behind the holes a source of light. It's very intense light. Light is scattered by electrons, it is bounced off electrons. And in other words, you can see electrons if they go by if the light's strong enough. So we stand back here and we look to see whether we see, when the electron is counted here, a flash, or have seen the moment before the electron's counted here, a flash behind hole 1 or a flash behind hole 2, or maybe a sort of a half flash in each place at the same time. Because we're going to find out now how it goes by looking. Well, you turn on the light and look. And lo, you discover that you see flashes behind either one hole or the other hole every time you get a count here. Every time there's a count here, you see a flash behind number 1 or behind number 2. What you see is that the electron comes 100% complete through hole 1 or through hole 2. When you look, kind of a paradox. Well, let's squeeze nature into some kind of a difficulty here. I show you what we're going to do, see? We're going to keep the light on. We're going to watch. And we're going to count how many electrons come through. And we're going to make 2 columns. I'll watch the holes very carefully while you please count how many are arriving in the detector. All right, you say, one arrived. I said, I saw that when it went through hole number 1. So we put here 2 columns, which is column 1 for number 1 hole and number 2 hole. And every time you get one, you tell me you got one. I have seen it, of course. And I say either number 1 or 2. The first one was 1. What's the next one? Number 2. All right. Number 2. Number 2. Number 1. So as we watch the electrons, as I watch the electrons, for every one that you count, I can separate them experimentally into 2 columns. Them are what have arrived via hole 1, and those, I know the English is right, I'm just trying to, that arrived via hole 2. So the total number that arrived, well, first, what does this column look like when you add it all together for different positions here, which is just the number that is supposed to have come through 1. I watch behind 1, and what do I see? I see this curve. That number column is distributed this way. Just like we thought when we closed hole 2. It works the same way whether we're looking or not. If we close hole 2, we get the same distribution in those that arrive as if we are watching. And likewise, the number in this column that is supposed to have arrived via hole number 2 is also this simple curve. Now look, the total number which arrived has to be the total number. I'm just counting little marks. It has to be the sum of this number plus that number. The total number which arrived absolutely has to be the sum of these 2. It has to be distributed this way. But I said it was distributed this way. It's distributed this way. It really is, of course it has to be. It is. It's distributed this way. If then we mark with a prime the results when a light is lit, prime means with a light lit, then we find N1 prime is practically the same as N1 without the light, and N2 prime is almost the same as N2. But the number that we see when the light is on is equal to the number that we see through 1 plus the number that we see through 2. This is the result that we get when the light is on. In other words, we get a different answer whether I turned on the light or not. If I have the light turned on, this is the distribution which you measure over here. If I turn off the light, this is the distribution that you measure over here. Turn on the light, this is the answer. Turn off the light, that's the answer. See, light just squeezed out. Now, we could say then that the light affects the result. If the light is on, you get a different answer than if the light is off. If you want to, you can say the light affects. It does affect. In fact, we found this by this experiment. We get a difference with the light on and off. Light affects the behavior of electrons. If you want to talk about the motion of the electrons through here, which is a little inaccurate, you can say that the light affects the motion, so that those which might have arrived at the maximum are somehow been deviated or kicked by the light and arrive at the minimum instead, so smoothing the curve to produce this thing. You see, electrons are very delicate. Although when you're looking at a baseball and you shine light on it, it doesn't make any difference. The baseball goes the same way. Electrons are very flimsy, very delicate. And when you shine a light on them, a little tough on the electron, it knocks them about a bit. And instead of doing that, they do this because you turn the light on so strong. You hit them with a hammer. It's not just a delicate thing like when you're looking at a baseball with light. They are hit them with a hammer. But you turn up the light too strong. Turn it weaker and weaker and weaker until it's very dim. Then use very careful detector that can see very dim light. And look with the dim light. Now, as the light gets dimmer and dimmer, you can't expect with very, very, very weak light to affect the electron so completely as to change the pattern 100% from this pattern to this pattern. As the light gets weaker and weaker and weaker, somehow it should get more and more like no light at all. And how then does this turn into that? Well, it turns out that light is not like a wave of water, but light also comes in particle-like character called photons. And as you turn down the intensity of the light, You're not turning down the effect, you're turning down the number of photon particle-like things that are coming out of the source. So as I turn down the light, I'm getting fewer and fewer photons. The least I can scatter from an electron is 1 photon, and if I have too few photons, well, sometimes the electron will get through, and it just happened there wasn't enough light. There was no photon coming by. I didn't see it. So a very weak light doesn't mean a small disturbance. It just means a few photons. And what happens is that I have to invent a third column. You see, you get a click over here. I say, I saw that one. That was in number 1 hole. This was behind hole number 2. Then another comes out. Sorry, I didn't see that. There wasn't enough light to give a photon at that time, so there must be a third column under didn't see. And when the light is very strong, there are very few in there. When the light is very weak, most of them end in there. So that there are 3 columns, this one, and sometimes in here. Now, you can guess what happens. The ones I do see are distributed this way. The ones I didn't see are distributed that way. And as I turn the light weaker and weaker, well, I see less and less of them. A greater and greater fraction are not seen. And the actual curve, in any case, is a sum of a mixture of this and this. And as the light gets weaker, so that fewer and fewer are seen, it gets more and more like that in a continuous fashion. So, in this case, if the electrons are not seen and nothing bounced off the light under those circumstances, you get this complicated pattern for those electrons which were not seen. The ones in the column didn't see are exactly distributed in this complicated way, and the other 2 columns are in these 2 ways here. Now, you say, I got another way to measure which hole it goes through. And I'm sorry I haven't got enough time to discuss a large number of different inventions that you might have to find out which hole the electron went through and what happens in each case. It always turns out, however, that it's impossible to arrange the light in any way so that you can tell through which hole the thing is going without disturbing the pattern of arrival of the electrons from this form to this form, without destroying the interference. And not only light, but anything else. You use neutrinos, you use anything. There's a principle that's impossible to do it. You can, if you want, invent a way to tell which hole the electron's going through. Then it turns out it's going through one or the other. But if you try to make that instrument so that at the same time it doesn't disturb the motion of the electron, then what happens is you get back, you can't tell anymore which one it goes through, and you get this. If you can tell, you get this. Heisenberg noticed when he discovered the laws of quantum mechanics that the new laws of nature that he discovered could only be consistent if there was some basic limitation to our experimental abilities that had not been previously recognized. In other words, you can't experimentally be as delicate as you wish. And he proposed his uncertainty principle, which stated in terms of our experiment is the following. He stated it another way, but they're exactly equivalent. You can get from one to the other, but unfortunately I haven't time to explain that. But in our experiment, his uncertainty principle would be stated in this manner. It is impossible to design any apparatus whatsoever to determine which hole the electron passes, and when one succeeds in determining which hole the electron passes, which can determine through which hole the electron passes. That will not at the same time disturb the electron enough to destroy the interference pattern. And no one has found a way around this. And I'm sure you're all itching with inventions as to methods of detecting which hole the electron went through. But if each one of them is analyzed carefully, you'll find out there's something the matter with it, and that if, without disturbing the electron, you'd think you could do it. But it turns out there's always something the matter, and you can account for the difference in the patterns due to the disturbance of the instruments used to determine through which hole the electron comes. Now, this, therefore, is a basic characteristic of nature and tells us something about everything. If a new particle is found tomorrow, the kaon, actually it's already been found, something, give it a name, let's say a kaon. And I used kaons to interact with electrons to determine which hole the electron is going through. I already know ahead of time, I hope, enough about the behavior of the kaon to say that it cannot be of such a type that I could tell through which hole the electron would go without at the same time producing a disturbance on the electron that changed the pattern from here to here. So that the uncertainty principle is used as a general principle to guess ahead at many of the characteristics of unknown objects. They are limited in their character. Well then, Let's go back. What about this proposition A? Does it go either through one hole or the other? Or not? Well, physicists have a convention, a way of avoiding the pitfalls which exist, and they make their game, their rules of thinking as follows. That if you have an apparatus which is capable of telling which hole the electron goes through, and you can have such apparati, then one can say that it either goes through one hole or the other. And it does. When you look, it always is going through one hole or the other. When you look. But when you do not try to determine, or you have no disturbance, no apparatus there to determine through which hole the thing goes, under those circumstances, you cannot say that it either goes through one hole or the other. You can always say it, provided you stop thinking immediately and don't make any deduction from it. We prefer not to say it, rather than to stop thinking at the moment. In other words, when we don't look, we can't say through which hole it's going, but if you try to look to see, you find it always goes through one hole or the other. Still, to conclude that it goes either through one hole or the other when you're not looking is to produce an error in prediction. And that is the logical tightrope on which we have to walk if we wish to interpret nature. This proposition that I'm talking about is more general. It's not just for two holes. It's a general proposition reads something like this, that the probability of any event in an ideal experiment, that just means that when everything is specified as well as it can be, the probability of an event is the square of something, which I call A here, is called the probability amplitude. And when an event can occur in several alternative ways, the probability amplitude, this A number, is the sum of the A's for each of the various alternatives. And finally, if an experiment is performed which is capable of determining which alternative is taken, the probability of the event is the sum of the probabilities for each alternative. That is, you lose the interference. Now, the question is, how does it really work? What machinery is actually producing this thing? Well, nobody knows any machinery. Nobody can give you a deeper explanation of this phenomenon than I have given. That is a description of it. They can give you a wider explanation in the sense that they can do more examples to show how it's impossible to tell which hole it goes through and at the same time not destroy the interference pattern. They can give a wider class of experiments than just the two-slit interference experiment and so on, but it's just repeating the same thing to drive it in. It's not any deeper, it's only wider. The mathematics can be made more precise. You can mention that they're complex numbers instead of real numbers and a couple of other minor points which have nothing to do with the main idea. And the deep mystery is what I described. And no one can go any deeper today, but only wider. Now, I mentioned probabilities in this calculation. What we're calculating here, this curve, is the probability of arrival of an electron. The question is there any way to determine where it really arrives? We are not averse to using the theory of probability, that is calculating odds, when a situation is very complicated. You throw up a die and it spins so many times in the air with the various resistors and atoms and all this complicated business that we're perfectly willing to allow that we don't know enough details, and so we calculate the odds that the thing will come this way or that way. But here, what we're proposing, is it not, is that there be probability all the way back at the fundamental laws. That in the fundamental laws of physics, there are odds. For example, suppose that I have an experiment so set up that with the light out, I get this interference situation and know that. Then I say that with the light on, I can't predict through which hole it will go. I only know that each time I look, it'll be one hole or the other. But there is no way to predict ahead of time through which hole it goes. The future, in other words, is unpredictable. It is impossible to predict in any way from any information ahead of time through which the thing will go, or which hole it will be seen behind. That means that physics is kind of given up, if the original purpose was, and everybody thought it was, to know enough that in given the situation, you can predict what's going to happen next. Given the circumstances, you can predict what happened. Here are the circumstances. Source, strong light source, tell me which hole, behind which hole will I see the electron? You say, well, The reason you can't tell through which hole you're going to see the electron is it's determined by some very complicated things back here. If I knew enough about that electron, it has internal wheels, internal gears, and so forth, that this is what determines through which hole it goes. So it's 50-50 probability because, like a die, it's set sort of at random. And that if I were to have studied it carefully enough, your physics is incomplete. If you get a complete enough physics, then you'll be able to predict through which hole it goes. That's the hidden variable theory, so-called. Well, that's not possible. It is not due to a lack of detailed knowledge that we cannot make the prediction, because I said that if I didn't turn on the light, I should get this interference pattern. If I have a circumstance in which I get that interference pattern, then it is impossible to analyze it in terms of saying it goes through here or here, because that curve is so simple, mathematically a different thing than the contribution of this and this as probability. So if it were possible for you to have determined through which hole it was going to go if I had the light on, the fact that I have the light on hasn't got anything to do with it. Whatever gears there are back here that you observed, which permitted you to tell me whether it was going to go through one or two, you could have observed if I had the light off. And therefore you could have told me with the light off which hole, each time an electron goes, which hole it's going to go through. But if you can do this, then that curve would have to be represented as the sum of those that go through there and those that go through there, and it ain't. And therefore, it's impossible to have any information ahead of time as to which hole it's going to go through when the light is out, or when the light is on, or out, in a circumstance where the experiment is set up that can produce this interference. So it is not a lack of unknown gears, a lack of internal complications that makes nature have probability in it. It seems to be, in some sense, intrinsic. Someone has said it this way: nature herself doesn't know which way the electron is going to go. A philosopher once said, "It is necessary for the very existence of science that the same conditions always produce the same result." Well, they don't. If you set up the electrons in any way, you set up the circumstance here in the same conditions every time, and you cannot predict behind which hole you'll see the electron. They don't, and yet the science goes on in spite of it, although the same conditions don't produce the same results. That makes us unhappy that we can't predict exactly what will happen. Incidentally, you can make a circumstance which is very dangerous and serious, and man must know, and still can't predict. For instance, we could cook up, or rather not, but we could cook up a scheme by which we arrange photocells so that if it sees the electron, one electron is going to go through. If we see it behind hole number 1, we set off the atomic bomb and start World War III. If we go see it behind hole 2, we have just to make peace feelers and delay the war a little longer. Then the thing is that the future of man would then be dependent upon something which no amount of science can predict. So the future is unpredictable. What is necessary for the very existence of science and so forth, and what the characteristics of nature are not to be determined by pompous preconditions. They are determined always by the material with which we work, by nature herself. We look and we see what we find, and we cannot say ahead of time successfully what it's going to look like. The most reasonable possibilities turn out often not to be the situation. What is necessary for the very existence of science is just the ability to experiment, the honesty in reporting results. The results must be reported without somebody saying what they'd like the results to have had been. And finally, an important thing is the intelligence to interpret the results, but important point about this intelligence is that it should not be sure ahead of time about what must be. Now, it can be prejudiced and say that's very unlikely. I don't like that. Prejudice is different than absolute certainty. I don't mean absolute prejudice, just bias. But not strict bias, see, not complete prejudice. As long as you're biased, it doesn't make any difference, because if the fact is true, there will be a perpetual accumulation of experiments that perpetually annoy you until they cannot be disregarded any longer. Only can be disregarded if you're absolutely sure ahead of time of some precondition that science has to have. In fact, it is necessary for the very existence of science that minds exist which do not allow that nature must satisfy some preconceived conditions like those of our philosophy. What I want to talk to you about tonight is, strictly speaking, not on the character of physical laws, because one might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing it. Someone suggested that it would be ideal if, as I went along, I would slowly explain how to guess the laws and then create a new law for you right as I went along. I don't know whether I'll be able to do that. But first, I want to tell about what the present situation is, what it is that we know about the physics. You think that I've told you everything already, because in all the lectures I told you all the great principles that are known. But the principles must be principles about something. The principles that I just spoke of, the conservation of energy, is the energy of something. And quantum mechanical laws are quantum mechanical principles about something. And all these principles added together still doesn't tell us what the content is of the nature. That is what we're talking about. So I will tell you a little bit about the stuff on which all these principles are supposed to have been working. First of all is matter, and remarkably enough, all matter is the same. The matter of which the stars are made is known to be the same as the matter on the earth by the character of the light that's emitted by those stars. They give a kind of fingerprint by which you can tell that's the same kind of atoms in the stars as on the earth. The same kind of atoms appear to be in living creatures as in non-living creatures. Frogs are made out of the same goop in different arrangement than rocks. So that makes our problem simpler. We have nothing but atoms, all the same everywhere. And the atoms all seem to be made from the same general constitution. They have a nucleus, and around the nucleus there are electrons. So I begin to list the parts of the world that we think we know about. One of them is electrons, which are the particles on the outside of the atoms. Then there are the nuclei, but those are understood today as being themselves made up of two other things, which are called neutrons and protons, two particles. Incidentally, we have to see the stars and see the atoms, and they emit light, and the light is described by particles themselves, which are called photons. And at the beginning, we spoke about gravitation, and if the quantum theory is right, then the gravitation should have some kind of waves which behave like particles too, and they call those gravitons. If you don't believe in that, just read gravity here, the same. Now, finally, I did mention that in what's called beta decay, in which a neutron can disintegrate into a proton and an electron and a neutrino, or alien antineutrino, there's another particle here, a neutrino. In addition to all the particles that I'm listing, there are, of course, all the antiparticles, but that's just a quick statement and takes care of doubling the number of particles immediately. But there's no complications. Now, with the particles that I've listed here, all of the low-energy phenomena, all of, in fact, ordinary phenomena that happen everywhere in the universe as far as we know, with the exception of here and there some very high-energy particle does something, or in the laboratory we've been able to do some peculiar things, but if we leave out those special cases, all ordinary phenomena are presumably explained by the action and the motions of these things, these kind of things. For example, life itself is supposedly made understandable in principle from the action of movements of atoms, and those atoms are made out of neutrons, protons, and electrons. I must immediately say that when we say we understand it in principle, I only mean that we think we would, if we could figure everything out, find that there's nothing new in physics to be discovered in order to understand the phenomena of light. Or, for instance, for the fact that the stars emit energy, solar energy, or stellar energy, is presumably also understood in terms of nuclear reactions among these particles and so on. And all kinds of details of the way atoms behave are accurately described in with this kind of model, at least as far as we know at present. In fact, I can say that in this range of phenomena today, as far as I know, there are no phenomena that we are sure cannot be explained this way, or even that there's deep mystery about. This wasn't always possible. There was, for instance, for a while, a phenomenon called superconductivity. There still is the phenomenon, which is that metals conduct electricity without resistance at low temperatures, and it was not at first obvious that this was a consequence of the known laws with these particles, but it turns out that it has been thought through carefully enough, and it's seen, in fact, to be a consequence of known laws. There are other phenomena, such as extrasensory perception, which cannot be explained by this known knowledge of physics here, and it is interesting, however, that phenomenon has not been well established, and that we cannot guarantee that it's there. So if it could be demonstrated, of course, that would prove that the physics is incomplete, and therefore it's extremely interesting to physicists, whether it's right or wrong, and many, many experiments exist which show it doesn't work. The same goes for astrological influences. If it were true that the stars could affect the day that it was good to go to the dentist, then, as in America we have that kind of astrology, then it would be wrong. The physics theory would be wrong, because there's no mechanism understandable in principle from these things that would make it go. And that's the reason that there's some skepticism among scientists with regard to those ideas. On the other hand, in the case of hypnotism, at first it looked like that also would be impossible when it was described incompletely, but now that it's known better, it is realized that it is not absolutely impossible that hypnosis could occur through normal physiological but unknown processes. It doesn't require some special new kind of force. Now, today, although the knowledge of the theory of what goes on outside the nucleus of the atom seems precise and complete enough, in the sense that, given enough time, we can calculate anything as accurately as it can be measured. It turns out that the forces between neutrons and protons, which constitute the nucleus, are not so completely known and are not understood at all well. And that's what I mean by that, is that we cannot today, we do not today understand the forces between neutrons and protons to the extent that if you wanted me to and gave me enough time and computers, I could calculate exactly the energy levels of carbon or something like that, because we don't know enough about that, although we can do the corresponding thing for the energy levels of the outside electrons of the atom. We cannot for the nuclei. So the nuclear forces are still not understood very well. Now, in order to find out more about that, experimenters have gone on, and they have to study phenomena at very high energy, where they hit neutrons and protons together at very high energy and produce peculiar things. And by studying those peculiar things, we hope to understand better the forces between neutron and proton. Well, a Pandora's box has been opened by these experiments, although all we really wanted was to get a better idea of the forces between neutrons and protons. When we hit these things together hard, we discover that there are more particles in the world. And as a matter of fact, in this column, there was plus over 4 dozen other particles have been dredged up in an attempt to understand these. And these 4 dozen other are put in this column because they're very relevant to the neutron-proton problem. They interact very much with neutrons and protons, and they got something to do with the force between neutrons and protons. So we've got a little bit too much. In addition to that, while the dredge was digging up all this mud over here, it picked up a couple of pieces that are not wanted and are irrelevant to the problem of nuclear forces. One of them is called a mu meson or muon, and the other was a neutrino, which goes with it. There are 2 kinds of neutrinos, one which goes with the electron and one which goes with the mu meson. Incidentally, most amazingly, all the laws of the muon and its neutrino are now known as far as we can tell experimentally. The law is they behave precisely the same as the electron and its neutrino, except that the mass of the mu meson is 207 times heavier than an electron, and that's the only difference known between those objects. But it's rather curious, but I can't say any more because nobody knows any more. Now, 4 dozen other particles is a frightening array, plus the antiparticles, is a frightening array of things, but it turns out they have various names: mesons, pions, kaons, lambda, sigma. It doesn't make a difference. With 4 dozen particles, there are going to be a lot of names. But it turns out that these particles come in families, so it helps us a little bit. Actually, some of these so-called particles last such a short time that there are debates whether it's in fact possible to define their very existence, whether there's a particle or not, but I won't enter into that debate. In order to illustrate the family idea, I take the 2 cases of a neutron and a proton. The neutron and proton have the same mass within 0.1% or so. One is 1836, the other is 1839 times as heavy as an electron, roughly. I remember the numbers very. But the thing that's very remarkable is this, that for the nuclear forces, which are the strong forces inside the nucleus, the force between a pair of protons, 2 protons, is the same as between a proton and a neutron, and is the same again between a neutron and a neutron. In other words, for the strong nuclear forces, you can't tell a proton from a neutron. Or a symmetry law. Neutrons may be substituted for protons without changing anything, provided you're only talking about the strong forces. If you're talking about electrical forces, oh no. If you change a neutron for a proton, you have terrible difference, because the proton carries electrical charge and a neutron doesn't. So by electrical measurement, immediately you can see the difference between a proton and a neutron. So this symmetry, that you can replace neutrons by protons, is what we call an approximate symmetry. It's right for the strong interactions of nuclear forces. But it's not right in some deep sense in nature because it doesn't work for the electricity. This is called a partial symmetry, and we have to struggle with these partial symmetries. Now, the families have been extended. It turns out that the substitution neutron-proton can be extended to substitution over a wider range of particles, but the accuracy is still lower. You see, that neutrons can always be substituted for protons is only approximate. It's not true for electricity. And that the wider substitutions that have been discovered are legitimate is still more poor, a very poor symmetry, not very accurate. But they have helped to gather the particles into families and thus to locate places where particles are missing and to help to discover the new ones. This kind of game of roughly guessing at family relationships and so on is illustrative of the kind of preliminary sparring which one does with nature before really discovering some deep and fundamental law. before you get to deeper discoveries. Examples are very important in the previous history of science. For instance, Mendeleev's discovery of the periodic table for the elements is analogous to this game. It is the first step, but the complete description of the reason for the periodic table came much later with atomic theory. In the same way, organization of the knowledge of nuclear levels and characteristics was made by Maria Mayer and Jensen in what they call the shell model of nuclei some years ago, and it's an analogous game in which a reduction of the complexity is made by some approximate guesses. And that's the way it stands today. In addition to these things, then we have all these principles that we were talking about before. Principle of relativity, that things must behave quantum mechanically, and combining that with the relativity, that all conservation laws must be local. And so we put all these principles together, we discover there are too many. They're inconsistent with each other. It seems as if we add quantum mechanics plus relativity plus the proposition that everything has to be local, plus a number of tacit assumptions which we can't really find out because we're prejudiced. We don't see what they are, and it's hard to say what they are. Adding it all together, we get inconsistency because we really get infinity for various things when we calculate them. Well, if we get infinity, how will we ever agree that this agrees with nature? It turns out that it's possible to sweep the infinities under the rug by a certain crude skill, and temporarily we're able to keep on calculating. But the fact of the matter is that all the principles that I told you up till now, if put together, plus some tacit assumptions that we don't know, gives trouble. They cannot mutually consistent. Nice problem. Example of the tacit assumptions that we don't know what the significance is, such propositions as the following. If you calculate the chance for every possibility, there's 50% probability this will happen, 25% that'll happen, it should add up to 1. We think that if you add all alternatives, you should get 100% probability. That seems reasonable, but reasonable things are where the trouble always is. Another proposition is that the energy of something must always be positive. It can't be negative. Another proposition that is probably added in order before we get inconsistency is what's called causality, which is something like the idea that effects cannot precede their causes. Actually, no one has made a model in which you disregard the proposition about the probability or you disregard the causality, which is also consistent with quantum mechanics, relativity, locality, and so on. So we really do not know exactly what it is we're assuming that gives us the difficulty producing infinities. Okay, now that's the present situation. Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature. Or we say compared to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it. It's true, however, that one has to check a little bit to make sure that it's wrong, because someone who did the experiment may have reported incorrectly, or there may have been some feature in the experiment that wasn't noticed, like some kind of dirt and so on. That's an obvious check. Furthermore, the man who computed the consequences, even if it may have been the same one who made the guesses, may have made some mistake in the analysis. Those are obvious remarks. So when I say if it disagrees with the experiment, it's wrong, I mean after the experiment has been checked, the calculations have been checked, and the thing has been rubbed back and forth a few times to make sure that the consequences are logical consequences from the guess, and that in fact it disagrees with a very carefully checked experiment. This will give you somewhat a wrong impression of science. It means that we keep on guessing possibilities and comparing it to experiments, and this is to put an experiment on a little bit weak position. It turns out that the experimenters have a certain individual character. They like to do experiments even if nobody's guessed yet. So it's very often true that experiments in a region in which people know the theorist doesn't know anything, nobody's guessed yet. For instance, we may have guessed all these laws, but we don't know whether they really work at very high energy because it's just a good guess that they work at high energy. So experiment said, let's try higher energy. And therefore, experiment produces trouble every once in a while. That is, it produces a discovery that one of the things that we thought of is wrong. So what I would say, experiment can produce unexpected results, and that starts us guessing again. For instance, an unexpected result is the mu meson and its neutrino, which was not guessed at by anybody whatever before it was discovered, and still nobody has any method of guessing by which this is a natural thing. Now, you see, of course, that with this method, we can disprove any definite theory. You have a definite theory, a real guess from which you can really compute consequences which could be compared to experiment, and in principle, we can get rid of any theory. You can always prove any definite theory wrong. Notice, however, we never prove it right. Suppose that you invent a good guess, calculate the consequences, and discover that every consequence that you calculate agrees with experiment. The theory is then right? No, it is simply not proved wrong. Because in the future, there could be a wider range of experiments, you can compute a wider range of consequences, and you may discover then that the thing is wrong. That's why laws like Newton's laws for the motion of planets last such a long time. He guessed the law of gravitation, calculated all the kinds of consequences for the solar system and so on, compared them to experiment, and it took several hundred years before the slight error of the motion of Mercury was developed. During all that time, the theory had been failed to be proved wrong and could be taken to be temporarily right, but it can never be proved right because tomorrow's experiment may succeed in proving what you thought was right wrong. So we never are right. We can only be sure we're wrong. However, it's rather remarkable that we can last so long. I mean, have some idea which will last so long. Incidentally, some people, one of the ways of stopping the science would be to only do experiments in the region where you know the laws. But the experimenters search most diligently and with the greatest effort in exactly those places where it seems most likely that we can prove the theory is wrong. In other words, we're trying to prove ourselves wrong as quickly as possible, because only in that way do we find progress. For example, today, among the ordinary low-energy phenomena, we don't know where to look for trouble. We think everything's all right. And so there isn't any particular big program looking for trouble in nuclear reactions or in superconductivity. I must say I'm concentrating on discovering fundamental laws. There's a whole range of physics which is interesting in understanding at another level these phenomena like superconductivity and nuclear reactions. But I'm talking about discovering trouble, something wrong with the fundamental law. So nobody knows where to look there. Therefore, all the experiments today are in this field of finding out the new law are at high energy. I must also point out to you that you cannot prove a vague theory wrong. If the guess that you make is poorly expressed and rather vague, and the method that you use for figuring out the consequences is rather a little vague, you're not sure, I mean, you say, I think everything's because it's all due to Muggles, and Muggles do this and that more or less, so I can sort of explain how this works. Then you see that that theory is good because it can't be proved wrong. If the process of computing the consequences is indefinite, then with a little skill, any experimental result can be made to look like an expected consequence. You're probably familiar with that in other fields. For example, A hates his mother. The reason is, of course, because she didn't caress him or love him enough when he was a child. Actually, if you investigate, you find out that, as a matter of fact, she did love him very much, and everything was all right. Well, then, it's because she was overindulgent when he was young. So by having a vague theory, it's possible to get either result. Oh, wait. Now, the cure for this one is the following. It would be possible to say, if it were possible to state ahead of time how much love is not enough and how much love is overindulgent exactly, and then there would be a perfectly legitimate theory against which you can make tests. It is usually said when this is pointed out, how much love is and so on, oh, you're dealing with psychological matters and things can't be defined so precisely. Yes, but then you can't claim to know anything about it. Now, we have examples you'll be horrified to hear in physics of exactly the same kind. we have these approximate symmetries. Works something like this. You have approximate symmetry, you suppose it perfect. Calculate the consequence. Easy if you suppose it perfect. You compare with experiment. Of course, it doesn't agree. Of course. The symmetry you're supposed to expect is approximate. So if the agreement is pretty good, you say nice. If the agreement is very poor, you say, well, this particular thing must be especially sensitive to the failure of the symmetry. Now, you laugh, but we have to make progress in that way. In the beginning, when the subject is first new, and these particles are new to us, this jockeying around, this is a feeling way of guessing at the result. And this is the beginning of any science. And the same thing is true of psychology as it is of the symmetry propositions in the physics. So don't laugh too hard. It's necessary in the very beginning to be very careful. It's easy to fall over the deep end by this kind of vague theory. It's hard to prove it wrong. It takes a certain skill and experience to not walk off the plank on the game. In this process of guessing, computing consequences, and comparing to experiment, we can get stuck at various stages. For example, we may, in the guess stage, get stuck. We have no ideas. We can't guess an idea. Or we may get in the computing stage stuck. For example, Yukawa guessed an idea for the nuclear forces in 1934. Nobody could compute the consequences because the mathematics was too difficult. So therefore, they couldn't compare it with experiments successfully, and the theory has remained for a long time until we discovered all this junk. And this junk was not contemplated by Yukawa, and therefore, it's undoubtedly not as simple, at least, as the way Yukawa did it. Another place you can get stuck is at the experimental end. For example, the quantum theory of gravitation is going very slowly, if at all, because there's no use. All the experiments that you can do never involve quantum mechanics and gravitation at the same time because the gravity force is so weak compared to electrical forces. Now, I want to concentrate from now on, because I'm a theoretical physicist, I'm more delighted with this end of the problem, as to what goes, how do you make the guesses. Now, it's strictly, as I said before, not of any importance where the guess comes from. It's only important that it should agree with experiment, and that it should be definite as definite as possible. What you say then is very simple. We've set up a machine, a great computing machine, which has a random wheel in it that makes a succession of guesses. And each time it guesses a hypothesis about how nature should work, computes immediately the consequences and makes a comparison to a list of experimental results that it has at the other end. In other words, guessing is a dumb man's job. Actually, it's quite the opposite, and I will try to explain why. The first problem is how to start. You see, I'll start with all the known principles. But the principles that are all known are inconsistent with each other. So something has to be removed. So we get a lot of letters from people. We're always getting letters from people who are insisting that we ought to make holes in our guesses as follows. You see, you make a hole to make room for a new guess. Somebody says to you, people always say space is continuous, but how do you know when you get to a small enough dimension that there really are enough points in between? It isn't just a lot of dots separated by little distances. Or they say, you know those quantum mechanical amplitudes that you told me about, they're so complicated and absurd. What makes you think those are right? Maybe they aren't right. I get a lot of letters with such content, but I must say that such remarks are perfectly obvious and are perfectly clear to anybody who's working on this problem, and it doesn't do any good to point this out. The problem is not what might be wrong, but what might be substituted precisely in place of it. If you say anything precise, for example, in the case of a continuous space, suppose the precise proposition is that space really consists of a series of dots only, and the space between them doesn't mean anything, and the dots are in a cubic array. Then we can prove that immediately is wrong. That doesn't work. You see, the problem is not to change or to say something might be wrong, but to replace it by something, and that is not so easy. As soon as any real, definite idea is substituted, it becomes almost immediately apparent that it doesn't work. Secondly, there's an infinite number of possibilities of these simple types. It's something like this. You're sitting working very hard. You work for a long time trying to open a safe. And some Joe comes along who doesn't know anything about what you're doing or anything except that you're trying to open a safe. He says, why don't you try the combination 10, 20, 30? Because you're busy. You're trying a lot of things. Maybe you already tried 10, 20, 30. Maybe you know that the middle number is already 32 and not 20. Maybe you know that, as a matter of fact, this is a 5-digit combination. There we have it. So these letters don't do any good, and so please don't send me any letters trying to tell me how the thing is going to work. I read them to make sure that I haven't already thought of that. But it takes too long to answer them because I usually in the class try 10, 20, 30. And as usual, nature's imagination far surpasses our own. As we've seen from the other theories, they are really quite subtle and deep. And to get such a subtle and deep guess is not so easy. One must be really clever to guess, and it's not possible to do it blindly by machine. So I want to discuss the art of guessing nature's laws. It's an art. How is it done? One way you might think, well, look at history. How did the other guys do it? Well, look at history. You first start out with Newton. He has in a situation where he had incomplete knowledge. And he was able to get the laws by putting together ideas which all were relatively close to experiment. There wasn't a great distance between the observations and the tests. Now, that's the first, but now it doesn't work so good. Now, the next guy who did something, another man who did something great was Maxwell, who obtained the laws of electricity and magnetism. Well, what he did was this. He put together all the laws of electricity due to Faraday and other people that came before him, and he looked at them and he realized that they were mutually inconsistent. They were mathematically inconsistent. In order to straighten it out, he had to add one term to an equation. By the way, he did this by inventing a model for himself of idler wheels and gears and so on in space. And then he found that what the new law was, and nobody paid much attention because they didn't believe in the idler wheels. We don't believe in the idler wheels today, but the equations that he obtained were correct. So the logic may be wrong, but the answer is all right. In the case of relativity, the discovery of relativity was completely different. There was an accumulation of paradoxes. The known laws gave inconsistent results, and it was a new kind of thinking, a thinking in terms of discussing the possible symmetries of laws. And it was especially difficult because it was at the first time realized how long something like Newton's laws could be right and still ultimately be wrong. And second, that ordinary ideas of time and space that seem so instinctive could be wrong. Quantum mechanics was discovered in two independent ways, which is a lesson. There again, and even more so, an enormous number of paradoxes were discovered experimentally, things that absolutely couldn't be explained in any way by what was known. Not that the knowledge was incomplete, but the knowledge was too complete. Your prediction was this should happen, it didn't. The two different routes were one by Schrödinger, who guessed the equation, another by Heisenberg, who argued that you must analyze what's measurable. So two different philosophical methods reduced to the same discovery in the end. More recently, the discovery of the laws of this interaction, which are still only partly known, had quite a somewhat different situation. Again, this time it was a case of incomplete knowledge, and only the equation was guessed. The special difficulty this time was that the experiments were all wrong. All the experiments were wrong. Now, how can you guess the right answer when you calculate the results it disagrees with the experiment, and you have the courage to say the experiments must be wrong? I'll explain where the courage comes from in a minute. Now, today, we haven't any paradoxes. Maybe. We have this infinity that comes if we put all the laws together. But the rug-sweeping people are so, sweeping the dirt under the rug, are so clever that one sometimes thinks that's not a serious paradox. The fact that there are all these particles doesn't tell us anything except that our knowledge is incomplete. Now, I'm sure that history does not repeat itself in physics, as you see from this list, and the reason is this. Any scheme, like think of symmetry laws, or put the equations in mathematical form, or any of these schemes, guess equations and so on, are known to everybody now, and they're tried all the time. So if the place where you get stuck is not that, you try that right away. We try looking for symmetries. We try all the things that have been tried before. But we're stuck. So it must be another way next time. So each time that we get in this logjam of too much trouble, too many problems, it's because the methods that we're using are just like the ones we used before. We try all that right away. But the new scheme, the new discovery is going to be made in a completely different way. So history doesn't help us very much. I'd like to talk about a little bit about this Heisenberg's idea that you shouldn't talk about what you can't measure, because a lot of people talk about that without understanding it very well. They say in physics you shouldn't talk about what you can't measure. If what you mean by this, if you interpret this in this sense, that the constructs or inventions that you make, that you talk about, must be such a kind that the consequences that you compute must be comparable to experiment. That is, that you don't compute a consequence like a moo must be 3 goos when nobody knows what a moo and a goo is. That's no good. If the consequences can be compared to experiment, then that's all that's necessary. It is not necessary that moos and goos can't appear in the guess. That's perfectly all right. You can have as much junk in the guess as you want, provided that you can compare it to experiment. That's not fully appreciated because it's usually said, for example, people usually complain of the unwarranted extension of the ideas of particles and paths and so forth into the atomic realm. Not so at all. There's nothing unwarranted about the extension. We must, and we should, and we always do, extend as far as we can beyond what we already know, those things, those ideas that we've already obtained. We extend the ideas beyond their range. Dangerous, yes. Uncertain, yes. But the only way to make progress. It's necessary to make science useful, although it's uncertain. It's only useful if it makes predictions. It's only useful if it tells you about some experiment that hasn't been done. It's no good if it just tells you what just went on. So it's necessary to extend the ideas beyond where they've been tested. For example, in the law of gravitation, which was developed to understand the motion of the planets. If Newton simply said, I now understand the planet, and didn't try to compare it to the Earth's pull, and then we can't, if we're not allowed to say, maybe what holds the galaxies together is gravitation. We must try that. It's no good to say, well, when you get to the size of galaxies, since you don't know anything about it, anything can happen. Yes, I know, but there's no science in it. There's no understanding, ultimately, of the galaxies. If you, on the other hand, you assume that the entire behavior is due to only known laws, this assumption is very limited and very definite and easily broken by experiment. What we're looking for is just such hypotheses. Very definite, easy to compare to experiment. And the fact is that the way the galaxies behave so far doesn't seem to be against the proposition. It would be easily disproved if it were false, but it's very useful to make the hypothesis. I'll give another example, even more interesting and important. Probably the most powerful assumption in all of biology, the single assumption that makes the progress of biology the greatest, is the assumption that everything the animals do, the atoms can do. What? That the things that are seen in the biological world are the results of the behavior of physical and chemical phenomena with no extra something. You could always say, well, when we come to living things, anything can happen. If you do that, you never understand the living thing. It's very hard to believe that the wiggling of the tentacle of the octopus is nothing but some fooling around of atoms according to the known physical laws. But if investigated with this hypothesis, one is able to make guesses quite accurately as to how it works, and one makes great progress in understanding the thing. So far, the tentacle hasn't been cut off. What I mean is, it hasn't been found that this idea is wrong. It's therefore not unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then how can you say it's likely, that it's unlikely? Well, that's the way, that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the result of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence. It's just more likely, that's all. And it's a good guess. And we always try to guess the most likely explanation, keeping in the back of the mind the fact that if it doesn't work, then we must discuss the other possibilities. Now, how to guess at what to keep and what to throw away. You see, we have all these nice principles and known facts and so on, but we're in some kind of trouble. That we get the infinities or we don't get enough of a description, we're missing some parts, And sometimes that means that we have probably to throw away some idea. At least in the past, it's always turned out that some deeply held idea has to be thrown away. And the question is what to throw away and what to keep. If you throw it all away, it's going a little far, and you don't got much to work with. After all, the conservation of energy looks good, and it's nice, I don't want to throw it away, and so on. To guess what to keep and what to throw away takes considerable skill. Actually, it probably is merely a matter of luck, but it looks like it takes considerable skill. For instance, probability amplitudes are very strange, and the first thing you'd think is that the strange new idea is clearly cockeyed. And yet everything that can be deduced from the ideas of the existence of quantum mechanical probability amplitude, strange though they are, all the things that depend on that work throughout. All these strange particles work 100%. Everything that depends on that seems to work. So I don't believe that idea is wrong, and that when we find out what the inner guts of this stuff is, we'll find that idea is wrong. I think that part's right. I'm only guessing. I'm telling you how I guess. For instance, that space is continuous is, I believe, wrong. Because we get these infinities and other difficulties, and we have some questions as to what determines the sizes of all these particles, I rather suspect that the simple ideas of geometry extended down into infinitely small space is wrong. I don't believe that space, I'm making a whole, I'm only making a guess. I'm not telling you what to substitute. If I did, I would finish this lecture with the known law, of course. Some people have used the inconsistency of all the principles to say that there's only one possible consistent world. That if we put all the principles together and calculate very exactly, we will not only be able to use the principles, but discover that these are the only things that can exist and have the thing consistent. That seems to me like a big order. I don't believe that sounds like wagging the tail by the dog. That's right. Wagging the dog by the tail. I believe that you have to be given that certain things exist, a few of them, not all the 48 particles, or the 50-some-odd particles. A few little principles, a few little things exist, like electron and something is given. And then with all the principles, the great complexities that come out with probably a definite consequence. But I don't think you can get the whole thing from just arguments about consistency. Finally, we have another problem, which is the question of the meaning of the partial symmetries. I think I better leave that one go because of a shortage of time. Well, I'll say it quickly. These symmetries, like the neutron and proton, are nearly the same, but they're not, for electricity. Or that the law of reflection symmetry is perfect, except for one kind of reaction, are very annoying. The thing is almost symmetrical, but not. Now, two schools of thought exist. One will say it's really simple, they're really symmetrical. But there's a little complication which knocks it a little bit cockeyed. Then there's another school of thought which has only one representative, myself, which says, no, the thing may be complicated and become simple only through the complication. Like this. The Greeks believed that the orbits of the planets were circles. And the orbits of the planets are nearly circles. Actually, they're ellipses. The next question is, well, they're not quite symmetrical, but they're almost circles. They're very close to circles. Why are they very close to circles? Why are they nearly symmetrical? Because of the long, complicated effects of tidal friction, a very complicated idea. So it is possible that nature in our heart is unsymmetrical for these things, but in the complexities of reality, it gets approximately looking as if it's symmetrical. The ellipses look almost like circles. It's another possibility. Nobody knows. It's just guesswork. Now, another thing that people often say is that for guessing, two identical theories, suppose you have two theories, A and B, which look completely different psychologically, have different ideas in them and so on, but that all the consequences that are computed are exactly the same. They say they even agree with experiments. The point is, though, that the two theories, although they sound different at the beginning, have all consequences the same. It's easy usually to prove that mathematically by doing a little mathematics ahead of time to show that the logic from this one and this one will always give corresponding consequences. Suppose we have two such theories, how are we going to decide which one is right? No way, not by science, because they both agree with experiment to the same extent. There's no way to distinguish one from the other. So two theories, although they may have deeply different ideas behind them, may be mathematically identical and Usually people say then in science one doesn't know how to distinguish them, and that's right. However, for psychological reasons, in order to get new theories, these two things are very far from equivalent, because one gives a man different ideas than the other. By putting the theory in a certain kind of framework, you get an idea what to change, which would be something, for instance, in theory A that talks about something that you say, I'll change that idea in here. But to find out what the corresponding thing is you're going to change in here may be very complicated. It may not be a simple idea. In other words, a simple change here makes maybe a very different theory than a simple change there. In other words, although they're identical before they're changed, there are certain ways of changing one which look natural, which don't look natural in the other. Therefore, psychologically, we must keep all the theories in our head. And every theoretical physicist that's any good knows 6 or 7 different theoretical representations for exactly the same physics, and knows that that they're all equivalent, and that nobody is ever going to be able to decide which one is right at that level, but he keeps them in his head hoping that they'll give him different ideas for guessing. Incidentally, that reminds me of another thing, and that is that the philosophy or the ideas around the theory, a lot of ideas, you say, I believe there is a space-time or something like that in order to discuss your analysis, that these ideas change enormously when there are very tiny changes in the theory. In other words, for instance, Newton's ideas about space and time agreed with experiment very well. But in order to get the correct motion of the orbit of Mercury, which was a tiny, tiny difference, the difference in the character of the theory with which you started was enormous. Reason is, these are so simple and so perfect. They produce definite results. In order to get something to produce a little different result, it has to be completely different. You can't make imperfections on a perfect thing. You have to have another perfect thing. So the philosophical ideas between Newton's theory of gravitation and Einstein's theory of gravitation are enormous. The differences, rather, are enormous. What are these philosophies? These philosophies are really tricky ways to compute consequences quickly. A philosophy, which is sometimes called an understanding of the law, is simply a way that a person holds the laws in his mind so as to guess quickly at consequences. Some people have said, and it's true, for instance, in the case of Maxwell's equations and other equations, never mind the philosophy, never mind anything of this kind, just guess the equations. The problem is only to compute the answers so that they agree with experiment, and is not necessary to have a philosophy or argue or words about the equation. That's true in a sense, yes and no. It's good in the sense you may be, if you only guess the equation, you're not prejudicing yourself and you'll guess better. On the other hand, maybe the philosophy helps you to guess. It's very hard to say. For those people who insist, however, that the only thing that's important is that the theory agrees with experiment, I would like to make an imaginary discussion between a Mayan astronomer and his student. The Mayans were able to calculate with great precision the predictions, for example, for eclipses and the position of the moon in the sky, the position of Venus, and so on. However, it was all done by arithmetic. You count a certain numbers, you subtract some numbers, and so on. There was no discussion of what the moon was. There wasn't even a discussion of the idea that it went around. There was only calculate the time when there would be an eclipse or the time when it would rise, the full moon, and when it would rise, half moon, and so on. Just calculating only. Suppose that a young man went to the astronomer and said, I have an idea. Maybe those things are going around, and there are balls of rocks, like rocks out there. We could calculate how they move in a completely different way than just calculate what time they appear in the sky and so on. So, of course, the Mayan astronomer would say, yes, how accurate can you predict eclipses? He said, I haven't developed the thing very far. He says, but we can calculate eclipses more accurately than you can with your model, and so you must not pay any attention to this because the mathematical scheme is better. And there's a very strong tendency of people to say against some idea, if someone comes up with an idea and says, let's suppose the world is this way, and you say to him, well, what would you get for the answer for such and such a problem? And he says, I haven't developed it far enough. And you say, well, we have already developed it much further, and we can get the answers very accurately. So it is a problem as to whether or not to worry about philosophies behind ideas. Another thing, of course, that one can use to guess is to guess new principles. For instance, in Einstein's gravitation, he guessed, on top of all the other principles, the principle that corresponded to the idea that the forces are always proportional to the masses. He guessed the principle that if you were in an accelerating car you couldn't tell that from being in a gravitational field. And by adding that principle to all the other principles, was able to deduce correct laws of gravitation. Well, that outlines a number of possible ways of guessing. I would now like to come to some other points about the final result. First of all, when we're all finished and we have a mathematical theory by which we can compute consequences, it really is an amazing thing. What do we do? In order to figure out what an atom is going to do in a given situation, we make up a whole lot of rules with marks on paper, carry them into a machine which opens and closes switches in some complicated way, and the result will tell us what the atom is going to do. Now, if the way that these switches opens and close was some kind of a model of the atom, in other words, if we thought the atom had such switches in it, then I would say, well, I understand more or less what's going on. But I find it quite amazing that it's possible to predict what will happen by what we call mathematics, which is simply following a whole lot of rules which have nothing to do, really, with what's going on in the original thing. So, in other words, the closing and opening of switches in a computer is quite different, I think, than what's happening in nature. And that is, to me, very surprising. And finally, I would like to say, one of the most important things in this guess, compute, consequences, compare, experiment business is to know when you're right. It is possible to know when you're right way ahead of computing all the consequences. Of checking all the consequences. You can recognize truth by a beauty and simplicity. It's always easy when you've got the right guess and make 2 or 3 little calculations to make sure it isn't obviously wrong to know that it's right. When you get it right, it's obvious that it's right, at least if you have any experience. Because what happens is that more comes out than goes in. That your guess is, in fact, that something is very simple. And at the moment you guess that it's simpler than you thought, then it turns out that it's right, if it can't be immediately disproved. Doesn't sound silly. If you can't see immediately that it's wrong and it's simpler than it was before, then it's right. The inexperienced and crackpots and people like that will make guesses that are simple all right, but you can immediately see that they're wrong. That doesn't count. And others, the inexperienced students, make guesses that are very complicated, and it sort of looks like it's all right, but I know that's not true, because the truth always turns out to be simpler than you thought. What we need is imagination, but imagination in a terrible straitjacket. We have to find a new view of the world that has to agree with everything that's known, but disagree in its predictions somewhere, otherwise it's not interesting. And in that disagreement, agree with nature. If you can find any other view of the world which agrees over the entire range where things have already been observed, but disagrees somewhere else, you've made a great discovery. Even if it doesn't agree with nature, it's darn hard. It's almost impossible. Not quite impossible. To find another theory which agrees with experiments over the entire range in which the whole theories have been checked, and yet gives a different consequences in some other range. In other words, a new idea is extremely difficult. It takes a fantastic imagination. And what of the future of this adventure? What will happen ultimately? We are going along guessing the laws. How many laws are we going to have to guess? I don't know. Some of my colleagues say, well, science will go on, but certainly there will not be perpetual novelty, say, for 1,000 years. This thing can't keep on going. We're always going to discover new laws, new laws, new laws. If we do, it'll get boring, that there are so many levels, one underneath the other. So the only way that it seems to me that what can happen in the future is first, either that everything becomes known, that all the laws become known. That would mean that after you had enough laws, you could compute consequences, and they would always agree with experiments, which would be the end of the line. Or it might happen that the experiments get harder and harder to make, more and more expensive, that you get 99.9% of the phenomena, but there's always some phenomenon which has just been discovered that's very hard to measure, which disagrees. It gets harder and harder to measure. As you discover the explanation of that one, there's always another one, and it gets slower and slower and more uninteresting. That's another way that it can end. But I think it has to end in one way or another. And I think that we are very lucky to live in the age in which we're still making the discoveries. It's an age which will never come again. It's like the discoveries of America. You can only discover it once. It was an exciting day when there was investigations of America. But the age that we live in is the age in which we are discovering the fundamental laws of nature. And that day will never come again. I don't mean we're finished. I mean we're right in the process of making such discoveries. It's very exciting, marvelous. But this excitement will have to go. Of course, in the future there will be other interests. There'll be interests of the connection of one level of phenomena to another, phenomena in biology and so on, all kinds of things. Or if you're talking about explorations, exploring planets and other things. But there will not still be the same thing as we're doing now. It'll be just different interests. Another thing that will happen is that if all is known, ultimately, if it turns out all is known or it gets very dull, the vigorous philosophy and the careful attention to all these things that I've been talking about will gradually disappear. The philosophers who are always on the outside making stupid remarks will be able to close in because we can't push them away by saying, well, if you were right, you'd be able to guess all the rest of the laws. Because when they're all there, they'll have an explanation for it. For instance, there are always explanations to why the world is three-dimensional. Well, there's only one world, and it's hard to tell if that explanation is right or not. So if everything were known, there would be some explanation about why those are the right laws. But that explanation will be in a frame that we can't criticize by arguing that that type of reasoning will not permit us to go further. So there will be a degeneration of the ideas, just like the degeneration that great explorers feel occurs when tourists begin moving in on the territory. Now, I must say that in this age, people are experiencing a delight, a tremendous delight, the delight that you get when you get how nature will work in a new situation never seen before. From experiments and information in a certain range, you can guess what's going to happen in a region where no one has ever explored before. It's a little different than regular exploration. There's enough clues on the land discovered to guess what the land is going to look like that hasn't been discovered. And these guesses, incidentally, are often very different than what you've already seen. It takes a lot of thought. What is it about nature that lets this happen? That it's possible to guess from one part what the rest is going to do? That's an unscientific question. What is it about nature? I don't know how to answer it. And I'm going to give, therefore, an unscientific answer. I think it is because nature has a simplicity and, therefore, a great beauty. Thank you very much.